Yeah. Yeah.
It's just my, it's like, oh no, there you go. Or time. Yeah, you just the geometry is so poor, and then what's so funny is that it then goes to the metal people because we printed these sections, and they instead of fixing it, but they could have they would have done a better job if I was just like do a figure eight,
right?
Kind of like not like this shit is mine,
Right? They tried to follow
but they followed it exactly. So yeah, there's like a lot of that early stage like digital application, like stumbling naivete. Process. That project really was that.
I know you're talking. I designed a hardware chair that became like pulled up out of reaching for hardware. And I want to be. I didn't even know I did something, and then make it up. And the chair was pretty ugly.
Yeah.
The form was just not very smooth. Because we could take like one pass of form. All the technical at some point, and it wasn't just for parametric, so it's not like you can go back and apply that to the form without doing it all over.
Yeah, totally. Yeah. It's so funny. I know this was like actually, even though it seemed through long, it was actually their meta calls or whatever meta. It was like that wasn't actually that kind of geometry that they do.
It wasn't ruled.
Wasn't ruled, yeah. So it's kind of funny. But yeah, a lot of that early stuff.
Yeah, it's also funny how the generation will see the flaw in it. They don't realize that it was like there was no where to look, at least in this space architecture. There wasn't just a problem. Anything that bigger than the chair were used to the digital process. It wasn't shampoo bottle relation. It didn't have.
Kick it off. It's this new year or two, and it's them and this filmmaker kind of and then there's a Q&A at the end. The guy who's moderating.
In an effort to try and keep a schedule, I think we'll probably try and get started now. So please join us in the auditorium. Take your seats, please.
He's also still moving about it.
Yeah.
Yeah.
Using this topic for 5 years. You did this one? I think I use your mine, and I need your implementation still.
Oh.
I'm usually. I have a. I don't have a thumb drive, no, but I have a. I don't have one either. What format is it?
You want to email it? Is N A S like one. Right?
Yeah.
Jonas A H.
A H.
F at DT. .edu.
ET.
Be like Victor
Oh.
at town.
All right. E.
.edu.
I can also send you an email back with a link to drive.
Big thing.
My email. Give you my email. Thank you.
I'm gonna do a quick introduction, and while I do, I'll just leave this splash screen up, and then we'll just switch over your USB. So you won't. You'll need this, right?
I have one. Don't you?
You won't.
Yeah.
Great. Right.
That's okay. Yours will last longer. In case somebody wants it.
I also have this clicker, a USB clicker. I've got this USB clicker. And yeah, there it is.
So far, I'm not getting your email. Okay. Thank you.
It did say it sent them.
Okay. Here it is. That's great.
Okay, well, I'd like to welcome everyone to AMT 2025. It's a pleasure to have everyone here. Maybe we can just get a round of applause for all the presenters and everybody. I want to kind of frame the conversation and just give a few remarks before we get into everything. So this is kind of the official opening of the conference. So we had a keynote last night, Marlon Blackwell, and we had the soft opening with the workshops that are happening concurrently. So the building is busy with life and vibrant creative actions happening currently, and we're really happy that the students are engaged with the workshops and learning more about how to engage with material. So that's something that we're really happy that's happening, and just want to kind of frame this conversation in terms of my own research. I'm really interested in thinking about material from a fundamental perspective and thinking about how we can scale material. Obviously, the most novel and innovative materials start with kind of small experimentation and then grow from there. From my days in graduate school, one of my professors had suggested that the best way to innovate or change or help to push architecture and design forward is to think about a very specific and fundamental element, and then focus on the innovation within that one element. And so I've chosen material as that fundamental element, trying to work with. And so that's why we are all here together today, is to think about material and think about how it can be more accessible to more people through technology, through innovation. And we have quite a number of individuals that have gathered here. We have several keynote speakers. We're grateful for their presence today and tomorrow. We started with Marlon Blackwell. We have Jonas Hauptmann, who's a bamboo expert. And we have Juhan Park from Korea. He's doing a lot of really interesting technology. We'll be talking about in-situ resource utilization on the moon and in those situations. And then we have tomorrow Dora Epstein-Jones, who's a history theory expert. And she's going to be bringing us some more theoretical aspects of material. And then tomorrow afternoon, we'll have Philip Beasley, who will close the conference. And so we're really grateful for the breadth of the individuals who bring expertise from different areas about material. And I think we're really fortunate that those keynotes have also brought individuals to the conference just by their expertise. And that's also really wonderful. So we have a lot of really great conversations that will be able to be happening. And it's meant to be as inter and collaborative as possible. That's kind of the intent. Oftentimes these material focused academic conversations happen very siloed, and the intent is that the breaking up of those silos happens here. I also want to thank the organizing students who helped me with this process. George and Jonathan and Carolina and Ali have been kind of fundamental to planning this conference. And in those times when the emails were coming in faster than I could respond to them, they were my saving grace, and I'm really grateful for their efforts and help with this whole process. And so that's kind of a wonderful thing to have a great team. I also want to highlight the graphics. These graphics are research that Jonathan and I endeavored on, thinking about how we can use high fidelity large language model generated imagery, but then try and force it to create abstract form. And it was a challenging process, but we had a lot of fun with it. And so these are meant to be evocative landscapes that think about the future of material. That's the whole intent with these images. And I only bring that up to kind of help to frame that discussion even further. So without any further pontificating, I'll turn the time over to Jonas Hauptmann, who will be running this morning's panel. The keynotes are organized in a way so that they have freedom within their sessions and can organize their sessions how they will. With a few key points, we're really interested in a dialogue. So trying to have some kind of a panel discussion, a keynote obviously from them, and then they'll be kind of framing that conversation at the beginning by giving an introduction. So let's give it up for Jonas Hauptmann. Thank you so much. I can change that. There you go. I got it.
Hey, good morning. So just wanted to thank the organizers to start with, and we're really looking forward to sharing some work and learning from others in the session whose work we don't know very well yet, but we'll learn more about this morning. So I'm just going to share a couple of slides in the beginning, and then I'll close the session with most of my presentation keynote. But just to say that we'll have presentations from the following people: Captain, Ali, Kelly, Tizia, and Wiley. And what I think is really nice, just last night, Spencer kind of shuffled the order a little bit. And if I would have had this session, I would have renamed it biomaterials. But I think that the alt is quite important. And as you'll see in the next couple of slides, I think that my inclusive way of seeing material embraces this idea of alternative materials that are effectively those of reuse. So I'd like us just to think about a couple of ideas to frame the conversation at a very kind of high level. Like, where do the materials come from? This is a really fundamental question. In reality, effectively, you could say they're not all earthen. It came from, from the cosmos, but you could definitely say they're earthen materials. But at what consequence do these materials play as we find ourselves in composition with them, as we acquire them? Do we extract them, or do we harvest them, cultivate them, or reclaim them? And I think when we get to the right two categories, we might wind up in a safer position moving forward. And if we remain in the left two categories too wholeheartedly as a civilization, trouble is already brewing. So I'd also like to make a kind of bold statement. I think we tend to, add some morality or definition for what is a biomaterial. But if it's from the earth, perhaps they're all biomaterials. But time, what about time materials? Maybe this is a way to think about it. So the work that I engage in is looking at materials that take less than 10 or 20 years to renew. To me, this is really an important idea. And between the alt materials of reuse and these fast regenerate materials, maybe this is the way towards the future. So I'm going to leave it at that point until after, actually I can get back, I have a few more slides. So I'm hoping to frame there's several bamboo papers. So I'm going to try to frame just a couple more thoughts about bamboo, and then I will stop. So what I like about some materials more than others is the ability to thoughtfully engage as humans in their cultivation in a manner that is what I would say more truly sustainable. So you could say that the timber is sustainable and depends on the lens of time. Some are arguing that the current rate of extractive use, 500 years, and we won't have timber the way we do today. Many other materials, stone, etc., these time frames are even shorter. Those that come from oil that comes from the ground that are petroleum-based, even shorter. Bamboo is unique that it's regenerative, it's agricultural, it grows as quickly as 5 years once you have a mature growth, and it has this sort of extraordinary structure as a material. It has a skin that's as hard as glass. It has a geometry that is well balanced and nearly round. It has diaphragms that stop it from crushing over distances. And so I find great inspiration in this, and so do some of the folks that are going to be talking this morning. Also, I think that we have, a really warped sense of durability in architecture. We have this grand idea that our buildings should last for 1,000 years, when many of them only need to last for 20 to 50 years. And some of these technologies that are 1,000 years old have stood for 200 years, but maybe they don't need to. Why are we asking housing to stand for more than 50 years or 100 years? I think the question of reuse might be an important one to bring into the conversation, but just the notion that we've been planning to have buildings that are durable enough to kick as hard as we want for the last 100 years, maybe it's a little bit grandiose of our culture and of many cultures to think about buildings in this way. So I think the rest, I'm going to see what happens with the papers before I go on, so that I don't steal their thunder. Let me just go back to my first slide. So Calcutta is going to present first. I'm going to disconnect you, Calcutta, because I want to meet your bio, but I don't want to share that document at the same time. Then when you get up here, you can plug in. So just a couple of comments. So I met Calcutta a couple of years ago now, has come to VT to to work on a doctoral degree, PhD in architecture, and has kind of the kind of bold idea that maybe the work we're doing could impact kind of built environment in Ethiopia. Kapitan has her bachelor's and master's from the Ethiopian Institute of Architecture, Construction, and City Development in Ethiopia, and we should like to welcome her with a round of applause.
Morning won't be able to hear you. You don't have the mic closed.
Thank you for having me. Today I'll present the integration of bamboo and industrial housing for Ethiopian housing industry. But like before proposing that, this research focus on the opportunity and the challenge of adapting those technologies and both the material and technology. So I will try to frame the problem in the background, and then I will describe why bamboo, why industrial housing construction, and then I will try to see different case studies, and then we'll continue with the research approach and recommendation after that and conclusion. So to give you a little bit about background, Ethiopia is rapidly urbanized, and that urbanization is driven by population growth and rural urban migration. It creates a significant increase the demand for housing, and particularly in major cities like Addis Ababa. So the country urbanization rate exceed from 3.8% to 5.4% per year, resulting in substantial pressure on the housing sector. For example, this estimation will indicate that in Addis Ababa alone, which is the capital city of Ethiopia, the backlog of the housing reach approximately 1.2 million units, with projected demand of 655,000 housing units between 2015 up to 2025. However, the supply remains significantly lower, with an estimated nationwide annual production of only 165% in housing units. So this creates a huge demand in housing. And on the other side, the essential construction materials such as cement, steel, and aggregates has experienced continuous price inflation worsened by the supply chain distribution and macroeconomic instability. The heavy demand on imported materials further compound these issues and create a huge expense on the housing market. And in addition to that, there are studies, for example, involving energy and carbon emission of these materials, and it identified that cement, hollow concrete blocks, and reinforced bar as a major energy consumption, and primarily they are the one who emit CO2. This material collectively accounts for 94% of the involved energy and 98% of the CO2 emission in the assessed buildings. On the other side, there is like a huge bamboo. Ethiopia has one of the largest bamboo resources in Africa, which covers around 1 million hectares, which makes it like the country is 67% of the bamboo resource in Africa, and also around 7% globally. So, but despite all those resources, the use of bamboo is limited, and it's limited on the furniture making, fences, and vernacular construction, and as a firewood also they use it. So as a result, for the building material, it's like utilizing a huge scale. So there are two indigenous bamboo species which are highland bamboo and lowland bamboo that grows in different locations of Ethiopia, and they both have exhibited rapid growth rate and significant biomass productivity, makes them valuable for application in construction, furniture, paper production, and bioenergy. Bamboo has a lot of benefits, but in the Ethiopia context, and for it like affordable housing, because we have like a resource and durability, rapid renovability, the higher accessibility alternative for construction. This significantly reduce greenhouse gas emission by 70% compared to conventional construction concrete structure. It also enhanced resilience, particularly in climate vulnerable regions like Ethiopia. So they are good in earthquake areas. And also, additionally, they create a social activity that generate employment opportunities for different group of people. So it has also a benefit of for forest ecosystem, which can create ecological benefit, carbon sequestration, solid stabilization, and also the social economic advantage that enhance the rural economy for the farmers, and all the value chain can be benefited from bamboo. But all this kind of has also a challenge, especially in the country like Ethiopia, adapting bamboo as a building material is challenging, and it has like technical challenge like standardized. There is a lack of standardized process and preservation techniques, so that creates a huge gap adapting to the larger scale. Additionally, the limited availability of high cost associated with the chemical preservatives and seasoning techniques, and also like the species in Ethiopia, the two species are exhibited lower natural resistance of biodegradations compared to certain indigenous species, further intensified the need for effective treatments. So, and on the other side, moreover, like the absence of formal standards for bamboo processing grading complicated the integration of bamboo into modern constructions. So, and the other side, there is also a marketing and supply chain challenge that limits the effectiveness of bamboo sector. So a weak bamboo value chain and inadequate market infrastructure result in a poor linkage between producer, processor, and end user. Additionally, small-scale farmers and producer frequently face difficulties due to lack of reliable market access. So insufficient facilities and inadequate financial intensity to invest in bamboo cultivations. And also it has a logistical constraints, such as poor transportation network and inadequate storage facility further contribute to the supply inconsistency and elevated costs. And it was also a big challenge in accepting bamboo as a building material. So there is a perception. Bamboo is commonly viewed as a material suitable primarily for low-income housing, lead to negative perception and reduced demands, particularly in urban areas where modern aesthetic and structural durability are valuable. And in addition to that, there is a knowledge and expertise gap. So there is a limited availability of technical experts and insufficient research focusing on modern bamboo construction technologies. Additionally, a shortage of training architects, engineers, and craftsmen in bamboo construction restrict innovations and limit the scalability of bamboo-based projects. So, to define industrial housing construction it's a holistic term that includes prefabrication, modernization, modularization of site fabrication, or modern method of construction. So why we are adapting or proposing to industrialize housing construction through bamboo is because it has like a huge benefits. It ensures like project cost, reduce post construction and labor expenses, and minimize on-site building durations, leading to improve overall project timeline. Additionally, off-site construction deliver better quality outcomes, reduce health and safety risk, lower environmental impacts, and it promotes resource efficiency. And also it has like there is a research in World Economic Forum. They suggested like adapting industrial housing construction significantly contribute to the GDP growth and employment in developing countries. So by improving essential infrastructures, utility service, and providing affordable housings, it enhances living standards and also stimulate broader economic development. So, but it has also a challenge to adapt industrial housing construction in Ethiopia. So one of the key challenges to adapt is the fragmented regulatory framework and supportive government policies. Despite the national effort to modernize the construction industry, there is a weak regulation and absence of intensive like tax break or subsidize how we have slowed the integration of prefab and modular method constructions. Additionally, the government prefer for the labor-intensive method as a means of employment generation for further delayed adapting the technology. And also there is another technological, economically, cultural factor also limit the implementation of IHC. The sector relies heavily on outdated techniques, which is limited R&D and a shortage of investment in prefabrication facility and skilled labor. And also there is a supply chain issue depending on the imported material and the lack of local manufacturing increase the quality of prefabricated house, and a shortage of trained professionals contribute to the poor implementation of the IHC. And also there is still a negative perception about adapting IHC. There is a public skepticism and lack of promoting the technology. So as I mentioned, like it has integrating both bamboo and IHC can be has a potential like to reduce costs, minimize environmental impact, and also improve housing affordability. There are research and there are case studies. I will explain those examples later. So those examples show significant reduction in carbon footprint. So one of the examples is CBFT, which is a cement bamboo frame technology. It is an innovative and sustainable housing solution that combine bamboo stay-side springs and flexibility with cement-based reinforcement. Utilize treated bamboo poles in a frame system stabilized by concrete foundation and cement plastered wall. CBFT enhance structural resilience against extreme weather, including earthquake. The integration of steel reinforcement joints and adhesive international standard like ISO ensure durability and safety. Environmentally, the CBFT can be reduced embodied carbon by up to 70% compared to conventional concrete and brick system. So material innovation such as using flattened bamboo instead of steel mesh further reduce the resilience of high emission material. CBFT also promote affordability and social equity by lowering construction costs through local labor and prefabrication with successful implementation in low-income housing by organizations like Base Baha'i in Philippines. And the second one is a mass bamboo, which is a light modified bamboo panel such as developed by Professor Jonas Hoffman, offers a sustainable and structurally efficient alternative to conventional building materials. Unlike fully reconstructed composite mass wood, retains the natural form of bamboo columns arranged in cross-laminated layers to enhance load distribution, straightness, and stiffness while reducing rolling shear. This system leverages digital analysis and fabrication to optimize performance and enable scalable prefabrication, particularly in regions in resources like Ethiopia. Sustainability is further supported by minimizing material waste and energy use. Data-driven selection of bamboo column based on diameter, straightness, and nodes distribution using biomass adhesive. Also reduced reliance on synthetic driven bamboo panels as promise offering the alternative to a mass timber and concrete in sustainable architecture. So this can be also a good example to adapt to Ethiopian context. And the other and a bigger scale is a bamboo board. It's It offers cutting-edge solutions for sustainable construction through its engineered wood hybrid wall system known as a prime wall. So this prefabricated dual panel wall system eliminates internal framing and reduce thermal bridge, air leakage, and energy consumption while enhancing structural strength and sound insulation. So it makes from laminated veneer bamboo. Bamboo core panels are prefabricated off-site for rapid on-site assembly. And also the life cycle assessment of this building will show significantly reduction in embodied carbon emission due to bamboo's rapid growth and carbon sequestration capability and reduce material waste. So the system also supports the living building challenging goals while integrating digital tools like BIM ensure precision and scalability. So what are we learning from these test examples are we can adopt industrialized construction not in a bigger scale but from small to large scale. It can offer like flexible in application and benefit across different parts of the value chain. So from this value chain, a lot of sectors can be benefited and it can create an opportunity, an employment, and also an opportunity to give affordable and social equity housing. So and also the system highlights bamboo potential for seismic resilience, cost-effective prefabrication, and also it makes them more suitable for the housing need. And also we can adapt the use of like engineered bamboo panel, digital fabrication, and hybrid construction method demonstrate how bamboo can serve as a high-performance building material while supporting efficient, scalable, and sustainable housing solution within the industrial framework. So this research is a narrative literature review, and the literature review we reviewed were the literature were collected from academic database and prioritized from publication from the last 20 years, and from that it categorized like housing demand, social economy, and environmental benefit of each strategies and also case studies. So yeah, in general, we harness bamboo's potential in industrial housing construction in Ethiopia. Ethiopia must invest in research, policy support, and industrial capacity building. So establishing from small to medium scale bamboo manufacturing hubs can drive local economy, development, great job, and strengthens value chain by transforming raw bamboo into high performance bamboo material, and also and it can be benefited in a larger scale. So in the future research, there has to be a structural base. So still there is a lot in investigating the bamboo species in Ethiopia. So it's good to start from the species and taste structural stability and also scalability study will be benefited to investigate more and also to adapt one of the case studies in the context and to see a practical project within Ethiopian bamboo. So those are like the essential future research, and also it needs also policy intervention, local investment, and also technical capacity building also essential to adapt, because it needs we need to change the perception of the bamboo to be accepted in the society. So it has to start from that to the paper. So, and that's all. Thank you.
So actually, we'd just like to field at least one question. Are there any questions from the group? Okay, then I'll ask one. Let's say. So if you were as an architect in Ethiopia to develop a project right now with what you know and with the bamboo resources, what would it be? As an example.
As an example, a project.
Yeah, so a built project at any scale, out of any of these systems or materials, where would you start?
I will start. I will start first with a showcase, not like believing in the building, as kind of office or some public. So I will start as a public building before adapting to the private building. So that like people can come and see, appreciate the material, because one of the issue or the challenge adapting bamboo in this context is the social skepticism. So people are more associated material with a poor material. So they don't want to adapt to themselves. So before we have to demonstrate, before we say you have to build with this material, we have to show them how beautiful bamboo is.
And do you have confidence in species that are naturally occurring are sufficient from what you've learned so far? Can they be used for construction?
Yeah, there are like a couple of examples and also buildings done by those species. So there are research.
The biggest gap is testing and social acceptability.
Yeah.
Right? Thank you. So we're gonna have one more presentation before the break. I'm just giving a minute to call it. So the next presentation will be by Saeed and also from our lab. And he's working on his PhD, and all he talks about in the statement I asked him to write is about that. So I'm going to go from my own knowledge. So Ali, as we refer to him, comes from Iran to be with us, came first as a visiting scholar, and now he's in the doctoral program. And he has a bachelor's and a master's degree in architecture. And he's focused his studies and his efforts on computation and on AI. And the heart of his interests, I think, are more in technology, but I'm keep pulling him towards bamboo. And so he's going to share some technical work we're developing in the lab. Thanks, Ali.
Good morning. Let me say thank you, Jonas, because of introduction, and also thank you, Kalpidan, for your presentation, and Spencer for the gathering all of us to sharing our thoughts about biomaterial and methodology we can use this kind of material. Today, I'm going to present my research on digital workflow for 3D modeling of non-standard material, and my case study is bamboo pulp. Actually, I I present this research on behalf of Jonas, Professor Jonas Hartmann and Ramtin Harlaza, and also a computer science group of students. But before I want to talk about the technical issue, I want to say that why we need to use material like bamboo, and why it is really important to use this kind of material. As you can see, the material like bamboo can reach 20 feet in less than 5 years, which is really interesting when you compare it with the other kind of woods like evergreen woods or deciduous woods, which is need 30 years or 60 years to grow that much. And also, these speed of growth provides us a lot of opportunity to regenerate and give the planet to reproduce itself without without any other force. Also, in comparison to the other material like block cement and cement block and steel profile, it's really considerable to use it as a construction material. And also, there are a lot of variation of bamboo, which is provide us this opportunity to use it for different applications, such as construction to handmade art. But how we can use material as a non-standard? How can we use bamboo as a non-standard material? One of the first solution is to standardize it, which is not really good. As I think we waste a lot of material to standardize bamboo, which is not a rectangular material. So we should cut it, and we should put a lot of time to process it and make some profile or make some sheets of bamboo. The other solution is to overuse of material to be sure that it is it can be efficient, it can be strong enough to be used as a construction material, which is again a waste of bamboo material. What is the solution for using non-standard materials like bamboo to use it as a something like construction material? I believe that knowing this material and understanding its feature is a key point for optimum using of this material. So we are investigating a lot of different methods which are somehow can be adapted for scanning bamboo. We divide them into 3 main methods, which is the first one is image-based scanning method. In this category, you can see laser triangulation, structural light scanning, photogrammetry, multi-sensor fusion, CT scanning, and shapes from silhouettes. Also, the second general category is touch-based method, which are linear and angular hybrid scanners, digitizing arm with rotary encoders, wheel encoder-based linear scanners, and CNC code. And the last general category is wave-based scanning method, which is Jetson nano with depth scanners, ultrasonic 3D scanners, LiDAR, time of flight sensors. In the next step, we compare these 3 main categories in different areas such as affordability, compactness, accuracy, speed, and deployability. And you can see each of them has its strong and big points. For example, you can see in the speed, the touch-based methods are not really good. And also for example, for affordability, the image-based is not really good one. And for accuracy, the image-based and the touch-based is good, but the wave-based method are not really good. So there is not a specific method which is good for all the area, but we can optimize them for specific use like scanning bamboo. Our first try was to using CNC probing for scanning bamboo. As a normal probing, you need around 1,200 tons for scanning a 12 feet bamboo, and it takes around 20 minutes to finish this process. But we understood that if we can optimize the points, we can decrease the time of scanning, but also increase the precise of scanning and the 3D model. So before we start the scanning, we take a photo of bamboo and we understood the position of nodes. And for that area, we put more points for scanning. And in the other parts, we try to decrease the number of points for scanning. So by this method, we can save around, we can reduce the time of scanning from 20 minutes to 6 minutes. And also we improve the accuracy because we can use more points on the specific points of bamboo, I mean the nodes of bamboo. And also by this method, we can reduce the machine work, which is really important for long-term using of CNC for these kind of tasks. In the second method, we are trying to make a wheel encoder-based linear scanners specifically for bamboo scanning. So in this trials, we made a machine for scanning bamboo. The wheel travel through the bamboo lengths and it's record the position of wheel in, for example, for each second. So in this method, we can scan a 12 feet bamboo in around 2 minutes. But the accuracy decreased to 2 millimeter, which is not really bad for construction tasks. But the point is that we can make this machine with a $500 budget, which is really affordable for everyone, I think, or in all over the world. In comparison to the general category, we can see that the wheel encoder-based linear is really great in comparison to the other touch method. So by this effort, we can increase the speed, which is one of the weak points of the touch-based scanning. And also we can increase the deployability and affordability. In the third try, we use the shape from silhouettes method for scanning the bamboo. As you can see, for the image-based method, one of the critical points is the speed. And also the other one is affordability because it needs really expensive technology to do that. But we are trying to optimize this method for bamboo So we make uh, we make a we make a cage for the camera, and after that we use a motor for rotating bamboo in specific angles, and after that the other process can done in the grasshopper, which is somehow a normal software for architecture and maybe artists. By understanding the age of bamboo in the pictures, we can extract lines, and after in each pictures, and after that we can producing a 3D model of bamboo in less than 10 seconds. So the total time for the scanning and having the 3D model is around 2 minutes, and the accuracy is less than 1 millimeter. So in this picture, you can see the differences between these three methods, which is not really a big one, especially when you compare it in a 12-feet bamboo column. And at last, I provide you a chart for comparing the shape from silhouettes with other image-based method. It's increased the speed of the scanning, and also it's increased the deployability and affordability. Again, the total cost of this method can be less than $500, which is very good. To summarize all of these items, all of these methods, I want to say that although the accuracy for image-based and shape from silhouettes and will encoder is decreased, but I think they are accurate enough to apply in construction tasks, and also by using the optimized probing, we can have the maximum accuracy, but we lost some time for scanning the bamboo column. So thank you so much.
So once again, it would be great to field a question, and I'll help you. Yeah.
Actually, of both presenters on these types of bamboo construction. I really loved your presentation as well. Which is both of you refer the bamboo construction to a industrialized standard. An industrialized standard, of course, cuts, shapes, trims, and all of that to be a standard. To what extent in becoming that standard do we lose some of the natural properties of the bamboo that actually lead to its strength and abilities to act in both compression and tension and so forth? I'm not exactly following what is truly gained by working within the industrialized methods of a kind of 20th century accumulation, rather than say, now I think the task might be having to understand a kind of newer form of industrialization that doesn't necessarily need a measured piece.
So you guys want to make any answers?
I can say something. I'm not completely sure that it is the answer for your question, but I am generally a fan of using non-standard material as a non-standard material, not making standard and then using them. I believe that if we can scan them with all of the features, we can use them in a specific, for a specific task. For example, if we knew that the dimensions, if we knew that the strengths, if we knew that the color, we can use it in a specific position, which is completely different from the other bamboos. So I believe that if we can collect all the data for each bamboo column, we can use it as a non-standard material, and also it can help us to use it for a specific tasks like computational design, because in computational design, we can understand, for example, in this position, we need a bamboo with these features, for example, with specific features. And then if we have a library for our bamboo, we can select that bamboo from a big library. So my general idea to do this research is to help using non-standard material as a non-standard material, not cutting them, not making different shape of them and then using. So I'm not completely sure this is your answer, but part of it.
No, it's part, it's part of it, but that necessarily also means then that you welcome non-standard formal outcomes.
Yeah.
Actually, could you repeat it?
Well, you're just gonna make boxes.
So in other words, if you use a non-standard material, right, and you embrace its eccentricity, then the fidelity, I think it's a question of fidelity. So I'm reading into your statement a little bit. Then the fidelity of the architecture or design intention has to accept a variance, not a precise result, imprecise result.
Not necessarily an imprecise, but an absolutely advantageous to the material condition as it presents itself. So I would actually recall the notion of appropriateness, right?
Absolutely.
Yeah, and fit. But understanding that fit isn't going to be within the realm of modules necessarily, if you're really going for one thing that, in Ethiopia, that there's tons of bamboo construction. I mean, just tons of it, but none of, very little of it is standardized. Most of it is done appropriate to the lengths of bamboo that are available with the least amount of chopping and trimming.
Right. So do you have some more comments?
Yeah, making it standardized is very, in one sense, we are not just proposing making a bigger industrialized system with bamboo, but we can start from smaller scale without losing the property of the bamboo material. So then we can start from that. Only now we are using bamboo as a vernacular building, only with the force and the local knowledge. But when we make it industrialized, we can touch a lot of sectors, and also we can be benefited from that kind of.
So that's the reason why we report that more industrialized.
Yes.
And so I think throughout the day we'll get into this deeper. But what I would say is that I think that you're from what you've seen so far, that's a very keen and appropriate observation. But I think as this unfolds further, you'll see that the collective approach we're taking is sympathetic to lots of these points of view. There's another question.
Yeah, maybe just to piggyback off Dora's comment, I think the formal part of your question, asking about the kind of formal potentials in this, I think it's really interesting related to the scanning, right? So several of you shared the cross section and the kind of internal structure of the bamboo, or at least one type of bamboo. And I think what could be really interesting about where the scanning goes from here is right now you're doing kind of external formal scan of the characteristics of each single bamboo. If you were able to kind of understand through X-ray or some other type of kind of scanning or vision, you would understand the internal structure, which then might offer more flexibility, more
potential in how these things can actually be used in more.
Yeah, that's exactly.
And I would say that we actually term the sub-project that scanning is part of, sensing, not scanning, with exactly this in mind. And the question will be, do we have to see inside of it to know inside of it? And the answer with AI and a small amount of sampling is, I actually don't think so, but we're working a little bit on both. So we're going to take about a 10-minute break.
Yeah,
No, that's-
yeah. I mean, I'm wondering, if we compare it to timber and you look at traditions, particularly art traditions of furniture, of very specific furniture that's made based off like live section logs, and it's more about the craft and the craftsperson responding to the material. What do you think the pro or con of training machines to understand the material versus just training individuals, more craftspeople, more artists, more artisans to understand how to scan or read the material, to be able to make furniture or buildings or things in response to an intuitive sense of understanding?
I mean, the current state of, let's say, bamboo training and education worldwide is that there is definitely not enough skilled labor interested in the craft. I also think that there's definite limits to permissible scale. So it's difficult to make a building more than 2 stories or 3 stories tall in an urban condition that is truly built by hand. So I think that there'll never be a shortage of need for tacit knowledge in the processing of material. I think that's quite essential. But the ability to scale that to meet the unmet need for housing, particularly, and to decarbonize construction, I think that we have to find a middle ground. And that's what we're after. Any other comments before we take a break? Okay, thanks. So we'll start again in about 10 minutes.
What? This is one of the speakers. That's good to know.
Yeah.
You haven't grabbed a tote bag in the back. Please grab the tote bag. It has a program in there. Good goodies. Grab the tote bag and have it card.
Make something which is messy, good enough to achieve the gold standard of being homogeneous and equilibrium. And then really, okay, so I think it was
all of this,
Right, but but if you can close eyes, we wouldn't bring them to not fly. And for
once it can, assume that these are the and
I've uploaded your pictures.
so it can be, forward. Strengths. So it can be motivated and the boss can be
Or look at that, sure.
You actually are like relaxed sitting there. It doesn't come across that you struggle. Having lived in Germany so long, giving presentations like one, like, I never had to feel. I'm based in St. Louis. I mean, I have an office. I'm in Washington. Shifting to like Washington and San Juan.
So it's like the same. That there are certain species excels in and flying there's. Yeah. You want to stir them up. You actually want it.
It's very important research because
Yes.
we can call it all of the other research.
Yeah. And something to consider is that, Autodesk has their makerspace in Boston to do apply for use of their space. Because there's this guy, I'm trying to think of his name right now. He's basically an architect of Autodesk. Does machine work architect. He's the head architect of Autodesk. And one of the projects he's doing is scaling. He was for urban recycling, scaling his buildings in New York. Teaching robots to scan for like diagnosing materials, but there would be something that Autodesk might do. I have to find his name. I can send you the contact, but they do. You can apply to like go to work in workerspace, and then you can access all the Autodesk stuff. There's a whole bunch of teams of other people that I did a project there.
Yeah.
That's really cool. Especially if you look to just
Okay, yeah. Oh, well, those are projects from years ago. And again, he probably wasn't. He's not there. He works in New York. But Autodesk is a big. That's what I'm trying to get his name. But he does a lot of projects. So Autodesk has like architecture, design, people that they're doing research. So they would work with them to see what he was talking about. Also projects actually trying to make Autodesk help people in particular. I think it's giving them tools to it's like they have a lot of different views. I think he was very interested in machine building. High tech, they also have a couple robot, they do some bamboo. Yeah, exactly. And so they're it's been interested in the Autodesk how robots their software and also construction of bamboo
Accommodation, like other things.
Let me see if I can connect you.
Material like this that's required, like live.
Yeah, that's definitely. I mean, I think it's contradictory to the question.
I mean, I know it's important in some way. It's not, I feel like there's.
Direction, it kind of gets more attention because it's like, oh, it's not. It's like, it's innovation, like a sense of So I think those are.
Yeah.
People. Just no, it's a journey.
Is to create something very simple.
Yeah.
And also very clear.
Yes.
To do it in every function.
Yeah.
Because that's what that's.
Yeah. Well, that's why I think the photo. It's like you have software, the laptop and the phone, or even just a phone.
Yeah, that's really interesting.
Just giving information as opposed to tools or some sort of.
Oh, no, okay. Yeah, that's gonna be very unlearning, you know, it's like, it's.
Very costly. So, you know, anyways. So you, well, it's when you, when it's not legal, pretty like, judge them.
Doing something wrong.
Architectural forms from those before. Thought it was very interesting. It's much better. Arts and neighbors. And these are the people working on I don't know exactly which technology they were using, but there was some reactive concept and showing how things.
Strong team. Or come back.
You did great. That's good. You got like all the key foundation stuff. It's like, oh, good.
We're starting in 5 minutes.
So.
Is there any such thing? That degree,
What exactly?
like the rub is going to not do anything.
Well, consider.
Always going to go first.
Actually, are you still reading right off here? Well,
You had the experience.
yeah, that's what if I can edit on your phone. Because I couldn't do it.
Make it easy.
I'll make it very easy.
What are you pointing at? Yeah. Well, this is sort of. I told him it had only changed. I never. So this is. All points to stop the big problem.
John Rock. John Rock.
You know, but I never knew him, but yeah. My only investment.
Yeah, yeah. So that's great.
Yeah.
That's right. Yeah.
And we were the timing's right.
No, that would be like fall, spring.
Yeah, by then, so if we can make it.
I wonder exactly how solid it is.
Which would be in
Bring my
time. Right.
Basically, a transport solution.
My point is like, we could do. 30 minutes. And so basically, we try to aggregate some of the funding towards.
Oh, wait, yeah, yes. I only have 1 year. My funds is.
That's, we would only be like, we start. Yeah. And then, what would be that, you would come to you second, third. We probably would go to get to or to a smart either one. So we could be already.
That would be great.
Yeah, so there needs to be a couple of.
Yeah, you do it. And I haven't, we only have a little longer. It was a stream of research that kind of.
Yeah.
Cool. That's about like planting value. In urban areas.
Cool. Yeah, I'm very interested in like. This is not a true story, but it's a beautiful metaphor that Peter.
Data.
So basically, it's in Oxford University. This theme through 100 years ago, but it's not true.
Oh, but it's a.
He's like, he's pretty sure he debunked it. I mean, it's like sort of true because like they were thinking about the future buildings, but that theme was not one that was replaced in such a rare tree. So that falls.
Oh,
So you would replace it with something newer with more joints.
although I worked on a short project. He's actually rebuilding short jobs. It didn't take us. And you know, there's a national park for forest oak trees. That's for the USS Constitution. Cool. And they got to use some trees. So these huge trees.
Yeah.
300 years old. It's actually.
Yeah. All right, it'd be great to begin the rest of the session. Yeah, like a Jason.
I'm sure. That means there's some.
Yeah, of course.
And.
First time I heard of it. It's my first time.
Oh, really? I've been on that email. That was his first concert.
Really?
This year. They did it.
Yeah. So we're gonna pick up where we left off. We have 3 more presentations, and Kelly Bear is going to be next. And Kelly is a partner in a practice called Bear Valiat. Also is the director of the graduate program and associate professor at the University of Illinois in Chicago School of Architecture. She's taught at SciArc, UCLA, and Woodbury, all places that I know and miss. She's worked in several really sort of extraordinary firms, in my opinion. So I'm going to save the best for last. The first one I don't actually know very well, but Canoe Form, Greg Lynn Form, and the one I think is really an amazing place is what was originally Pew and Scarpa. The VT people might know that because Larry was just in town a few weeks ago. And so she's worked with Brooke Scarpa and done some really great work there. Holds a bachelor's in environmental design from University of Colorado, and a master's degree from UCLA. So we welcome you here. Thank you.
Thank you, Dennis. Thank you, Spencer, for putting us all together in one room. I'm going to be the interloper on this bamboo crew. I'm not a bamboo expert, though there are a couple of images of bamboo in here. It's not, they are mixed with the really bad materials, so I might also be the kind of bad guy, bad gal in this person. Thanks for the introduction and the focus on practice. I'm not going to talk about practice really at all today. I'm going to talk about teaching, which is not something I usually do. Some people do. Okay, so some say we have enough buildings in the world. Using photography to halt the demolition of buildings important to Chicago's cultural heritage, generally during the time of urban regeneration of the 60s and 70s. Richard Nichols said that great architecture. Realize this was holding this. This one? This one?
Yeah.
Okay, sorry. That great architecture has only two natural enemies, water and stupid men. Urging the pressing need for more sustainable practices of building with the social, cultural, and political desires of preservation. Waste not is a pedagogy that poses the question, what if we teach to design and build with what we already have? With the building industry being one of the top contributors to carbon emissions through the manufacturing of construction materials, it's imperative to instill material consciousness into our emerging practitioners. Shifting to a circular economy in the building industry addresses both sustainable aspects of material production, consumption, and reuse, as well as cultural ones. Tapping into waste streams from existing buildings, and perhaps considering deconstruction over demolition, buildings that are slated for removal, especially those which hold historic, social, cultural, or architectural significance, is one place to start. This paper traces a history of materials place within pedagogies, from apprenticeship models to more formalized models of education that emerged in the 16th century. Offered as both an extension of and counter-argument to these established pedagogies, the paper presents recent courses that I've taught that make the case for a more sustainable, generally through building material circularity, inclusive through digital representation and physical model production, using reuse and salvage practices, heterogeneous through hybridization of standard materials and methods with emergent automated construction technologies, and impactful culturally and socially pedagogical model for the architectural education and for the profession at large. Just a few little slides. Stumbling around it. This is maybe considered a primer or an introduction to the lecture. The paper was submitted under the primary topic of pedagogy. It's worth noting that nowhere in the conference organizers call for papers or listing key topics is the term pedagogy mentioned. However, given the Academy's duty to prepare today's architecture students for an unclear planetary future, it seems worth discussing the role of material in architecture pedagogy here and now. So in that spirit, the paper is written in a lecture format and more specifically should be read as lecture notes. The intent is to trace a timeline of material pedagogies found throughout the history of architectural education, present current approaches to material-focused curriculum across design and technology coursework undertaken in recent years, and finally to speculate on the wider implications of this disciplinary work on the profession at large. So to start, past pedagogies. To engage in an architectural discourse as a material practice is to frame the materials we design and construct with the historic, technological, cultural, political, and economic forces that they emerge from, engage with. Material pedagogies have a long history within architecture, dating back to the origins of training through apprenticeship models, long before it emerged as a formalized discipline. In the apprenticeship model, the act of working under the mentorship of a master was intended to put the student in direct contact with both materials and methods. The environment in which these materials and methods were taught were deeply tied to their locations, and their historical precedents were all around. making the construction site the classroom. A shift that follows the movement of the architect, craftsperson in the field, and practitioner in the office that we would see emerge within the profession in later years. In Mastery, Robert Greene posits that mastery is the process of transformation through observation of the rules and procedures that govern success in a particular environment. While Greene uses the term observation, the apprentice was only capable of deep observation through total immersion and active learning. In a material practice, this means exposure to both successes and failures of the unpredictability of the learning environment, i.e. the construction site or the workshop, is never static, nor does it offer the controlled environment of the research lab or classrooms consistent with older models of education. Eventually, the Beaux-Arts would shift from an apprentice model to the classroom model, the effects of which we still see in the curricular structures of most schools of architecture today. While observation was still at the forefront, it took the form of more passive formats such as lectures on tours of buildings, generally trading tools of construction with instruments of representation. While the introduction of a theoretical framework for architecture, as well as the result discussions that stem from both public lectures and studio interactions between the master and the student, helps to formalize architecture as a discipline rather than a vocation, it removed the tacit knowledge of materials in their physical sense. A common exercise in the Beaux-Arts model asked students to draw material with exactitude. In fact, overall success in the program relied on the highest fidelity between the material and its representation, most typically through drawing and replica models of existing buildings or their fragments. Exercises, which almost always took place within the confines of the school, often began with an initial conceptual sketch. The sketch would be handed to a guard at the school, and students were dismissed to develop the design and drawings and models on their own before returning to the school to have their final artifacts compared directly to the initial sketch, thereby extending their learning environment to the domestic realm. Projects found to not exactly match the student's initial conceptual sketch were not given credit for the course. It prevented experimentation, process, and the unexpected results that are often generated in material practices. With the emergence of the Bauhaus, the study of material as material returned, however, the pedagogy did not always necessitate that students work with material, but rather with simulations of material properties. Walter Gropius structured the Bauhaus model around the idea of workshops intended to support research that suggested a return to more transformative processes from initial ideation to final design. Joseph Albers asked beginning architecture students to work with materials in ways that were uncommon to them. Certainly a focus on material, however, one that favored abstraction over literal material properties. Later assignments or exercises, what Albers called matière, French for material, asked students to combine actual materials to test their readability and their ability to appear or be perceived as other materials. This approach to material would eventually lead to the formation of Black Mountain College, among, of course, many other things, where an anecdote about Annie Albers mistaking a note nailed to a painted wood column as marble would exemplify the idea of material ambiguity. And here I'm using a Shawinski photograph of kind of performative aspect of material being kind of embedded into the curriculum of Black Mountain College. Because there is a photo of the Annie Albers painted wood column that exists. At the same time, Gropius' decision to center the curriculum around workshops could be seen as a return to not only the immersion model, but also to the market-driven labor focus of apprenticeship. Gropius' financial model for the Bauhaus relied, in fact, on the production of design objects, designed and fabricated by the students, which is maybe happening over there as well, to partially fund the school. Objects that were not sold were often reduced to raw material and reused either by the same student or by another attempt at product profitability, or by others just for prototyping and research purposes. The following teaching experiments collected under the title Waste Not set out to learn from successes and failures of the earlier pedagogical models outlined above. Framed in both disciplinary terms, material practice, and environmental terms, material circularity, the teaching focus embraces the immersive working with your hands format of the apprenticeship model, the exquisite material representations of the Beaux-Arts, and the transmutability and material simulations of the Bauhaus model. of course, now using digital tools in tandem with analog ones. To engage in architectural discourse today is to frame the materials, as I mentioned before. In Waste Not, the material practice is theorized through a rereading of Semper's Origins of Architecture. In 4 Elements of Architecture, materials, methods, and their elemental roles within a building are siloed into 4 distinct types. We know them well and won't go through them. But Waste Not offers a counterpoint to Semperian notions of material autonomy. Instead, it favors material and method remixes to coax out novel building assemblages and promotes ambiguity and reciprocity between materials and methods, thus making the ancestral pit house perhaps a more suitable precedent for the ensuing work than Semper's HUD. The second tenet of the studio is less disciplinary, but equally as critical. The general ethos towards architectural materials since the Industrial Revolution has been, why bother reusing material when we can just make more? And instead, we frame material at all scales as living, evolving, and transmutable matter, and therefore its methods over time, as well as material properties, are up for reinterpretation. A shift from thinking about buildings as having linear lifespans to cyclical life cycles. Given that material availability and construction phase timelines often do not align, a major downside to circular economies in the construction industry is having enough of any one material at any given time for its reuse, at least consistently. Circling back to the rereading of Semper above, Waste Not addresses this conflict through material reprocessing between 2 or more existing building materials. Centering design methodology around physically reprocessing material encourages students to generate new material and constructs and assemblies with existing materials and methods that are not often put into dialogue with one another. The topic of Waste Not evolved several years of teaching technology seminar electives and design studios, both at UFC and 1 semester as a visiting professor at the University of Illinois in Urbana, a big school as we call it. Where research focused on hybrid construction types between standard building technologies, so wood, masonry, steel, and concrete, and emerging digital and or automated technologies, specifically additive and subtractive methods of construction. The research made clear the need to address pressing issues of construction waste, regardless of the material or the methods applied. This is wood and 3D printed wool being woven through lightweight framing, or the insertion of a mail order 3D printer chassis that uses wood waste from demolition of a portion of a typical suburban house as aggregate. These seminars laid the groundwork for the Waste Not Studio, which is a 3rd-year design studio that commences the core sequence, the design sequence at UIC. And falling under the topical theme of urbanism, the studios have approached the topic globally, the theoretical and environmental implications of building in a metropolis, as well as locally, the social, cultural, and political implications that building anew has on an existing community. I won't get too into that part of the studio. I'm keeping it in the material lane, but we are kind of engaged at all scales. The ensuing case studies illustrate the objectives, processes, outcomes, rewrites from the spring 2024 and spring 2025, what I'm currently teaching, Waste Not cohorts. So this is very fresh stuff. Students were asked to meet 3 primary objectives in the spring of 2024. The first was to acquire knowledge of circular economies and practices of deconstruction in the construction industry. The second, acquire analytical tools and methods for dissecting an existing building. And the third, to develop research into a speculative architectural building that supports material circularity. In the first instantiation of the studio, so last spring, we occupied the middle ground of this graph, which is charting the economic value versus the environmental value of circularity in a building, or in building construction in general. The studio was divided into 3 assignments, dissect, site and salvage, and project. Dissect centered on the idea of unbuilding, which is a term borrowed from Jan in a text about Gordon Maddock Clark's building cuts. For Maddock Clark, unbuilding was an act of anarchy, or as he called it, anarchitecture. So as much a verb for how he used the medium of buildings and the photography of those buildings and more specifically building materials in his work, as it was a statement on building preservation. Using salvage building materials obtained from literally slicing buildings in half, the medium became the message, a critique of capitalism through removal. The process of dissection generally necessitates a body in its entirety to start with, and this initial exercise offered buildings in Chicago slated for demolition as hosts for the process. Students and their faculty unbuilt these buildings along a spectrum of scales, from the recycling of building materials to the reuse of building modules. We're back to the chart that I shared. Primarily a digital modeling and drawing exercise, dissect, catalog existing building materials, elements, and modules, and analyze their viability for reuse. The site and salvage assignment shifted to a primarily model-based exercise, physical model-based, where students were asked to walk a given site in search of building material waste. An infill lot between the historically and architecturally significant Century Building, which is a Holliburg and Roche building from 1915, and the Consumers Building, Jenny, Money, and Jensen from 1913. Two buildings caught between a preservationist battle against city-led demolition, offered a literal scrap bin for students to forage for model-making materials. This waste was brought into the design studio, physically modified by splitting, stacking, intersecting, merging, and finally assembled into abstractions of mass and void strategies. And the models, out of scale for a model, but one-to-one as a building material, were situated and photographed between a scaled model of the Century and Consumer buildings, suggesting both meta ideas about how to fill an infill lot with matter, as well as projections on what that matter might become, were it to be developed simultaneously in the design process. The literal and abstract working in tandem rather than in sequence. As the project entered the building proposal phase of the studio, they determined that the primary material in their dissection of tacked hull, which is concrete, required the highest level of processing in order for its reuse, and thus had the largest negative impact on both economy and environment. To offset this, they proposed reusing the building that formerly occupied the site, a non-landmark commercial building, thus shifting the dissection work from the middle of the graph to two opposing poles, one end being the recycling of building materials and the other being the reuse of an entire building. Given the program of a material bank, the project developed into a repository for the storage and processing of building material waste, as well as a public space for cultural and social knowledge transfer around issues of material reuse and circularity. Gabion walls were used to both store physical material, structurally reinforce the existing building's cast-in-place skeleton, and mediate visual, thermal, and acoustic differences between programs. Also promotes varying spatial and atmospheric zones throughout the building. Grinds, Gabions, and grids, the project's title, found symbiosis between an existing post and beam structure and Gabion infill construction that emerged from a design methodology centered on the simultaneous physicality of building materials as well as their abstraction. While the case study outlined above clearly articulated a tendency towards reuse as both recycling of materials at the particulate scale as well as at the building scale, it was a technical conceptual outlier among the class of over 80 students. Most students, if not all, approached the dissection phase at the scale of a building element, a brick, a building component, a wall, or a building module, a larger assembly of multiple components. And they maintain that level of reuse throughout the rest of the project proposal. While this led to some productive speculations on material reuse, and perhaps even more so on the deconstruction tactics to avoid demolition, or maybe the biggest criticism towards what we're doing now, which is energy-intensive recycling processes, the projects tended towards material collage rather than a symbiosis found in the students who worked with more reuse and overtly reprocessed building material. Coupled with the reuse of an entire existing building, the Grinds, Gabions, and Grid students were afforded more time to focus on successfully developing the technical materials and methods proposed. They also had more opportunities to explore alternative drawing and modeling techniques to represent the material qualities and the phase changes of their building over time, and also to strengthen the narrative and circularity in the project concept. This assessment of the first studio led to a radical rethinking of the starting point for the second instantiation of the wasteland studio this semester. Rather than dissecting entire buildings slated for demo, the first assignment, retitled Extraction, asked students to gain expertise in the full life cycle of one material. Materials that are most typically used in reuse were selected, so they're listed here. And they provided students a kind of ability to shift their mindset from looking more broadly at building precedents, a building as a whole, to looking at material that the building is made of or from. From this starting point, looking at Matt Clark's wall series provided a better starting point or better precedent, more applicable, I would say, than the splitting series. Or returning to the economy over environment graph again, this semester we begin at two ends of the spectrum rather than middle. The extraction exercise asks students to frame a single image, staging a scene that conflates space and time in an effort to graphically convey the entire life cycle of their material. This is earth. From extraction to processing or manufacturing, to construction, to post-occupancy, to deconstruction, followed by an additional zoom-in scene that focuses on the reuse or recycling associated with their material. From there, a material catalog is produced that rendered both standard practices of material reuse and recycling, as well as speculative materials through the combination or processing of or with another material studied by a peer in their studio section. So this is earth getting together with various things like terracotta, glass, bamboo. Told you there'd be bamboo. Digital tools, typically workflows used by gaming and environment designers, were introduced that allow students to design their own physically based rendering, or what we call PBR materials, by adjusting the variables of each of the original materials, so qualities such as color, albedo, roughness, and activity. And this allowed them to experiment with simulations of material attributes of materials that do not yet exist in the world, together using commonly used materials that do currently exist, but on their own. Using rendering software, students applied their digitally produced texture maps back to generic stock material based on the typical forms that they normally come in, so sticks, sheets, blocks, etc. The second assignment was retitled Processing. It asked students to partner with another student based on their speculative digital material catalogs from the previous assignment. They were asked to physically fabricate new material samples from their speculative texture maps that were digitally explored in extraction. We called these material mix-ups. And we use Richard Serra's verb list as a kind of starting point or as a guide for how to operate on or with physical material. The pairing of two materials yields a third new material embedded with the potential for attribute variation that would inevitably come with the salvaging of building materials sourced across several deconstruction sites. For most students, this was also their first time working outside of the traditional modeling, methods, both analog or digital. They were encouraged to explore new tools and techniques to combine their materials to reflect the digital simulations. This led to more urban and suburban and rural, even foraging for material models rather than Amazon orders for work trips. Some of the techniques used to mix their materials included filling and embedding, laminating, baking. So we're getting back to the kind of domestic realm of Bauhaus workshops, curing or bosons, baking, curing, vacuum forming, casting, embedding, foaming, kneading, weaving, and layering, just to name a few. The resultant material samples were 2- and 3-dimensionally scanned and fed back into the digital environment to be deployed in the building project. We're not going to get into now, but I will say it's a 500,000 square foot adaptive reuse project for one of Chicago's original central manufacturing district warehouses. So we're kind of starting at a particular level and deploying at the 500,000 square foot level. Get back to you on how that goes. So just to conclude, projections also as a conclusion, In recent years, material practices such as Hertzog Demeron, Holthrop, and Ensemble Studios, to name a few, have been described as alchemical, as it is the construction of material itself and the processes of its fabrication and assembly that conceptually ground their work as well as translate to the estrangement of their spatial and environmental effects. In our own work, in my practice, Verballier, we've tried to kind of toe this line of waste not, but coming at it from the manufacturing end or manufacturing point of purchase. And so our MoMA PS1 project was actually working in collaboration with the company in Riverside, California, that produces HDPE pipe, which tend to see this all over at least in the Midwest, along the highways, getting ready to be deployed into the ground. We actually worked with them to take all of their material that didn't meet their quality control, which is about 5% of their material. And usually that quality control had to do with the extrusion process not being exactly perfect all the way through. So it was minute differences that for us, for what we needed to use it for, didn't matter. In fact, we actually embraced that variability. But for them, it was not consumer ready or approved. And so really, I think in this project, you can also see that kind of generation of different diameters and different levels of corrugation would have to be deployed because we knew that we couldn't get all of one type of material. And the only times that this would really be revealed would be a few key moments in the cuts into the pipes. And then also working kind of more at the domestic soil, looking at using waste aggregate from conventional light wood framing in the 3D printing of components. This is for an ADU project that I'm still working on. And then more recently, working with, this is a project that we're still in design phase with. It's going to be built in Spain this summer. But we are working with an inherited pile of like 42 sheets of plywood and looking at how we can use plywood as or to rethink kind of wood framing, but through the thinness of the plywood sheets that we've been built. So as waste not matures as a pedagogy, it finds closer ties to the theoretical and technical underpinnings of other coursework that we typically find in a standard architecture curriculum. However, the resultant work diverges from known material histories and theories within the discipline and standard practices within the profession, as material is not taken as a theory, but rather as a point of transmutable departure. In the introduction to Reiser Yamamoto's Atlas of Novel Tectonics, Sanford Pointer likens the invention of gun cotton, a material that stemmed from a famous and unintentional accident, to the work of the firm. For Pointer, Reiser Yamamoto's use of the diagram is, quote, the vessel that holds the inherent features of any material construct. And I embrace this analogy, though from a much more literal standpoint. I encourage students to view the material practice of architecture not as a theory, as pre-described construction types, which generally or often is predetermined by others, clients, budget, occupancy type, nor is an end stage practice of assigning materials to the elements of a building, but rather as the starting point of a design methodology that embraces nonlinear modes of learning and of building. Thank you. Why would I go through?
In a really amazing way. So I'll ask a question then. I have a couple of thoughts moving through my mind. The first is just a comment, which is that in my mind, I started this work with bamboo without thinking a lot about why, other than that I wanted to try a biomaterial with a digital tool. But as I've been working this way, a couple of years ago, I walked in my backyard after a tree fell, and I'm like, I've never worked with a piece of material that I just happened upon in that way. Mm-hmm. And that's something that I think is the product of a suburban upbringing and a consumer culture. And in my mind, reuse and biomaterials, if they're thought about with the right lens, as I've said, beginning with the cement is even a biomaterial, they really are one and the same. And so I wonder, from your perspective, perspective of pedagogy, like, how do we get our students to walk into their backyard, right? And the thing that I think is both powerful but also unknown is at what level of abstraction will it have an impact on their thinking? In other words, a lot of this work, I don't know that it can be translated exactly in a literal way. And some of this kind of alchemy, I think we've never stopped doing as creative maker type designer teachers. But how do we ensure that we don't wind up at 50 never recognizing that we haven't walked into our very own backyard? So that's an open question for some more comments.
Sure. I mean, I think one of the questions that's come up about this is only in its second year of this particular studio, that's come up just in our own like faculty walkthroughs and kind of criticisms is, does it belong in a core studio sequence, right? Because I think for some it feels a bit niche. But I would say it certainly does. I try to kind of make the case that it also does the kind of knitting or the weaving with the other parts of the curriculum, maybe that other studios don't do as directly, don't confront us directly. But I think to the question of, well, I mean, also it then requires all 80 to 100 students, however many in that cohort, to come across this and be exposed to the idea that like there's a lot of stuff out there. You know, you can probably source from what you can find, both from a kind of backyard standpoint and from a reconstruction of an entire building, or from kind of like, you know, urban foraging and things like that. So I think it puts it into their mind, but I think it has to be written into the assignment, right? Like those students, even in last year when we said, okay, you're making massing models, like their immediate thought was like, well, I need to order these materials, you know, and we didn't let them, like I've been more lenient this year, but there's epoxy in here. It's probably part of what they have to order, you know, been more lenient with this more processed version of the studio, but in that one, I was like, you have to carry it.
Yeah.
I mean, we like overloaded the structure of our 60-year-old Netch building up there in Chicago. So it was a really kind of strange way for that to work, you know, not having the precision of with sticks. And
I think that also outside of the highly important sort of environmental responsibility for greenhouse gas, global warming, et cetera, just in a very simple sense of how we learn to be creative. I think that as computation has taken such a foothold, as the modes of representation are so super real, they're also completely synthetic, right? And I think that just having students get dirty again is really important. And I think, you know, Black Mountain College, Virginia Tech, the Ferraris, the Ohm School, like the claim when I got there 8 years ago, and I guess we're being recorded, so it's public, was that we were actually engaged in that same work. I think the lens of which you shared today, I kind of understand that work more than what I did before, but I also continue to disagree that we were actually fully engaged in that. I think we still had the workshops, there's still sort of the geometry of how we were engaging with them, but the real kind of hands-on quality of one-to-one making to explore what the built environment might be, I think had largely been forgotten, or the fidelity had gotten to be so low that there was little left. And so that's one thing I've been trying to think about, how do we re-engage in this, you know, digital future, is how, whether it's for the sake of the environment or just for simply teaching designers to be well-rounded in terms of the modes of representation or of design, how might this interact? What I really like about what you shared is that you don't really have to be engaged in sustainable thinking to understand the semantic power and beauty that's possible from this kind of alchemy.
Right. Yeah, you can kind of sneak it in the back door.
Right. Well, it's ironic that it comes in the front door, but after doing it 3 times, people can just look at it and be like, holy shit, is that cool, right? And that, some of that happens even more easily as you loosen up the kind of, as you said, you let the resin sneak in, right? I mean, in other words, it doesn't mean that it's not a guilty pleasure for everybody, the faculty as well as the student making it. But there is an awareness of that responsibility that wouldn't be there if you hadn't, if it was only coming in the back door then. Right.
Yeah.
So are there other questions? Hopefully we're commenting, like, I'm gonna ask Mark.
You already have your hand up too, so I can't wait. All right, well, I wanted to hear what you're gonna say. It's Philip. I have kudos, a reminder to myself and a speculation about some gaps in questions. First, I think that you're teaching some of the most important material in the world today. I was completely knocked out by your presentation. It's just so transformative and clear and inspiring. Please keep going. This is profoundly important and clear and effective work. It's a beautiful presentation. Remind myself is that I have the notion that Buckminster Fuller in writing Synergetics also said to the world, "Madam, how much does your building weigh?" And that was kind of an aestheticized thing, and the working drawings came out with a little speck on the right-hand corner that said weight as well. And but I think that you're really demonstrating some rubrics and syntax and methods to fill in those tantalizing gaps very, very directly. Again, that folds back to kudos, but I'm just really thrilled by the kind of enabling language that you're setting out in this work. In terms of gaps, I find myself wondering, how on earth do you grade and rate and critique and evaluate and foster development? And I say that because perhaps an elephant in the room is the question of elegance and fitness and effectiveness and cost and speed, like some of the other elephants that were in the earlier presentations, which make you perfect to be in this. That is to say, how is non-standard somehow valid as opposed to just aestheticized and new and good for peacetime but not good for war? You know, like when the chips are down, does this practice matter, and can we believe in it, or is it another postmodernism excess that at the end of the day won't be able to stand up in the face of just relentless, immediate, brittle results, concentrated, powerful results? So my questions are about a rubric of slowness as opposed to speed, a rubric of diversity as opposed to unification. How do you work with those kind of spectrums? A quick comment before I ask you to respond is that when you showed the ateliers, which was a beautiful part of your presentation, then I saw kind of lurking in the Bauhaus the sense of a pyramid of values where, yes, we integrate, but then we concentrate and then we make them master. And the master leads the workshop. And that kind of hierarchy is not replaced by the Bauhaus, it's enabled by the Bauhaus. So I'm wondering about your models of agency and a reward structure then that deals with ideas that perhaps going slow is actually better and more effective than going fast, for example. And making a mongrel might in some cases be actually exactly what you want, rather than making that intacte Kunstwerk.
Yeah, there's a lot of questions in that question.
I'm gonna actually ask that you hold those, and then we have a small kind of closing conversation and engage those questions.
Okay, you're gonna give me a chance to write them all down. Then I will respond.
Yeah,
sure.
that was really great. Yeah, feedback.
Cheers.
Yeah.
So let's one more round of applause, and then we'll. So next we'll have Letizia's presentation, and she's a visiting scholar at Virginia Tech, working on her PhD at the University of Bologna in structural mechanics. However, she's actually an architect, which is an unusual but amazing combination. She's on the RILEM committee, and she's going to share her work with Stardomes. And I'm excited to have just another translator talking with us with a couple of different cultural perceptions to share. So thank you. Oh, I'm sorry. Right.
Anyway, thank you so much, Jonas, for the presentation. Thank you, Spencer, for inviting me. I appreciate it.
Who knows the short key for?
No, control.
You got it.
Yeah, but it's sharing.
Oh.
Drag it. Let me try to drag it before opening.
No, it's losing from over. I try Windows speak.
Okay.
I'll try it.
Today I'll be presenting bamboo stardom, and I'll be analyzing mechanical property as well as its design. And I will talk also about the environmental benefits that bamboo has. So the contents will be from some generical aspects about my research to more specific aspect about it. So basically, the stardom is a geodesic-like structure. That means that it's not really a geodesic one, but it can look like a geodesic one. And we will also see that it will behave like a geodesic in some kind of points. So it's peculiar because it's constructed with 17 elements with all the same length. So we will see that the bamboo rope will be all the same length. And in my case, I've analyzed stardom structure using Italian bamboo. So basically, why using bamboo? Bamboo for the research is considered as a very sustainable material in terms of its environmental impact. In fact, compared to other material like wood, it requires less resources in terms of time, space utilized, and nutrients that you have to give to the soil to harvest in. And for us in Europe, it's a big concern to think about the land use that we need, and as well as the maintenance. So bamboo for constructions, as Jonas said, I'm from structural mechanics, so I'm studying the specific behavior in terms of mechanical properties of bamboo. And it's very fascinating because if it's correctly applied to the structure, it can behave somehow like steel, but if it's not correctly applied, it will not behave very, very good. So the importance of bamboo is not to use it or not to use it, is how to use it. For the sorghum, the material preparation takes a huge part of the whole process. In fact, also the cane selection is crucial. It will be an active bending structure, so you're not supposed to use a cane with a huge wall thickness, which would fit perfectly for other solutions. In this case, medium or a small thickness for the cane wall will be perfect. So I would say less than 1 centimeter, not 1 millimeter. And also the cane diameters, because we are not using the whole cane for the structure, we are going to be using splits from the cane. So from 8 to 12 centimeters, we can obtain 5 or 6 splits from a cane. And we see that this structure doesn't require a lot of material. 3 canes will be enough for the whole structure. So it's a very good point for me in terms of material using. Basically, for the split themselves, we'll be needing 2 different types of splits. They are all the same length, but the division between the drills that will be the points for the connections is different. So we will be needing 10 splits divided in 3 parts and 7 splits divided in 5 parts. During the material preparation, it will be crucial to clean the cane in order to have strips that have more or less the same thickness in all the parts. And if you know bamboo, you will probably know that it has some nodes and discontinuity, but we can clean the nodes and have more continuous splits. And pre-drilling. In this research, I used bolts and screws as connections, but you can also use other types of connection. I will explain later why I use bolts and screws. As I also said before, the stardom is an active bending structure, which means that when it's finished, it is in its own equilibrium. But during the construction, you will have to bend the bows and secure them between each other and between the base as well. For this reason, there is a specific item to follow during the construction. So you will have to construct the base at first. Then I will show you this slide. After the base, you will construct the upper woven. And from this picture, we can clearly see why it is called star dome, because basically every woven layer looks like a star. So all of them are secured between themselves and the base and between other layers. So the connections. It is important in this type of frame to use design for disassembly connections, because it's an iterative process. So you have to connect and disconnect during the process. For this reason, I pre-drilled the cane and I use bolts and screws, but you can also use rope to tie up the connections. In my opinion, using these connections helps to prevent the slide in between the canes and have a good joint. I mean, for me, it's the best connection, even if drilling the cane could not sound very good. So for the structural analysis, I used a software called SAP 2000, not 200. So sorry. And I had to simplify the boats because the software doesn't read any kind of curve. So based on the connections, I decided to divide the curves into 15 segment polylines, which was the best option to fit both the type A and type B both. So before going to the result, I will ask you a question. I said that sometimes the geodesic structures behave unpredictably. So do you have any guess of which one would be the most reflected part of the frame? You can also say, let's raise our hands. Who thinks that all will deflect the same if a vertical force is applied to the whole frame? Everyone thinks that they will deflect the same? No? Any guess for the upper woven? 2? Okay, 3? Okay. Middle woven? 1, 2, 3, middle woven. What about lower woven? Okay, so basically also from your response, we can see that no one has a yes. So the lower woven is the one that affects the most. And this is the form structure and the underform structure. Yeah, as I said before, I use a vertical distributed force, and this is a very basic analysis. It just says which is the element that deflects the most. So I secure the frame with pin connection, which means that rotation are allowed while translation are not. So I love just 3 freedom degrees. And yeah, we can see that the lower layer is the most deflected one. So I have some conclusion as well, some follows up. Like, as I said before, the Sardom used less resources compared to other structures, and it's very strong. So I really like the fact that he used less, is a low resources structure. And I really love that it's modular. So I never mentioned anything about a specific length. I also mentioned some parameters in order to have a good construction process, but you can select 17 different elements and you can construct a Sardom very easily. So it's very useful if you have to do an emergency shelter, for example. And as well, it's designed for disassembly, which means that in case a piece breaks during the construction, you can very easily replace it. Or if you just want to move it from a place to another, you can just disassemble it and move all the pieces and construct it again. Some follows up will be that as a PhD student in structural mechanics, I would like to investigate more on his structural behavior, because here I just presented a very simple analysis of which is the element that undergoes the more deflection. But I like to see how would it behave if I use different thickness or different width elements, as well as using different materials maybe, or different species of bamboo. And also, in my opinion, a parameter analysis for each geometry will be helpful, because I said that we are using all the same length elements. So also analyzing what other type of structure we can make using the same length elements will be interesting for me. So yeah, thank you everyone for your attention.
Are there some questions?
Question about the bamboo thickness. Is that a function of the species of the bamboo, or is it like a matter of when you harvest the bamboo? Or do all like bamboos just have different thicknesses and you have to choose the right ones?
Okay, all the species has a different thickness, and for us in Italy, we usually have very thin bamboo. So
also the place that you grow bamboo can affect its thickness as well as its strength. So yeah, it depends on where you construct and what species. There are also some type of bamboo which doesn't present any oak inside it. He's working also with this.
So just to add to that, so the age of the bamboo rhizome, so bamboo is rhizomatic. So if the rhizome is mature, you start getting bamboo that shoots at the same diameter. But then along the length, most species, even if they're semi-hollow or mainly hollow species, they tend to be thicker, even solid at the bottom. In the middle, they're thinner, and then as they get to the top, they get more solid again. So when you're making things out of splits, you can, if you want to use the whole split without subtracting any more material other than just splitting, you would, from most species, you can find a part that might work at a particular scale. So the biggest timber species that's commonly known is Dendrocalamus asper. You might make star domes that are 3 or 4 times the size of the ones we were talking about at a minimum, because where that material bends well, where it has the right aspect ratio, would lend itself to really long parts that might be 50, even 100 feet long. So that will lead me to a question, which is, do you think that this has, outside of temporary structures, can you imagine in the space of architecture, because you're a translator, how active bending structures could or should be applied to the scale of more permanent building and building to occupy more than 2 or 3 people?
In my opinion, if you add some layers, like if you use this frame as a structural part and you add some layers, like maybe also bio-based layers, for example, I would say adobe bricks, or also I saw a research that they were using broken parachutes to cover it. So in my opinion, using something that could be a byproduct or a waste from another element and construct different layers like we do for homes could be good for things like that. I mean, it could be a small shelter, but it can last long. Because as we I think all we know that if you put bamboo in the outside and you live there, it will rot very easily. So yeah, if you add some layers, you will fit for long-term construction.
Thank you.
We
will close the paper talk for this session with Wiley's presentation. I gotta find my notes again. So Wiley is an assistant professor at Washington University in St. Louis and a founding partner of Leopold Brown. Thank you. And they practice in Munich and Stuttgart, and he's a fellow of the Institute of Lightweight Structures, also in Stuttgart, and his MArch is from the GSD, and he has a bachelor's in anthropology. And very much kindred spirits. The director of this school actually has been trying to bring it together, so very happy to have him here, and I'm very happy to meet him.
Yeah, I'll see them. So will I be able to see the next slide on here? This first. Okay, good. All right. Hello. Well, so it's great that we've had. Yep. Oh, Mike. I speak pretty loud. Is this better?
More for the audience.
Oh, okay. Oh, just so
Supposedly, yeah.
Okay, so I'll try not to close people's ears out. So yeah, we had a quick introduction. It's great. And thank you, Jonas, and thank you, Spencer, for having me here. And it's great that we've had a presentation of all of the main benefits of bamboo, because I'm going to give a bit more of an experiential journey of how I became what I call bamboozled and from a skeptical point of view, and then getting more into it. As Jonas mentioned, I am a practicing architect. I have an office that's based in Germany and the US. This is a couple of years ago, but you see some of my employees there, founding partner. My partner is Andreas Leupold, Christian Goldbach. And we designed everything from stadiums to schools to community centers, housing, museums. And the fundamental of our design is environmental sustainability, social responsibility, but we're realists. And we recognize that in order for things to actually be built, it needs to be financially feasible as well. We really try to make things possible. So we build a lot in that sense. At the same time, I'm more recently a professor at Washington University in St. Louis. And the kind of way I teach is through making and breaking and operational models, I call it. So students will make this particular tensegrity thing, but it's through experiences. So students ask, "This is going to work?" And I say, "I don't know, let's make it." I don't really like teaching, but I like creating learning experiences. So I learn with the students. And so that's kind of the journey I'm going to get across here is, why bamboo? And so a number of years ago, when I first started teaching, 2019, I was kind of looking around like, what should I do? I'm a professor now, I'm supposed to do some research on something. And something that's kind of always bugged me is that, so this is what home construction in the US looked like in the 1800s. Basically a bunch of people, mostly men, walking around with their, tool belts, hammering some sticks that they got somewhere nearby and build a house. And here's how we do home construction today. It's basically a bunch of guys in tool belts, mostly men in tool belts, hammering sticks together. And this is actually ironic because this is a building I designed and got an innovation award for its energy positive and affordable housing. And what's interesting is I initially proposed it to be modular, made in Boston, made in New Hampshire, and then transported and put up really quickly. But the city of Boston was basically donating the land, and they said, "Oh no, it has to be all local labor." And it turns out what local labor means is the contractor has an office in Boston, and all their employees live in New Hampshire and drive down every day. So it's what you start to realize is that innovation is not a technical problem; it's a changing the minds of people problem. And so one of the things that I look at is like, we don't design our cars like we did 100 years ago, right? Like this would be ridiculous. And we absolutely don't design our phones like we did 100 years ago. So why do we still build our homes, which are like our biggest individual investment, the same way we've done for like 200 years? And so it's a question. It's like, oh, well, don't fix what's not broken. Well, the problem is these are a little bit old statistics, but since 2008, the financial crisis, cost of housing has gone up and up and up, cost of building, and we're not building enough houses. So it's like continues to go up. So it's like it is a broken problem. And during COVID, we noticed that timber prices went through the roof. If you go to like, a box store and buy regular 2x4s, they like tripled, sometimes 5 times the amount. Although I was building projects with like big, huge like timber framing from local mills that were from stores out in New Hampshire and milled in Massachusetts, and the prices did not change. So I was like, wait, what's going on here? There's something funny happening. What you start to realize is that most of our standardized lumber is not coming from the US. So it was a global problem. We're actually shipping stuff in from Canada, a lot from South America, Central America, from all over. So I was thinking like, okay, well, if we wanted to like reboost the American system, we'd have to plant some trees, which might take 25 years. It's not a really, good solution to this. So what's an alternative? So I started, looking and ran into bamboo. And it was like, oh, we're talking about like a 5 to 7 year turnaround, not a 25-year turnaround. Let's investigate this. And my partner at the time was very happy to fly with me to Costa Rica to do some investigation. And so I took some students down there and went to this permaculture farm down on the Osa Peninsula and started looking at like how do you deal with bamboo? And so we walked out and, went about 150 feet into the jungle, and with a sawzall, we were able to harvest 60, 70-foot poles. We carried it out by hand, and on the way back, we grabbed a papaya and had lunch too. And then you could treat it very simply with some saltwater solution and about $800 worth of plumbing, stack and dry it, and now you have some usable bamboo. No heavy equipment, no big tractors, very simple tools. And then you can do things as we just saw. You can split it pretty simply, make long strips that are very flexible. We actually tied that in a knot, pulled it tight and untied it, and then the bamboo barely even noticed. And so we designed a quick little structure, also pseudo geodesic, and laid out some strips. We used a lot of cable ties. We didn't use bolts in this particular one. Popped it up. We did lash it with field techniques based on fishing line, and made a little dome that we then, this was the model, there's the dome. This is my student from WashU. Covered it, we put a little thin shell concrete over it and made a little happy structure with basically just using field methods. And everything comes from less than about 10 kilometers away from that location. Here's that project. So I was like, this is interesting. This idea of like, you can grow your materials, you can grow your lunch all right nearby where you're growing, where you're working. And why can't we carry that idea back to the United States? I mean, we could also, rather than having, floral gardens that are pretty, we could actually grow our food and material. And so I worked on a project actually in St. Louis. There's a lot of a good half of St. Louis is a divested area, very kind of impoverished folks. And there was a project with WashU to build a park for them. So I created a design build studio. Students came up with a design. We kind of developed it and presented it to the community. They were really excited about it. And then we made more development in the model and created a workshop where the community was invited. And we all, with students from many different schools, put together this little pavilion in St. Louis. And what was really interesting is one of the residents had this amazing comment and said like, wow, this is so amazing, this material. It's not like the big pillar you see in the back, which is kind of the idea of like single or multiple, if you build with pillars, identical pillars holding up the building. This is a construction where you have many individual pieces that every piece is different. And together they create a communal shell that's stronger than the sum of any individual part. And I was like, wow, that's a really amazing way. The meaning of this material actually has some impact, particularly in a community that's been treated very poorly for decades. And so this led me to think, okay, well, let me investigate this a little farther. This material clearly has some interesting things. So I flew out to Southeast Asia and started to explore these amazing projects by Ibuku architects. They're probably well known. If you have Apple TV, you've probably seen some of these projects, Laura Hardy, and started looking at these amazing forms and very incredible individualized structures that are really remarkable, bridges, 3-story buildings. It's like this thing has capacity and possibility that's real. But at the same time, every time I presented this to somebody in a temperate climate, whether it's Europe or the US, they're like, yeah, but we can't live like that. We have cold weather. And so, I knew, and well, my neighbor planted bamboo, and it's a horrible thing in my yard. Bamboo like that doesn't grow here. And it's, you start thinking like, okay, clearly there's still a translation to the aesthetic of what it is. Of course, you wouldn't necessarily build tropical designs in the temperate climate, but that shift of thinking was difficult. But so what was almost equally amazing in Southeast Asia is the use of bamboo as a utility material. So here it's used as concrete formwork. It's used as a basic ladder, very portable ladder. Or this was not my experience, but this is another photo of scaffolding, multi-story scaffolding. So it's clearly cheap. It's clearly available. You can use. It's strong. It's used for as a utility. If it's nearby, and then of course warehouses. So I started thinking, if we're trying to bring it to a temperate climate, because I think there is a great possibility here, it's not going to be through a design argument to say this is a great new way of thinking, but how could we bring it in scale in the US, right? How could we actually bring it here in a way that's actually maybe through the back door? We were talking about back doors. So what do we build a lot of in the US? Any thoughts on that? We build a lot of these. They're not pretty. It's not like the architect's like, yes, I want to get an Amazon distribution center. But as of 2018, it's the most common type of commercial building that we've been building. And as of 2024, a couple months ago, $9 billion worth of warehouses are under construction, 25% for Amazon. So the thought is, could bamboo actually replace these boring structural systems that nobody cares what it looks like? It's just like the cheapest, most convenient thing. But, and it's not like a super strong steel structure, but we just use steel because that's what's available, and that's what's cheap, and that's what we know. So could we do that in bamboo? Why not? And so I flew back down to Costa Rica and met with a friend of mine at the Department of Forest Engineering in the Costa Rica Institute of Technology, this Professor Roger Moya. And he's been doing research on over 4,000 wood species, mostly tropical. And he kind of laughed at me when I suggested bamboo, even though within 50 feet of his building that I just showed you, it's like a bamboo grove of all the timber species. He was like, bamboo is not really a serious material. We're into timber, and we're doing some interesting work on pineapple, but bamboo. And I was like, what if I bring the funding? He's like, okay, fine. So, you know, he's been doing all this experimentation. And so we took some bamboo slices from a nearby grove, chopped it up into little tests. And, you know, he's like, okay, let's run a quick test on it. Let's see if this actually is serious material. So, of course, this is in grams. That's about a quarter pound, that little piece of guadua angustifolia. And then we ran it in a you know, compression test. And this is what came out. That piece of quarter pound, it's like quarter pounder, right? We're at Burger King now, carried 9,800 kilograms before it broke. That's like 22,000 pounds. That's like 10 cars. Am I running out of time?
No, it was green.
No, it was dried. It was dried and cured and treated. Yep. And and that was just that piece. I mean, there's many more experiments. So we kind of whipped up a quick few calculations and compared a piece of standardized guadua to a hot rolled steel L profile that those silly trusses are made out of. And we saw, like, as far as compression goes, it's actually better. Tensile goes, okay, it's a you know, quarter the factor, but we're not trying to make, you know, amazing bridges across the span of things. We're making lightweight small structures. So we whipped up a little quick design of kind of what I would call a very, you know, not really thoughtful. We were just kind of being a bit dumb about it. Like, let's just be straightforward. Let's just go to the basics, make it really simple. Ordered a bunch of bamboo poles. Well, got some of my bamboo builder friends from nearby who came and like, okay, yeah, we can put that together. And with some students, in just a matter of hours, built a handful of these structures with very simple joints, as I said, put it together and built a little mock-up, and then did, of course, a little quick field test. And it was interesting because the bamboo builders were actually skeptical of this. They were like, there's no way that thing's going to hold anything. This is not how you build with bamboo. And me and my students climbed up there, and then finally they did, but there was still this one that was like, I'm not sure. But so again, we were trying to be really, you know, dumb about the joints. So we just did threaded rod on one. We did another one that was lashing with with basically fishing line. It's a coated nylon. And then we did do one with stainless steel straps. And we took it to the other engineering department. They mostly do concrete testing here, so it's not ideal for a timber base or bamboo structure, but that was the facilities we had. And we did some testing on those trusses. Let me see if I can get this video. Okay, so it's running, and you see it's compressing, it's compressing, it's compressing. And it's actually failing at certain points. It's hard to tell when here. It's failing where it suddenly stops taking load, and then it starts actually taking load, and you see it pop back. So it stopped, it got to a point where it stopped taking load, and then started taking load again. Stop taking load. The ambushes. And did my mouse here? You can see the blue line. So the blue line for the nylon and for the standard, it kind of, you know, it did a couple times and it just failed. But with the steel straps, it would take load, it would fail. It would take load, it would fail. It actually would take more load as it went up, which was really interesting. And what we realized, and what the concrete guys said, is actually for life safety, that's fantastic. Because usually what they have the problem with concrete is as soon as the concrete shows a crack, like 3 pounds later, the whole thing explodes. Because concrete's very, what's called, you know, there's ductile and there's fragile materials. It's getting a little structural engineering. But bamboo, particularly with this particular joinery, acted like a ductile material. So it would start to fail and you would recognize it. And you would have about, you know, 3.5 hours to walk slowly out of the building and get your coffee while you're on your way. So there's actually, as far as life safety, that's in a lot of ways more important than some of the other aspects. And so what we saw is it was actually the steel straps were stopping the splitting. Because I think, as Letizia mentioned, if you do joints wrong in bamboo, you do get splitting because it has a, you know, there's a different way of thinking how joints work. But if you hold it together, it will actually support it. I mean, the nodes do that too, but so having some sort of banding can be a way to bend it. And actually, it's pretty easy. I mean, that's not like a hard thing to do. So even with just simple joints that are kind of sloppily made by students who've never built anything in their life, you could actually make trusses that will hold up. So what it showed me is that there is a potential for this. They do appear to have the characteristics needed to be standardized truss systems, but we need to develop those joints a little bit more. And you know, we need to do more testing and probably actually work with the structural engineer to stabilize these things. But as I said, you know, I'm following a method of experimentation to discover things, and now it's getting to a point where I want to like really get serious about it. And I think we're pretty close to. I've done a couple other experiments since then, and I think we're pretty close to a method that I think could work. And it's a matter of then, again, changing the minds of people to say, like, this is possible. And so that's actually more of an issue than, I think, the technical solution. So, I started the question, why bamboo? And really, the question, when you think about all the things we've heard about, is, carbon sequestration. It produces the oxygen it produces. It can, it's good for water retention. It has all these ecological benefits. And it's light and easy to use. You don't need huge, heavy equipment. It's a small business dream because with like 3 people, you can harvest it with just a few things. So the question really is, why not bamboo? Thank you very much.
And I apologize if I missed this, but I guess, have you figured out exactly, what the length of the maximum span that you can get out of these trusses is?
I mean, that's something, it's something that can always be developed. So I don't think there is a maximum yet. I'm sure that's something we'll run into, but those were 10 meters long or 33 or 35 feet long.
Yeah, I find this presentation very interesting, because, I heard that, Amazon basically bought out all the steel trusses and there was just a shortage of material. So it'd just be a very interesting replacement to use bamboo instead of the steel trusses, and if other people can then use those materials where they see fit. But I honestly see this as a great fit, as a replacement.
Yes.
I totally get the lashing working better than the full joint, right? But the lashing allows for a little bit of movement, right? Is that it? And so the bamboo can do what it does best, which was in your test, it flexes down. It's not really failing as much as, flexing and then popping back up, which is part of its behavior as, as a whole, as this material works. So then the lashing allows that to occur. Do you think then that, maybe we need a new set of metrics for what stability needs, right? Because we usually test stability based on the stability of the joint. In other words, the tolerance of which the joint won't move, right? But in this case, there's a different kind of tolerance being suggested. Is that correct?
Yes, and so I think that's a general issue with bamboo. I mean, I think often, and again, I have a degree in anthropology, so I've looked at technologies throughout history. And a lot of times when there's a new technology, we tend to treat the new technology like we would the previous technology before we actually shift over and think about, when you think about the creation of ceramics versus woven baskets and things like that. And so I think we're still thinking of bamboo as a timber, and it's not a timber. And so there is that shifting of thinking and shifting of how we're doing it. We know that concrete works very different than wood, works very different than steel, and we can manage that. But now with bamboo, it's not any of those. It actually has properties of steel, as we mentioned. It has properties that are very similar to wood. In fact, I view it as almost a rope that can carry compression because it has that low shear like rope. Like rope will take, you can carry huge amounts of weight, but if I come with a knife and just touch it when it's boom, it explodes. So particularly from my background in lightweight structures in the Friono Institute, like tensile structures, I find bamboo actually more like that, just that can handle compression. And so it is that shift of mentality of how we use it and how we think about the joinery and really focusing on that as opposed to continually using it like another material. So I think you actually hit it right on the head of that shift of thinking. Yes.
I thought this was an incredibly important and valuable study. I am curious about whether you worked with the periodicity of the material because it seemed like the truss form that you're using was asking the bamboo to act like the relatively amorphous rolled steel units, which is valuable to set up everything. But then the joints in bamboo are of course formed by their own nature. Did you engage them?
No, I mean that's also exactly the case. Like again, I was being very dumb with this one intentionally. And I say dumb, but very simplistic. It was trying to create that direct translation of how we visualize steel usage and turn it into bamboo to just see where that stands as a baseline that we can move from. But that is what we learned as well. I mean, and as you saw in some of the previous presentations, the node length becomes really the metric of the material. And to be able to modify things very quickly and whether it's a machine doing it or just a well-trained craftsperson doing it, understanding that really following the material itself and letting each piece be individualized is very likely the optimal way to use it, and not just be systematized and have all your measurements the same.
The term spectrum has come up a couple times already today and will continue to. And what I would just like to add is, what I think is an interesting thing to think about is let's call the spectrum of the way to develop innovation and material and construction and architecture. There may be these two paradigms. One is like completely incremental, and that's the one with great intention explored. And the other one is with like a kind of a clean slate, right? A new way of working. And I think that we really do have to be doing both.
Yes.
And I think that it takes these full-scale physical experiments just to kind of place oneself both in technical sense through the validation of testing, but also in an intuitive sense. Like
Yes.
what is like theoretically possible, what is actually possible, are not always the same thing. And I think we have to use what we know already at times in order to place ourselves as designers and inventors on that spectrum.
Yeah, exactly. Hitting it from both ends.
Is there any more questions?
I want to go back to Dora's question comment, because I think there's something really rich there that I think needs to be explored. We have mass dampeners in towers to minimize the movement because of social, because of
comfort.
Well, comfort,
Yeah.
and then also just like social perception or the perception of something that's solid or stable, right? And I think I feel like we have to get past that. I mean, we see Philip's work, which is all dynamic, and it is about embracing the dynamism of spaces. And I think bamboo kind of plays into that, where it's meant to be swaying in the wind, right? And for it to be dynamic allows it to have strength that normally a static material doesn't allow for. And so I think this might take a really long time to be able to get to the place where people expect their buildings to be dynamic in fundamental ways. But I think that we need to get there. When you think about something that's rigid, like you said, it shatters, right? But then when you think of something that's not rigid, flexible, then it can respond and be and flux back or recoil essentially.
Yeah.
And I think that we have to get there.
Well, I mean, this is actually a project that I'm working on in Nicaragua right now. It's an open air classroom, and we had a bit of like at the opening, people dancing, and the floor flexes, and people actually initially were like, "Whoa!" and then they were actually like, it became part of the fun. They're like, "Wow, it's responsive. It's like a trampoline," and so and of course it was perfectly safe. But that I think there is we can learn, but it is that shift of thinking that is much harder to do than to come up with technical solutions, I find, in my experience. Yes.
Your background in anthropology is interesting to me. I guess I'm wondering, like, I was just doing some Googling. There are native bamboo forests in the US.
Absolutely, yes.
Why, like, are there examples of indigenous or vernacular bamboo architecture in the US? And like, what is, if so, or if there's not, why not? And like, what is the resistance, or why can't we do it?
Well, now I'm way outside of my area, but I will say, I mean, I teach environmental systems as well, and one of my slides about passive house is, if you want to look at passive house, look at pre-Columbian architecture. That you build very differently in New England than you do in Arizona, or the Anasazi and the Wampanoag built very differently based off their thermal conditions. And so actually looking backwards or looking at those indigenous traditions is a wonderful way of actually innovating. Sounds a little crazy at first, but so I don't know specifically if the U.S. definitely has native bamboo, but I think the reason that we as Europeans, we arrived and said, "Oh, all these are silly primitive huts. We know how to build properly," and they were timber and plenty of it at the time. So they translated there. So that's why we build pretty much the same in New England and Arizona and Denver and every location that you can imagine, and just make up the difference with mechanical systems. So it's still a colonial way of thinking, quite honestly. And so we don't have the diversity when you look at the mud huts or mud homes in the Southwest versus the birch bark up in Connecticut. where there was great diversity in the ways of thinking based off the resources and their climates. Because we have this, the whole country is basically this uniform idea that's basically a Mediterranean, well, it's either Mediterranean or from, England. It's the same typology.
I'm sorry, can I add something based on the European context? Because in Europe, we used to use bamboo instead of steel because it was less expensive, but this was before the city's development. So then when we had a boom for a very huge increase in the house demanding that buildings became higher and more engineerized, I would say. Also standards became something mandatory for build something. And for this reason, people stopped using this kind of materials and they opt for more standardized materials like concrete, wood, and steel. And for this reason, people just stopped using this kind of materials. But if you go to Italy, for example, and you see in the country some old homes, you can still see in the middle of the floor the use of canes. And they are still good because they were protected, so they didn't rot. So I think it's something because of the engineering and the development of new and bigger buildings that make us stop using this kind of materials.
Well, I mean, in Europe, my experience also is even wood homes are considered kind of cheap and if there's a new resurgence of wood, I mean, in Germany, I'm speaking more specifically, but there was this like, no, masonry buildings are real homes. And even the shift to, we've been trying to get developers to build wood homes for years, and only in the last like 3 or 4 years are they actually going for it. We'd always do like a masonry version and a soft mass timber version. And so even wood in Germany has had struggled to come back. The roof would be made out of timbers, but like, walls and floors and things. So bamboo, I think you're right. I think there's the loss of some of these traditions and ways of thinking. And it's now, there is a resurgence, but it's still in the corners and edges. And I think that's my kind of concern, is that we see a few examples, like Simone Valles did, in the Hanover Expo, a pretty cool bamboo building in Hamburg or Hanover, excuse me. And there's a few examples of a few projects, even my St. Louis project, it's all these like one-offs, but it hasn't taken hold and noticed the real value of this material. And it's funny when people say, yeah, but bamboo doesn't grow here. And I'm like, well, your phone didn't grow here either. And petroleum didn't grow here either, but there's a gas station every corner. So we are moving materials around. There's some problems with moving bamboo poles or even bamboo splits, but to say we can't move things around, at least kickstart things, is ridiculous. And a lot of these species, or some of these species, can grow within the continental U.S. potentially. I mean, there needs to be research on that. But some of the less or the more temperate species, particularly, I had my first. It's Philostachys anutus called moso, could very likely grow in about half.
One of the big challenges yet to be answered, and I think the warehouse work will point at this, is this fire, right? So in other words, steel has its problems with fire too, but bamboo is not like steel or wood this way. And we really don't yet have very few experts researching it, and there's very little knowledge of how you would mitigate fire in a different way, or how long it will take for a bamboo structure to fail, right?
Well, I mean, in Germany, and that's where the other half of my work is. It is classified. There's the research. It's classified as what's called a B2 material, which means a flame retardant but burnable material. This is how Simone Valles did that pavilion. So he did get it classified as a. So the silica layer on the outside does actually resist fire. Now it doesn't quite work like timber, but so there is a resistance. And this is the thing about warehouses, is actually most warehouses aren't even protected steel. Exactly. So that's why it's like, let's start and let's bring this as a material into the quiver of a material palette and start playing with it. Just like when you go to Home Depot or any box store, and there's all these third-party products that are, timber related. If we start using it and it becomes like a regularized material, they'll start being third-party products. One of the problems is coatings. Is actually, we use a lot of like wood-based coatings, but the chemistry of how it attaches to the bamboo is a problem because it has a different chemistry. And so if we start having chemical engineers making proper coatings, and we have, you know, Simpson ties, making Simpson ties for it, and all these third-party things because it becomes a regularized material. And that's the question. Like, how can we make this normalized and be another option? Particularly in light of the carbon footprint of concrete, steel, and glass. Like, it is there and it's really accessible, and like small farmers can grow it. And so there you go.
All right, so the first thing I would say is that I don't have slides. So I'd like to start by saying it's been really great to hear from architects that are getting their hands dirty, right? I think there's also other areas of knowledge that bamboo has, it's one of its problems and one of its successes is that basically craftspeople have never stopped working with bamboo. But the gap between their intuitions and knowledge and the research in engineering or in architecture has been pretty broad. And I hope I'm helping to kind of close that gap. So a few other things that have been kind of talked about, but maybe not clearly enough, is like, you know, in Europe and the United States, there's demand for construction. Of course, there's appetite for design and construction. But the real demands in the future really look like they're in the tropics, right? In arid and tropical climates around the world. And what's pretty interesting is you look at where population centers are evolving and growing, you look at where demand for housing is, it's mainly in the belt where bamboo also, you know, is a really kind of common growing material. So I'd like to kind of begin by asking us to think about bamboo as a spectrum. Until now, and most of what we've seen today, really occupies the edges for the most part. The edges are using bamboo as an engineered material, meaning you are engineering the fiber into a new composite, or bamboo as a comb as a material. And what I would say is that this binary that we've used and we continue to use is the problem of most of our material problems, and that actually it's the nuance, what falls in between, that requires more attention. And our work in the lab is just one example of what I hope will be many in the future. So just to kind of share a kind of broader net of the lab's work, in the room over there, you'll find Ramtin carrying on a project that we started about 6 or 7 years ago called Retooling Bamboo. And we're really exploring the nodes, the solidity, cutting into it, changing its vernacular, exciting students about the possibility of a standardless material. You know, are we measuring it? Are we not measuring it? In what way are we measuring it? And how does the unit change? We've also played around with lime plaster and using bamboo as a reinforcement, but also as an expressive element. We've also combined mycelium. We're researching mycelium, the root structure of mushrooms, as its own material, but also as it might be nature's glue for bamboo. And we think that this is an important speculation, but not a practical solution anytime soon. But we should be asking questions like, are petrochemicals okay or not in these composite assemblies? So, you know, we continue to kind of stretch ourselves by looking at other materials for how you aggregate, you know, the base material, in this case, bamboo, together. Also, is bamboo just one standardless material that happens to be nearly a straight line? But there are others that are less straight lines, like the limbs and canopies of trees, that in our context might be equally important. So we have begun to research that with USDA. Also, although absurd, how might we grow bamboo with computation or design control? Is that something that we should explore? our sponsors thought so, so we tried. It did work, but it is quite absurd. And then lastly is this idea of lightly modified bamboo. And the question came up, like, should you use the bamboo or any material in its most raw and natural state? And my opinion is when that's practical. And the question is, can we render something practical with slight amounts of change? And so that's, at least in the work that I lead most directly, the work I'm focused on is by lightly modifying bamboo, can we build composite systems that we can build structures out of? So also, I think, this idea of lightly modified bamboo is really about tuning. And we've been tuning materials for a very long time, right? With wood, we have lots of technologies that we've been developing for hundreds of years. Even with paints and coatings, we can tune the color. And in other materials, these are common technologies. Bamboo has had very little technical development in the last 300 years. So we have no real head start. And so some of the work we're doing at a very fundamental level is just trying to level the field. If we can sense bamboo, if we can machine bamboo, if we can lightly change it, can new kinds of architecture, construction, material come out of it? So I would also just like to recognize some of our sponsors. So the AIA Upjohn Award has funded a bunch of this research. Invar Latin America has also sponsored a bunch of it. And the Institute for Creativity, Art, and Technology at the Attack has been our other kind of main sponsor. And we've really had including all the infrastructure, in 8 years, less than $250,000 has been spent on developing this research. And one thing that I'm interested in is how as a community, we start to work together with other institutions, and how a lot of the work happening in the field actually brings students a really unique opportunity to experience culture, but also makes the development more applicable and less expensive. So, we really started with these two different trajectories, and I'm interested in sort of the opportunities that the morphology of bamboo might offer, and really how technology might interface with that. To go back to this idea, like, do we work with foams? Do we work with composites? And if it is a spectrum, where might our work sit in between? And what fundamental elements do we focus on? So we really focus on a couple, but the two that I think may be most important and have the most benefit to the broader conversation. One is the knowing or the sensing of bamboo, and the other is, like, how do we delicately modify it in ways that bring it more utility? And are those all digital? Are some of those analog? And what amount of change, what amount of subtraction or division is reasonable? So, on the left is the retooling projects, and you'll see Ramtin developing the next one of those using typical frames. That project has gone through a series of kind of experiments, and they're really aimed at, like, trying to put people's hands, students' hands particularly, on a material. Whether it's through assembly or through fabrication or even the mere act of cleaning the bamboo, do we learn something about materiality that we didn't know before? Also, if we begin to think that the line of a sketch and the line of a building might be more synergistic and we don't need a hard line, how might that change the way we think about making the built environment? And then on the other side, the more practical, perhaps one, is can we make panels that begin to mediate between what we might do in concrete or mass timber with a local resource in the tropics where we want to build. This work requires as much kind of design of processes as it does products or forms. So this is probably the work that I'm most interested in myself personally, which is to hack and build tools and machines to treat bamboo as any other material that has appropriate technologies available for its articulation. we spent a lot of time thinking about how its morphology affects its fabrication. So early on, just, where do you cut it? How do you respect the node? Can you come up with a new logic? How much, this came up earlier, how much of your design intention should shift? So I never remember the red from the green, which is which, but one of these sets of lines represents the idealized model. The other one allowed us to flip each element in its position to avoid cutting through nodes. So if you want to avoid the nodes, can you simply just flip a stick and move a joint a little bit? And is that form perhaps add value to this, a more honest form that is somewhat symbiotic between design intent and material expression? So this is what that looks like in reality. So do you really just, you find a node, can you just simply slip the joint? Yes, it changes the form, but is that in this case a big deal? My answer is no. So this was the sort of second of the three projects that help us clarify an idea, which is how to think about nodes and joints in a nearly solid bamboo in a way that might create aesthetic expression as you kind of reveal the inside, but also that would kind of remain practical and increase the efficiency of bamboo utilization. So the kind of third technique we came up with was basically stopping thinking about linear measure by inches or meters or feet, and to start thinking about biological measure of nodal distribution. So if you only terminate bamboo at a nodal length, and then you apply the nearest part, can you get to kind of close to zero waste? And can you also cap the parts by the nature of the material? So in other words, if you only cut on a node, it's naturally closed. It works sometimes, but it's not highly successful, but close. So, then the other thing we've been thinking a lot about is, again, how much do we remove and, what is the yield? In most engineered bamboo, the dirty secret is they're using like 30% of the fiber. In most round column construction, the dirty secret is they're only using 40% of the linear material that comes to this site. Sometimes higher, but sometimes even lower. And that's because dealing with bamboo's eccentricities using, incremental innovation is full of problems. And so this is the space that we are stumbling through ourselves. So, now many years ago with McDonald and Schumann, we developed this concept one night at my dining table, which was instead of exploring CLT as our next project, could we think of the bamboo line as a plane? Could we approximate something like CLT? It turns out that you can do that, but not the way that we originally thought. But it's important to, again, acknowledge sometimes you make an incremental idea first. So, we looked at like how logs are processed, we looked at how traditional bamboo is processed, and neither one of those methods worked, but some old machines did work. So the radial arm saw became a kind of critical piece of technology. And people would say, well, what about the table saw? What about splitting it? What about the band saw? And none of them really work. But this old machine that is considered dangerous and obsolete, it holds a blade in the air. And that geometry of the blade in the air made a huge difference. And so since then, we've been, in the US, we use radial arm saws because they're really cheap. When we go abroad, we bring a motor and we build our own machine because it's cheap. And maybe not any more dangerous. So we've tried to share this information, this knowledge, and it continues to grow. But basically, you can take the same kind of small diameter blade, and you stick it in the air, you can really, get through a much thicker piece of material. And we've developed strategies for how to hold these things so they're safe and efficient. And so there's, human-centered design elements of the process that we're really interested in. But there's also, of course, the utility of the product that we're using. We have tended to work, initially with these really solid species. I went to Kyoto, to Ho Chi Minh City, to Bangkok, and I've forgotten now, one more Asian city early in the project. And my wife is from Guatemala, so I actually knew of bamboo slightly from Latin America, but really thought all the knowledge was older from Asia. And although it may be fundamentally true, it turns out that actually just like we have forgotten lots of technologies, so has the rest of the world. And the only place maybe on the planet that really never stopped using bamboo to some extent was Colombia and Ecuador. And so actually most of the knowledge that we find, translated into the Asian context today is from work of maybe 60 years ago, 40 years ago, coming out of Colombia. So Guadua angustifolia kunth is a very prolific species in Latin America. It would have occupied most of the landscape if the Spaniards hadn't destroyed it as a form of, imperialism. So now it's a very small percentage of the landscape, often by rivers, on agricultural land, and growing in the wild. Also, we've used a lot of Dendrocalamus strictus, often known as iron bamboo or papata bamboo. And I use the vernacular Vietnamese name because it's quite unclear with many bamboo species what they really are. So we started this research after James Wolfe and I were playing around in his shop in Ho Chi Minh. And he's like, we can make a 4x4 out of this hollow material. And I didn't really believe him. And he did it. And it worked once. The next time it didn't. And I went home only remembering that it worked. So what we do with this bamboo to kind of get some kind of ability to make it into a composite is we lightly modify its let's say it's round diameter to two things that have parallel bases along a theoretical center line. And it turns out if you do that in really solid species, you get really little waste. And if you're surgical about it as you go up in diameter and hollowness, you still get a pretty low amount of waste. But it is notable that it doubles by percentage when the bamboo is more hollow. We don't need the thing to be totally flat and rectangle because we're only going to laminate it on two sides, not all four. So if you compare that to traditional bamboo splitting, this is just geometry. This is not a study of throughput. If you don't even turn these into rectanguloids, and if you ignore the actual process with which these are made, which removes quite a bit more waste, you still get 60% fall, or what some would call a co-product, which could be used for energy. With this process, in our best case, we get 6%. So this is like the most extreme polarized example, but there's some wisdom to light change instead of heavy change. It also translates to the number of steps in processing. Also, we think that you can use different parts of the bamboo for different parts of the building assembly, and that this third cut, and even what's called the kuhe in Ecuador, the fourth cut, are usually not used for construction at all. So their value is somewhat downcycled, but it is used for agricultural purposes, but not with the same kind of value. So we're thinking that maybe walls of different floors and floors with different applications in a single building don't need to have the same parameter. So this slide has already been shown in some form, but basically the taxonomy of the panel is there's a core, there's lath and layers and cross lamination, and then there is hopefully a very thin skin to avoid sun, water, and fire. We've made many different panels, one-offs from many different species, really just trying to sort of throw a lot at the wall and see what sticks. And momentarily, I believe that a panel that has 45-degree outer layers and a core running the long direction to the middle makes the most sense for a floor with pretty kind of high density of core members. Likely we'll still need some beams. And then for walls, a much more porous arrangement, and probably the bamboo could be much thinner in diameter as well. Also within a panel, maybe you don't need every element to perform the same way. This is why, parametrices, generative design, the scanning, all these things coalesce in this idea that to improve the kind of utilization, you really have to be really, really nimble with how you use material. So back to the question earlier about are we standardizing material? Not in the conventional sense, but we don't have all the answers in terms of the process yet either. Staying reading mode again. So just in summary of the mechanical properties, which I'm far from an engineer, so, don't ask too many questions here. But, the panels have all taken about 8 to 12,000 pounds to break. We've done a little bit more quantitative testing in more recent times that haven't been fully evaluated yet. And, these panels are 2 foot by 6 foot for about 5 inches. So from this 12,000 pound, maximum kind of load, like in Wiley's work, when they kind of spring back, they're still amazingly stiff. But we kind of discounted that as something that you could use in current construction kind of logic. So we can span about 12 feet with a ½ inch of deflection to the floor panel. Then the question might be, do we get true composite action? And the answer is not really yet. But what is somewhat clear already is that in regular bamboo construction, it's hard to make a floor because it's not flat. In regular bamboo construction, you would avoid any broken or cracked member because it would not meet the standard. And we use all of them. We use bamboo that's rotted, we use bamboo with holes in it, we use cracked bamboo. By compositing it together, our elements equal or improve the stiffness and strength of the same number of elements in the raw state. And we get the benefits of unitization. So here's just a look at different panels and how they broke. And I just pointed this one as kind of the one that I like the best. Just a slightly deeper dive, we've been looking at do we need connection systems that are more like CLT or more like flat pack furniture? And from the last week or two, I think we might be okay with CLT-like connections. But my earlier assumption is that because the edge of these panels is likely very vulnerable, maybe we need to move in further into the middle. And so developing tools that are inexpensive that can be used in the field has been another focus of the research. So should those be pipes? Should they be wood dowels? Should they be wood blocks and wood screws? But how do you assemble these things together is a question we're still asking. And so we've made 2 floors now, one in Ecuador and one in the Philippines. This now has 1.5 inches of cement on it and hasn't failed yet. But we haven't, and it's made with the wrong glue and the wrong saw. Long story, but JetBlue sucks. So basically, some of these things we're just testing in the field to see what happens. This is on a farm at Regenerative Field Institute, and Lucas is taking a small risk to put that much cement on an untested floor using tight bonds, not a proper structural adhesive. We've also been training, we're collaborating with Inbar, training construction bamboo carpenter that are being trained in these notions. They can't deploy them yet, but shouldn't we be engaging local people with some local knowledge in a wider range of ideas instead of the reduction to the simplest house? And then in the Philippines, with Base Baha'i and Pine Collective, we've begun to do a little bit of work that will be tested. We've also just decided that sometimes just jumping on something might be enough to tell you that has some difference. Thank you.
So provided you guys are willing to cut the lunch from an hour to a half an hour, we have time for some questions and a panel. So that's it's straight out there.
Or we can grab our lunch and then have a panel too.
You want to do that?
Yeah, so I'll take questions first and then let's have the panel. So I'll take 1 or 2 and then let's have the panel, if there are any questions at all. Yeah.
What, if anything, you took from the wood techniques that, since wood has been developed so much, did you take a lesson from that to?
I mean, absolutely. But so to start with, I'm trained as a metalsmith. I would say I'm kind of a materials expert at fabrication in many materials. And what I would say is that bamboo does not hold enough parallel space to any one material. If you take glass, steel, carbon fiber, and wood, and you put them together, and then you change their morphology completely, you have something like bamboo. So there are absolutely things you can steal from wood, but there are also things you can steal from metalworking. Probably the closest material that shares this range of possible ways to manipulate is aluminum. Aluminum, you can work in a wood shop, but you can weld, right? So like aluminum, bamboo has like a lot of dexterity, but also a lot of dead ends as a material for how you might process it. Sure. Are there any other questions? Yeah.
No, I just said church. No, it's very quick. Have you tried welding?
I haven't, but it can be. So like, so welding really is when you use heat to marry a base material, right? So let's move away from welding for 1 second and say you can change bamboo's density through heat, chemistry, and pressure, or any two of those variables. And you can definitely get ligand to cross-link across two pieces of bamboo in a thin strip. And there's a company that mostly makes composite materials for boat building in France that's got a proprietary method, which I think is Sonics, to make continuous filament out of bamboo. So I haven't tried it, but it's possible. But it's only possible maybe as a fiber, not as a foam. Yeah.
There's actually some work in Costa Rica Institute of Technology where they are welding bamboo sheet. There's some species have sheaths that grow off, and they're taking the sheaths and they're welding to create, formed panels with the sheaths.
And it's interesting you think whether you use chemistry, biology, or electrical energy to make that translation.
Well, I was just thinking in terms of like how a truss uses a plate.
Yeah.
It's welded to that plate, right? That there
Right.
could be an equivalency of bamboo somehow using fiber to connect.
Yeah, and I haven't done it yet, but so I talk about in my materials course about the different methods of assembly, of connection. And so mechanical, chemical, etc. And wood glue doesn't stick to the outside of bamboo, right? It's got way too much silica. But there are glues that are, for like people who don't know much about the chemistry, they're a little bit like super glue, but much tougher and thicker, called methyl methacrylates. And I think they may work as a way to composite bamboo skin together. And so actually those have been used to replace welding in things like highway signs that have big wind loads, but that are lightweight. Was there one more question?
Your talk is an absolute feast, and so I'm just going to do a grab bag of three different quick questions. One, have you speculated about pollarding and pleaching? That is the kind of manipulations of the growth in order to control the periodicity. And secondly, can you comment about progress in fireproofing?
Yeah. So
and third, how does bamboo age?
You're gonna have to ask the second two again. I'm gonna start with growth. So there's been work by two architects, Oscar Hidalgo Lopez, who passed away maybe 15 years ago, and the other one is actually not an architect, designer craftsman named Brian Erickson, who's an expat in Costa Rica, and they've explored growing bamboo either through tires or pulling into complex shapes. We did a little bit of the same work with sticking bamboo plants on kind of rotisseries with fixed angles and using grow lights with the plant scientists to just prove that we could control change of curvature. And then in the Japanese tea house, I met a 5th generation grower in Kyoto that builds basically an extrusion apparatus around growing bamboo. And if you can calculate the circumference and the conversion to a square section, you get it right, that prediction is correct, you can grow a square section. So that's been done with long apparatuses in Kyoto, and actually Lewis Bamboo somewhere, I think Mississippi maybe, has done some of it with very short, extrusion like apparatuses. So it is possible, and there are some species that genetically grow somewhat square. So I think there's a lot of room there, but I think there's so much territory before we go anywhere near growing it differently. For me, growing it that way would excuse the kind of clumsy moves of a craftsman at being a plant scientist, and just taught us some very basic things, experientially about growing material. But I wouldn't claim to. When we started, I thought we would stake a claim on subtraction, addition, and growth. And I would say that growth and cultivation harvest need a lot of work, but it's not work that I will probably focus on. Now, what were the second two questions?
Progress in fireproofing.
So there's a researcher, first name is Matteo, he's Colombian and he's working in Australia. And there's been some development. And I think must be more. And I think it's quite interesting that, again, bamboo will fall between wood and steel. And things like anemic coatings or those that can be absorbed into bamboo, they definitely have an opportunity to work. But because the bamboo will open in a fire, there's some other really complicated issues that I don't know how we'll move around. And I think the panels we're making, for example, I don't think we need cement for lateral stability, even necessary for mats, but we definitely need something to resist fire. And presently, we think that cementitious coatings or lime-based coatings will be the shortest path to actually have an impact in the market. And you have one more question?
The last one was about aging and embrittlement.
I don't know. Yeah, I don't have a good answer for that one. I do know that there are buildings that are 200 years old in Colombia and in Ecuador. Some of them even with sun exposure, where bamboo is there's risk, but that doesn't mean that it's as temporal as we might think. And that another interesting thing about so bamboo is now mostly treated with either borates that basically fill a bug's stomach so it can't reproduce and therefore stops consuming and destroying the bamboo in a building, or with other chemicals that are used as pesticides. And most of these chemicals are on the low end of risk for human health if they're used correctly. But the interesting thing about bamboo's history is that for the last 200 years until 50 years ago, in Colombia, what they would do is they would basically cut the bamboo, push it a few meters up into the canopy and let it drain for a couple of days, up to even a couple of weeks. And then they would maybe throw it in a river and wash it some more, maybe not. And they would store it in things a lot like a coffee house, like a solar kiln, for 2 years. And any bamboo that wasn't eaten by the insects after 2 years was considered durable. And that's what they would build from. So this question that came up earlier about time is a really important one. And I've been collaborating with some scientists from UC San Diego that work with algae. And a couple of years ago, we were debating mycelium versus chemicals made from algae that were plastic-like. And they were saying, no, it's just too slow. You can't grow a material. And I'm like, well, you were growing a material. Now you're growing it in a tank. The difference is, can we live or can we rethink modes of production to give things a month to cultivate instead of having to bring all the resources together in a moment? And this takes a large kind of cultural shift that will, whether it's from the reuse of cement or whether it's from the growth of new materials, in my opinion, it takes necessity. And we don't really realize how close to that edge we are. There's a video that I often show that David Suzuki made that talks about humans in a test tube and how close we are to kind of destroying ourselves. And I think humanity just does not recognize the urgency. Until we do, that time it would take is not seen as something that we can afford. So we should grab lunch and then we can have kind of a round table. Thanks, everybody.
Yeah.
When did your I think it'd be worth out how to consider. Really, you want to know that.
I'm so glad you're on. Presentations, I didn't collect them. I always look at the papers. No. Online. Yeah. Yes. Virtual or not. I don't come up with that. Yeah, they should go through. Like better joke on this. Yeah, exactly. Yeah, they are. They should be confirmed. They're mostly on stage.
Yes. So not so much structural modeling, and but I also do imbalance. I usually start with they physical action, right?
Yeah, most of the like institute sort of rehabilitations.
How do you know, for example, because I saw you, join some bunch of, for example, bamboo come together. How do you know, for example, you need 5 or 4 or 6? Did you, dimension before?
So that's where a lot of it just, there's loose dimension in the form, and then a lot of steel. Readjust. So I usually create parametric models that I can get a sense of where I want to go, and then I measure it when it's in space, and it will make the best figures.
Can Neil and Avery come up here? I'd like to queue up for the next panel. Can Avery and Neil come to the front?
It's a lot of starting with an idea, the field conditions of readjusting the model. So what we call parametric modeling allows for simple, quick readjustments.
That's possible that how much they are, comparable together. The first, for example, modeling and the result, the physical result.
They're not that close. I mean, they're close. I bet, but there's no ounce. And I think that's that middle space. How coaches it usually, and particularly I'm working in tropical areas where you're then not coming in like glass facade systems. But everything has your own columns, so it's a matter of like if we were in we probably do the structure first. Yeah, it's just building the balance of whatever we measure before we actually build. But that would be very complicated. No, I agree. Construction area. Yeah. The concrete's gonna have over a series of businesses. You can schedule in the lower the concrete columns, the higher it costs. But it's always a matter of how close do you need to get it to the exact thing you have, and how willing you are to have some tolerances and kind of make it just. That's something we cross for today. As architecture, traditionally, like, we want to have a quick control geometry, but if you allow the material to kind of, you can actually open up huge possibilities and still be very precise. Still have control. Actually, that's not that timber framing, cabinet making, or glass facades.
Is there other things for me to mention? Career.
Well, they created so far.
I just gotta put it quick. Yes. Almost so. I graduated with 2 years ago.
It's been a lot of fun.
That's myself.
Yeah, it's one of the coolest things. Every time, every time I visit like a specific search query or anything like that, there's always like new papers and there's probably been as many published in like the last 2 years as there were when I first started. So I love it. I think it's so much fun.
It's one of the reasons why.
Actually, so my graduate thesis is focused a little bit less on functional more functional functional. I just want to it also, yes. And just right, we a little bit nicer.
That's promising. Glad you have done this. It's really good.
Thanks, I'm really happy.
Yeah, we're getting.
Wow, I think it's with no socks or anything like that, it'd be about we had it was 2 cars, yeah. So we had one minivan and just
It's awesome.
it worked out really well.
The original plan is to rent Airbnb. You know about it? Okay. I just emailed it, but I just checked. So we did you see the abstract? So in the abstract, I wanted all grayscale images. And my grad student colleague who's making a book for me, it's like, this picture needs some color. And then we like, this like turns out the saturation just in time, just for yours. I mean, there's like one other paper here, but pretty awesome.
I appreciate that. I tend to stand out from the general architecture school of like flags and I don't like colors. It's always a challenge.
Yeah.
Oh, no problem at all. I appreciate that.
Yeah, they asked me later.
It's really nice to have a trouble master because all places are quiet and less. The airport is quiet too.
Hello. Hello. How are you? So Johan Park is leading this session. This is one of our faculty in the interior design program, an accomplished musician and interior design professor.
Wow, it's amazing.
Yeah, she's looking for positions. You don't have positions in Korea, do you?
Are you Korean? My school is actually a very small one, specialized in science and technology. So even my university does not have architecture department. So I teach design instead. So called convergence IT design. So kind of it's a mixture of technology and design thinking. So it's kind of also, it took a while for me to adapt to myself.
Coming back?
Architecture or other backgrounds?
Thank you for
My
finding that out.
first major was electrical engineering and electronics, but I so much love architecture. So later then I have master and PhD in architecture. But now I also taught at University of Miami School of Architecture. But now I'm totally outside of architecture. Yes, it's quite a shift, yes. So that's why I'm coming here. To feel about design and architecture, more about it.
What's happening with her box? I think we just do the.
They're really engaged in this. That's the thing. And I'd rather them being more engaged in more hands-on action.
So that's what I think building a lot of would be great. A good fit.
So obviously you even tell them if they want to help out today with this stuff too, they can look at it.
Yeah,
But I'm gonna make a phone call to Nikki to let her know that if you're okay with her just doing a little bit of presentation.
We also talked about the blue master. Yeah. Because she was with the other podcast.
So, okay, cool. I gotta run real fast.
Sounds good. Take a lunch with you and
I'm taking it home.
today. So we have an afternoon panel. And then there's the exhibition at 5. You don't have to stay for all of them. Feel free to, enjoy what you want and don't.
So those 3 days.
Oh, cool. Well, thank you. That's really nice. It's good. I'm kind of building a thesis statement of my research. Like that's kind of what this conference is. It's like setting a trajectory starting point.
Where to go from here?
Yeah. I kind of consider this conference like my coming of age party or something like that. As an academic. Yeah. And the publication is what I'm interested in. The conference is like a little featherling. The book is needed for my tenure track process.
Like everyone
all the papers, yeah. Because I submitted a paper also, but I would be the editor of the volume, right? So I'd be the editor and having contributed to it. Yeah, that's right. 1:30. I think. Is that right? Yeah, 1.
Are you recording any of the lectures?
It's all live.
But not.
It's all live and we'll stay on YouTube.
Okay.
Yeah, I mean, hopefully the mic's working well. See.
So if I'm over there,
Yeah, you can catch it later. Yeah, that was the intent. Was the hands-on stuff would be happening, and so people could take breaks and come in here, and it's just kind of multifaceted. Yep, that's the idea. And unfortunately, I think the students aren't taking advantage of it, but it doesn't matter. It's okay.
It's hard, right? I feel like you have to do something far from one for them to take space out of the work they do.
Yeah.
Or they have to right. For something which is very difficult.
Yep, it's hard. It's difficult, sure. Thank you.
And it's amazing from first grade to their 8th grade.
Yeah, well, I mean, Jonas was a force. Jonas Howland was a force to be reckoned with. Like, he heard about the conference, and then he got everybody to submit papers. It was awesome. So it's pretty heavily Virginia Tech. Yeah, well, it's starting. It begins that conversation for sure. Yeah, part of Jonas's award, or like his honorarium, was an equipment purchase for him. Was an equipment purchase. So he's got some equipment, like a significant amount of equipment that I purchased for him as part of the honorarium, and I'm hoping we can go over and take advantage of that equipment at Virginia Tech. We'll see. Yeah. How's your semester going? How's everything? It's good. You're working with Erica extensively? Oh, that's so nice.
Yeah.
That's cool. How did that work out? Because it seems like that's kind of a unique opportunity somehow.
It is. I think it's very. Well, there's like anything else. There's really big problems and some.
Sure. Yeah.
Well, the worst part is that you probably just get to know each other better.
Yeah.
It's usually one person supports people.
Eric, this is Hiroku, Eric. You guys met? Okay. We're just talking teaching. She's team teaching with somebody right now.
Second years, spring semester. It's also 2 sections combined. So we have double number, or sometimes triple the number of students in one classroom, 3 or 3 instructors.
Oh, that's interesting. Does it feel hectic? Like so much is going on at once? And maybe someone's a coordinator, right? Someone is the main teacher.
Let's do one thing. It's not like 2 different studios. It's one studio. You're working on the same project. They just have 2 different instructors. If they have any questions, we are going here.
Okay. Wait, you're going somewhere else?
Sometimes.
Oh, you know, I'm sure.
The challenge is that sometimes
you do, yeah, you do. Right, for sure. Yeah.
So we
did you have a photo shoot? Got to keep it renewed. Right.
Yeah, I was like expiration.
Yeah, that's interesting. Yeah.
You went up there?
How many?
Semester 1 class like 35.
You said 35?
Yeah.
Glad you're back. Okay, take your mom home. Get a box for her. Or 2.
Yeah, I remember in school it was
take some.
We're like not gonna 20, they separated our students, they broke us in half. Just
yeah, they're here, they're working. You might go touch base with them.
I think like similar projects, but just 2 different instructors. So yeah. Which I guess is nice because that's a lot of students to like critique and review. Yeah. It's a lot. I mean, this semester I have 19 in one class and then 9 in the other.
That's a high. Okay.
Studio class?
No,
Get some money.
schools getting, they whole your department's getting very big too, but with history class, I think it's just one section. I think she has 60, 70 students.
Wow, 70 students, that's a lot.
So that's
Yeah, but that was like the norm back in the day, like having between 50 to 100
like
students.
the big lecture classes.
Yeah, and like this reminds me of like the 80s movie Back to School. So with I don't know if you
Do we have any of those big lecture classes like that? Do we have any like big seminars at IU? Yeah, in Eskenazi, in Eskenazi.
Intro to art, architecture, design, or something. There is one class that everyone in the art student has to take. So that class is at the big lecture hall of Pioneersville.
Yep.
So you might get more address.
Maybe like a intro to photo or something like that might get a lot of people. Like cross majors. Sure. Maybe it's like history theory of some art form. But yeah, big, I don't know. It's interesting. I think we should take advantage of that more. The large lecture.
I mean, it depends on the subject matter.
I'm sure, but I mean, like, it's in terms of efficiency. Yeah. Get them through. I mean, I took a really influential class by a guy named Max Underwood, who had worked a lot with the Eames. You know, like he was personally connected to the Eames, and he taught a pretty potent lecture class, kind of history theory lecture class, to a huge, a big seminar in undergrad, and I think it was pretty successful. But we don't have a lot of history theory in Eskenazi school. We're pretty theory light, history theory light.
Yeah.
Like almost, yeah.
I think our department, like interior design, I don't know why, but we need to classes were required, but now we have to like English students, and I don't know if you see that.
Yeah, we had one and we did study abroad in Paris for 2 weeks for that class.
That's nice.
Yeah.
But just one. Yeah, one history theory with a travel component. Okay. Like that ups its potency a little more,
Yeah. Unfortunately, I got pickpocketed and.
Oh, you did?
And yeah, so I lost my wallet and everything, and then I had to like cancel my credit cards and get money Western Union to me. That part was disastrous, but the rest of it was pretty good. So yeah, it happened so fast, and but yeah, nonetheless, it still was a good trip. I was like, well, I'm going to Paris, so and I was couch surfing actually. I had 6 couch surfing hosts doing that, and everybody was like, despite Eric's misfortune, like in the references, because I told them what happened. And in fact, one of my hosts, they they were roommates during the time. A couple years ago, they actually got married. Pierre Philippe in Norway.
Oh, no way, really?
Yeah, so I actually flew to Paris, then took a train up to Valenciennes. So that's just like east of Lille.
Okay.
Like a small town, beautiful. They like went to the chateau, had an outdoor wedding reception.
That's
just
nice.
beautiful. And everybody was like, "You came here for the weekend just to plan?" I said, "Yeah."
Like I helped them hook up, right? Like I gotta celebrate.
Yeah, so that was nice because I mean that was years back that I met them, and then I said, "Well, hey, I'll come if you invite me. I'll come to your wedding." So that was actually that was a beautiful wedding. And the French, like I said, is the food gonna stop? They're like, "No, the food and drinks is just gonna keep coming until we literally stop." And I said, "They're like, Eric, you gotta try this." I'm like, "I'm full." No, yeah, don't worry, just a couple minutes, then you can eat more. You can drink more. I said, "Oh my gosh." But Italians, they know how to, they also know how to throw a wedding.
Because you went to one recently, right?
Yeah, that wedding was amazing. Like we were outside, then inside, then outside again. So yeah.
I'm gonna grab some food.
But yeah, so this semester I had less students in the fall. So so I teach in theory
yeah, it's nice. And for my cat doc specification that's in the class, I'm actually it's only 9 students, however, due to the nature of their final project,
I'm gonna break them up. So 3 of them will present potentially that could be the same night as our open house. So that's like great because we'll have you know, we invite the students to come see their work, but also they invite their friends, colleagues. We invite a lot of architecture firms. Usually I'll have like a list of firms that I reach out to, and then also ask some of them if they'd like to be on a jury. So some of them would say yes. Yeah, last fall it was a great turnout. So I'm looking forward to this semester as well. It'll actually be good if I can get one of the jurors, and I'll just finish my I hope he confirms it. But actually, his projects from his he's on the list. Premise behind that class is like the students are to research exactly what the famous architects are and architects. So after the list, yeah. So then after the list is like modernist architects, black modernist architects, and 3 of them, 3 of my students selected 3 projects for that, and so the jury, his project is on the list. Although I don't think anyone selected it, it's on the list, but I thought it would be great. And I just to have him, and I just saw him in New Orleans at a conference. I was just at the AFA conference, and so I saw him and asked him if he, you know, if he like yeah. Yeah. Well, also I said, well, hey, you're in my syllabus, and then I showed him stuff. He's like, oh yeah. I was like, in case you don't believe me. Because he's releasing a new book next month that he wrote, and yeah, so I think they're promoting the book, and so hopefully he does come. He can't come on Saturday, so I do have George for both days. And should be pretty excited. I always like a few people have been there several times. A few are like they just started coming out to my crib. So, but basically, one here's what that research. So like they'll begin just researching that architect. Their first presentation is about the house and the architect. I mean, I give them pretty much like what they need to say, just so it's standardized. And then they'll then work on the drawing documentation. So they'll actually draft the house themselves. It doesn't have to be like one-on-one, but just as close as they can get. Because later on in the semester, or by the time they get to the final, they're going to use those drawings specifically for the final, but also choose throughout. So then they also, I have an assignment for specifications where they'll specify the materials, the finished materials of an architect's house. Plus, I have them research or select a sustainable material technology, and then they can apply to that architect's house. So that's the midterm.
Different materials, like proposing different materials.
So it's like two parts. Like first just specifications. Like I had them. Normally I would have an inspector, but like that's now going away. So I have them use message back to do an exercise. So literally, if it's like 4 or 5 materials they identified, just do the 3 parts for that specification, and then for their presentation, they include that plus like that same material or technology. And then I had to do like cut sheets, specifications on that, just so they can understand what it looks like. And I said, well, look, I'm asking for what on a project. A lot. So that was in midterm. Now they're working on estimating. They're using having these RSMEs to do a cost estimation of the architect's house. And then the next part is they're going to present the next, not this Saturday, next Saturday, with, I have parameters for that as well. What I did also just gave them examples of previous student work, that they had, because then eventually I'm gonna have, another assignment where I'm going to give them a contract on the client. They're gonna do a site acquisition, and so wherever their, house is located, they're going to be located. We're going to do site acquisition relocated to like DC, Maryland, Virginia, which wherever it works. And then for that site acquisition time, the client that they're like replicating the house for. So they'll have a contract, and then they have to like fill out the scope of work, indicate like the phase, how long the phase is designed. They'll have to like hire a civil engineer, structural engineer, and then do like the cost of that as well for like those things. And so there's four parts to that, but the hard part is every semester they triple. The first three they did already. So all this is on purpose. Yeah, it's on purpose because I just, I'm like, you know, follow instructions because that's like really key. So I said, but I said you need this information for that whole part of that contract. So you're utilizing that, and I'm just asking for that. And students would always say, oh, I'm like, you did it, you submitted it. So I'm like, well, that's no point to that because you just didn't submit it. So I always have to explain that assignment. And then for the final, it'll be a combination of all of that, and I'll have them be an addition, like as a homage to like the architect's house. So it'll be like either a bedroom, a room. I have like three different dimensions that you can do. Like I can add like 10 minutes and then based specifically on the code that they can actually where they build it at. They'll just they'll just support and indicate that. And then I'll have them select another percentage material technology for that addition that they'll do. And so usually by then I'll have them do boards as well. So usually like 225 boards that'll kind of like the first one is like research part, the second part is like the design. Last semester, last year, one student, they all agree, one student in particular, he knocked it out of the park. In fact, I even had some please do like a 1.5 2 minute clip of like the design, and he just did it, and we had it on loop during the open house. We put his boards up, and everyone said their jaw dropped. They were like, "What class is this?" People were like, "Is this studio?" And then he was like, "No, this is not studio." But I said, well, you can apply to one of those classes. In fact, I had one of those last year, that same class, he works in construction management. So he said, well, hey, do you have any licenses to RCs? Because he said, I keep getting like trials but I didn't shout to the faculty and said, well, hey, you guys are great versus then we'll have a need, and maybe we can take some licenses. Other than that, for my class, I don't have any licenses like two assignments. I don't have that. There's going to be trials and stuff to do that. But some students, well, you don't or don't. Or do they just sign up and then forget about it, and then they're like, oh, listen, I can do it when the child is available. So then I'll have to like work around that. But usually I think you just have to just switch your but I like to stuff. I could have just did construction documents, but they have a course that's similar. I was like, I don't want to be bored. I think this kind of with the research component of them, get excited about the house and knowing about it. I said, well, you're an expert. And so just pretend like I'm listening to this design process. So yeah, those three steps, I think they come together, and I think the students don't really envision it, but then they get to like, oh, this all does come together. This all makes sense. And I think, well, eventually in career, you will do specifications for something, but you will not be doing it the same way will come on board. So this is so you can be exposed to it, so then when it does happen, you can get you'll at least reflect back on this time and say, oh, well, I think these types of assignments that relate to that. So I just try to make it engaging. And what I would like to do for the ones that you end up providing, I told them whoever's interested, perhaps if they So a few of them I didn't know they did it in Revit. And so we're utilizing VR at UBC. And so I actually have a VR set and then connect to Inkscape. And then it's just maybe just doing a demonstration of like their project, just like a walkthrough. I thought that would be like really cool on the day of their final with their group. So some of the try to push for that. I mean, all three, they don't have to. Maybe if just one of them want to do it, I think that would be really cool. And then if it's like housing and people like, what's up about the project you're doing VR? You know, they'll come at the cusp of it and they can just like engage. And so that's what I was talking about with Anna yesterday about curating my students' work. It's like usually outside of the world, in the past I was saying, or everyone saying, it's like disastrous. And I remember one semester, I mean, it's disaster. I mean, they trashed like the studio. So I came all the work and stored it, and then literally around it was securing the whole all the spaces in my class. And I remember getting like I was getting on a call, and I was just remember one of the questions. She's like, before I just gotta say, Aaron, oh my gosh, the studios look amazing. Like she was like, would you get up there? She was like, it feels like that's, you know, and so yeah, but I did take some time. And actually, it was funny because like a couple students saw me, and one particular I really want students to feel good about their work. And I just really number one program where she was one of the I mean, they were just like lit up. They were so just motivated. And they were like, oh, come see my project. So and then you know, and then for my class, I like cleaned up my students' work. Usually I try to go above and beyond and just do something like really creative. I'm using Notepad, so people like, so that's what are you doing this year? Like, definitely put your students' work up. Yeah, so I try to do what's like engagement. And I'm already thinking of ideas for like this spring. I'm hoping to execute that. I think I like this because in April, I got things going on, but I'm not going to be traveling. So the good part is I can like start like really working on that. And then by the time we get to when just making sure they're prepared and ready for it. Once you're there, I'm like, your project's not here. You can do it. So and then what can I do with that? Saturday or
Ready? Yes.
And so put them all I said that one. Whatsoever.
Hello, everybody. I really hate to say this, but I'm so sorry to interrupt your joyful conversation, but it's time to go back to reality. Would you mind coming to the seat?
Oh, God.
Okay, in order to keep the time, we're gonna need to start the next session, unfortunately. Let's keep the conversation going. This is really amazing. I know that we're having some wonderful conversations. Looking forward to starting the next panel. I know.
Yes. Are you ready for your presentation material here?
I'm ready, yeah.
Do you have a file? Oh, you need to translate
Your laptop? Oh, sure, absolutely.
How about you do it on his?
I can send you the presentation.
Is that okay?
Actually, I'm a little bit run out of battery.
Oh, you did? Do you have a
So I-
power cable?
I can turn it.
Okay, oh yeah, then actually it would be.
Whatever is smoothest, I can help with. I don't know if we have the same charger.
If you don't, we can probably find one.
Oh, okay, actually, I'm just using USB-C type.
Let's see. This one is one. That's that one.
Yes.
Super.
It's sometimes going to use my mic actually, but it should work. Oh, I did that.
Or you can just use you have a laptop and then you can just use this gender, so you can plug the HDMI can be plugged to USB-C.
I have the HDMI too.
Yeah, so you can actually ready right after the first presentation, or do you want to make it ready now?
Sure. Will I be presenting first?
No.
Second. Oh, is this power cable?
Yeah.
Okay. Yeah.
Hello, everyone. Can you see us?
Not yet, but we can hear you, and we
You
will
can
be able
hear
to
us.
see you once we get started.
We hear an echo. Do you hear an echo as well?
What's that?
For us, there is an echo on the Zoom link. Participants, we hear your voice echoes.
Okay, we have a very slight echo here, but maybe you have more of an echo there.
It's pretty good.
Is it bad?
If there are two hosting computers, there might be an echo between them, or something like that.
Try again.
We can still hear an echo, and we cannot see you, but let us know if you can see us under Kelechi's name.
Sorry, one more time. Did you have an echo?
Yeah. Yes. There's another participant from our lab, and she hears the echo as well.
Okay.
And I'm seeing two screens with who has a voice. One is by Spencer and one is another Spencer, which is the co-host. So it might be that because you have those two
Thank you.
computers connected, it creates echo.
Stop sharing screen. Let me see here.
Sure.
Is the echo still there?
No, now it's gone. Fantastic.
But that's because they can't hear us. Or we can't hear them.
You can hear us.
Check 1 2. Nope.
Now there's an echo again.
Wait. How about you try? You just talk and let's see if you have an echo. That's what's important. Please say something.
We hear you. I don't know if there's an echo if you speak out.
But there's no echo from our side. That's what's important.
Gotcha.
We don't hear any echo. No.
Sure. But in the Q&A, if there's an echo, it's really hard for us to hear you. I'm seeing the co-host, Spencer co-host has the screen shared, and there's a Spencer host. What happens if you mute Spencer host and keep the Spencer co-host? Hey, now you're seeing us. Yay. I think like you need to mute one of your accounts. Now it's muted?
Sorry, one second.
No, still haven't. Still haven't. Maybe because. Yeah, I'm not an IT person. I always get confused. Why is that happening?
I'm worried about this.
I love that shadow. That's good.
I think we're gonna try to deal with the echo during the Q&A. I'm sorry, that's not it will be perfect for your presentation, okay? Sorry about that. Yes, but it's not the same way. Okay. Turn your audio on. I'll turn it back on. Welcome back to the afternoon session. I'm very excited to introduce Juhan Park. He's probably a lesser known quantity than some of the other people here. I'm happy for that. Because he's no less of an influential player. And I'm really glad that he's here with us. I mean, it's really difficult. He's done so many wonderful things in his life. He's currently at a university in Korea called Post-Tech, and he's running a lab there based on human-centered human-computer interaction, HCI. He's done research at MIT. He's worked for Blau and OMA. You know, he's just kind of hit all the things he's done. And so really happy that he's here, and he's going to be presenting work on institute resource utilization on heavenly bodies, you know, like Mars, Moon, etc. And so a lot of the presentation, he'll get into this more, but a lot of the presentations this afternoon are dealing with institute resource utilization. So we're really great to shift gears away from bamboo into other things. We're really happy that we have the bamboo in our back pocket now, a little bit more. We all are a little more expertise, gain a little more expertise in the subject. We're going to kind of travel to other areas. And so I just want to turn the session over to Juhan for his mediation. Thank you.
So I know that many of you, my previous professors, have a problem in memorizing my name, so I'll be introducing my name. My name is Juhong Park, even my grandfather. Ju means actually column, and Hong means giant. So basically, I'm a giant column. So my grandfather might know that I'm an architect. But actually, in terms of pronunciation, Juhong actually represents the color orange. So you can remember it as orange juice kind of juice. Okay, so I'm a researcher in convergence IT engineering. So my job is actually connecting everything around IT technology. So that's what I do. That's my topic. And then today, I kind of read about amazing papers today that Olga and also Avery and also Neil, and also including mine. And I kind of thought about how can I organize these amazing projects together. And kind of one way to do it is actually referencing Bruno Latour's mediated situation, always my favorite theory. So just everybody knows about it, just for some people who may not be familiar with it. Bruno Latour theory is called the actor network theory, AMT, and then actually he explained that there are different actors. It doesn't matter whether some of them are humans or some of them are artificial objects. And actually, they together create another network, and this network actually translate all the participant object, including human being or non-object or non-human being. And this translated or transit or networked condition actually transform the original being to something else, and then they never come back to the original purpose before. And actually, during we all remember that during the last COVID outbreak, you were already mentioned that we can never go back to the previous normal. But actually, I'm very kind of excited about the last 3 hours presentations about bamboos. And actually, bamboo to me is basically the food for panda. But now bamboo is amazing potential that structurally, ecologically, that now I have a very different understanding of bamboo because of the network that we created here. And actually, I cannot go never back to the previous bamboo at all. So today, and then actually in this section, we are going to talk about sugar kelp and also mycelium and also earth material. That agent is actually worked with 4 and 3 amazing presenters here, and then actually create another new network. Then probably we all together will create a new network and new understanding about this new material. And then we cannot go back to the previous state once we understand after watching this presentation. So instead of kind of like simply switching gears from bamboos to this amazing material, actually previous, I kind of remember Wiley, you actually mentioned about great question in the middle of presentation that should machine train about material or we should train human being to deal with the material. And actually this session is answering that questions that it's not really about dissectional word that teaching machine the material, human material. It's actually machines or technology or material. They became create a new network and could be a new condition. Then actually we are actually mutually become a new agent or new property. And then actually together we kind of will explore how those new conditions will give us a new insight about it or about them. What I mean by them is both material and the technology that all of 3 that Olga and Avery and Neil will talk about. And actually that the hidden agent here is actually those 3 presenters. And we are kind of we will see that how amazingly they present or they create a new network with those materials. And then we think about that as material as one agent. And then actually Neil and presenters are actually platform. And actually we all know that how platform changed the content as if like the things that I cannot do anymore is actually waiting a taxi or waiting a pre-programmed schedule on the TV. I cannot tolerate that because this time is actually while you're watching YouTube or Netflix, you only see that what you exactly want to see at the moment that you want to see that video. So actually you cannot go back. As almost similarly, you don't really wait for a taxi anymore. You call a taxi using Uber exactly when you need it, and you just at the moment that the taxi will arrive, you just go out. So actually, that platform actually changed the content, not just change the content, but actually how we interact with the material is kind of totally translate or transform. And actually here today again, Olga and Avery and Neil will show us how this kind of material as an agent and platform, their technology, their insight will transform the way how we interact with these new materials. So from now on, actually, I first introduce Olga. I pronounce correctly, Olga Beatrice Calcazzi. Is it correct?
Hello, I'm Kalechi. I'll be presenting for today. There's an echo, so we're not able to hear.
There's still an echo.
Yes.
We're just gonna introduce. So bad. We're going to introduce.
Can you mute them temporarily? Tell them what you're gonna do, and then unmute them.
Okay.
We can't understand what.
Okay.
Are we good to present? Is okay. Okay. Hello, my name is Kalechi and I am a second year Master of Architecture student and a research assistant at the Natural Materials Lab, where I work alongside Assistant Professor Lola Benelon, the lab director, and Olga Kakasi, Assistant Research Scientist here at Columbia University's Graduate School of Architecture, Planning and Preservation. At the Natural Materials Lab, we explore innovative uses of raw earth and fiber-based materials. Our research delves into the material life cycles, supply chains, and fabrication techniques, aiming to create socially equitable and ecologically sustainable solutions by merging material science with architecture, art, and design. So today I'll be presenting our research looking into the potentials of kelp algae as a material for sustainable construction. The motivation for this study came from the recognition that we are in a time where circular economy and environmental regeneration conditions for building materials need to shift toward locally and minimally processed material solutions. And the lab identified algae as a material of interest for its capability to be locally sourced, low carbon, minimally processed, and because of its status as an underutilized biowaste. Seaweed in particular offers unique advantages as a material resource because it does not compete with land-based crops for arable land. It offers a vast landscape for cultivation without worry of interfering with existing land-based systems. And seaweed does not interfere with food production and absorbs excess nutrients from agricultural runoff, giving it the potential to mitigate issues like eutrophication in marine environments.
Kelsey, are you progressing your slides? We can't see any progress in your slides.
Oh, we are progressing the slides. I'm not sure why.
If you have a second screen, then move that presentation back over to your other screen.
You know, to fix this. Give us a moment. We'll try to fix this.
Share it again.
There's a reason there's no echo right now. There's no echo anymore.
Oh, yeah, there's no echo anymore.
Where is the
It's right there.
Which one did you share it already?
I believe it was this. Wrong. That's the wrong template, I think. It should have been this. Oh. So that's still somehow not working. Should we try this?
You only open that?
Yeah, maybe we could try sharing from your screen. All these presenter notes here. We're just going to try sharing from Olga's screen instead.
Can you see us now?
Yes.
Okay.
Okay. I will just start right back here.
And you can continue.
All right.
We don't have the slides.
Yes. Let's see. All right.
You can go to
it's this way.
go down with you.
All right. Are you able to see me moving the slides now?
Yes.
Okay, great. So, as I said, today I'll be sharing or presenting our research looking into the potentials of kelp algae as a material for sustainable construction. And the motivation for this study came from the recognition that we're in a time where circular economy and environmental regeneration conditions for building materials need to shift toward locally and minimally processed material solutions. And the lab identified algae as a material of interest for its capability to be locally sourced, low carbon, minimally processed, and because of its status as an underutilized bio-waste material. Seaweed in particular offers unique advantages as a material resource. Because it does not compete with land-based crops for arable land, it offers a vast landscape for cultivation without worry of interfering with existing land-based systems. Seaweed does not interfere with food production and absorbs excess nutrients from agricultural runoff, which gives it the potential to mitigate issues like eutrophication in marine environments. Historically, various species of seagrasses have been utilized in their natural form, often bundled and compacted together to create fiber mats for insulation purposes. These seagrass mats provided an effective, low-cost, and sustainable means of thermal and acoustic insulation in buildings. And due to its natural resistance to decay and excellent insulation properties, seagrass was commonly used in traditional European architecture, such as in Denmark and Germany, as you can see here in this image on the left, where eelgrass was woven into thick layers for thatching roofs and lining walls. And that ability of seagrass to resist mold, pests, and degradation over time made it a durable and efficient bio-based material long before modern synthetic alternatives emerged. We also looked to the more current innovative example of Sargablock, a brick developed from sargassum to utilize the excess washed up sargassum polluting beaches in Mexico and the Caribbean. The bricks are composed of 40% sargassum and 60% other organic materials and serve as an eco-alternative to traditional bricks. And as well, in Mexico, the mucilage of nopal has traditionally been used for a variety of purposes. And we're thinking that beyond its structural applications, seaweed also has the same potential because it contains valuable biopolymers found within its mucilage. For the purpose of this study, 3 different experiments were conducted. Firstly, pressed kelp to investigate whether kelp could be melted or fused together at high temperatures. Second, boiled kelp to investigate how heat and submersion may impact the kelp. And lastly, ground kelp to investigate optimal compositions for shape retention. So here's just a simple visual that kind of displays our experimental procedures and steps that we took. And for our first experiment, the pressed kelp, the guiding observation kind of question was, how will heat impact kelp? Can this be melted? Will it fuse together at high temperatures? So using our materials and equipment, we went in by manually tearing the kelp to pieces that were roughly 2 to 3 inches in length. And then we layered multiple pieces of kelp and pressed them under the dab press heating element and let them sit for 10 minutes. And we conducted these trials both for dry kelp and for kelp that was wet with a few drops of water to see if any difference would be made between these. So here are just some images of our kelp trials pressed at different temperatures, both dry and wet. And after conducting the experiment, we had our samples observed underneath an electron microscope. So you can see here that the kelp structure kind of became denser and flattened from being pressed compared to the non-pressed control where the structure is looser and not as dense. So our results there were that heat had negligible impact on both the dry and wet kelp samples in a manner that was visible to the naked eye. The kelp generally remained intact and was able to withstand heat without damage extremely well. And so we can kind of conclude that heat doesn't appear to melt the kelp or visibly fuse it together. For the next experiment with the boiled kelp, our guiding question was how heat impacts the kelp while it's submerged, because we wanted to look further at this quality with water. And in this experiment, we filled a pot with water essentially, and then took our pieces of kelp torn to 3 to 4 inch length pieces and kind of overlapped and folded them around each other. We wanted to see if there would be any kind of adherence or cohesion, and also, of course, did a control. And from this experiment, the most notable takeaways were that the water that was used to boil the kelp changed considerably from its original state, as you can see here in the images. So the boiled kelp did not really perform visibly from the control kelp. The key takeaway was that the water color changed considerably, suggesting the release of this mucilage. For our ground kelp experiment, the question was how best to adjoin the kelp particles with soil. So we focused kind of on grinding the kelp to make a fine mixture and then start adding small concentrations of soil to begin to observe how the two perform together and to determine what is an ideal, maybe mixed design to continue looking into kelp soil samples. So for this, we used a Vitamix to shred the kelp and then sifted it to our desired granularities. We looked at 4.75 millimeter particles first, and then 850 micrometer particles a second. So here you can see the mixed designs that we tested. And between the first and the second kind of trial across the different sizes, we decided to divide our ratio parts into tenths rather than quarters, just to gather additional information looking at these. Here are some images of the kelp samples after they were finished, so you can get a sense of kind of the scale of them. And these are the resultant pressed tiles in higher quality images. So on the left, we have the samples containing more natural soil, and toward the right are the samples with higher kelp content. You can see the resultant shrinkage in the varying sizes kind of the samples as you move right. And this is because the kelp soaks up so much water that it results in higher shrinkage for the kelp heavy samples. So that's something that kind of has to be mitigated and overcome in the structural durability of making samples of this nature. Ultimately, our takeaway was that the integration of kelp with soil is highly dependent on that kelp to soil ratio. And we found that the 3 to 2, 1 to 1 kelp to soil mixtures yielded the most promising results. As well, the longer fibers yielded more stable kelp soil final elements, likely because the longer, larger fiber was able to provide more mechanical support. So in our conclusions, basically sugar kelp-based materials in applications such as biological mats will require strategies to achieve cohesion and structural integrity, and would likely be possible with an alternative binder. Our boiling experiment highlighted the role of heat in facilitating the release of water-soluble compounds. the mucilage that could function as a natural binder or stabilizer in this case or in other cases. And our ground kelp experiment showed us how important the integration of, how the integration of the sugar kelp with soil is highly dependent on that ratio, and gave us insight on how to yield a more ideal mix design. For future directions, let me play this video. For future directions, we're interested in additional material characterization, such as strength testing, biodegradability analysis, long-term durability assessments of different kelp composites. And we hope to investigate the effects of different drying and processing techniques to see how that could further impact or enhance the mechanical performance of kelp-based materials. We're also interested in just the scaling up and evaluating environmental impact of these processes in the real-world applications. That will be critical to integrating sugar kelp into circular biomaterial systems. And I think we're most keenly interested in exploring the application of kelp-derived mucilage as a biopolymer-rich solution that could provide an alternative kind of stabilization strategy for low-carbon earthen materials. So. Well, that's the end. Thank you.
Thanks for your amazing presentation. Is there any questions from table? Yes. Give her a mic. Oh, back in there. Can you hear her? Okay.
Are you able to hear
Your
us?
mic is off. Okay.
Are you able to hear us? Are you able to hear us still?
Yes.
I think use yours or mine.
Okay.
What they say?
We currently can't hear you.
To the
Okay.
Hello.
Hello, we can hear you now.
Okay. I'm wondering if kelp grows like grass. Like, can you put it onto the, if you were developing a coastline, could you like grow it to help with purifying the water, but then could you also cut it like grass and then process it to make the buildings on the coastline? I don't really know how kelp works.
So the kelp can be grown along the coastline. I think even the kelp that we're harvesting comes from Lazy Point Farms, and a lot of it is used for the cultivation of oysters. I'm not sure how much the kelp behaves like grass in the sense that you would be able to cut it and grow it along the coastline in that manner, but
okay,
like you can just cultivate it, yeah.
Okay, thank you. Thank you so much.
Any other question? Actually, I have some minor question that in your presentation you show amazing tables showing some other components or elements. Would you mind explaining what the table enlighten us?
Sure. The table was just showing the different mix designs that we developed. So we looked for the 4.75 millimeter kelp. We looked at different ratios of kelp to soil, kind of 1 part kelp to 3 parts soil, 2 parts kelp to 2 parts soil. So just this progressively. And then for the 0.85 millimeter kelp trials, we were looking at kind of these ratios of 1 part kelp to 4 parts soil, broken into tenths rather than quarters. And those were the tables.
Okay. And then how do you get the idea of using kelp?
Of using.
How do you get the idea of using kelp?
I think we were interested because we had the opportunity to go to a kelp farm and to kind of harvest some of the kelp and see what we could make possible with it. So I think we're always looking for new ways to kind of explore and apply what we're doing here. And it was more that we had access to the kelp and just decided to jump in and start asking questions about what could be done with it and what experimental pathways we could start to look at.
And then when you explore your methods, such as at first time you try to create a mat, but then later that you want to create some mixture with soil, and then later you actually extend the idea into 3D printing, then how kind of like set up your experimental design of using this kelp into mixing with other materials? How do you organize your thinking, or how do you get those ideas?
Well, we're kind of building on each experiment. So we started with just some initial questions to base ourselves, but then based off of what we found in, say, the pressed kelp trial, where we saw that the kelp didn't melt or fuse together, we thought, okay, maybe if water is present for this whole process, that might be different. So that experiment was kind of built off of the results of the prior one. Same with moving into making the pressed tiles. After boiling, we saw kind of that heat could be a factor in the release of mucilage, but not necessarily in the material composition of the kelp. So we wanted to now see, since we are in the habit of mixing fibers in soils, how those two could come together.
Very nice. Other questions? Oh. Thank you very much for your great presentation, and it is so nice to see your amazing work and also the great work in your backside of your desk.
Thank you. Thanks for having us. It's great to present.
Right. Okay, thank you very much. Okay. Next presenter, actually, Avery is the second, right? Sorry, Neil. So Avery is currently MS architecture student. Also that with the amazing cohort. Oh.
All right, sweet. Well, first off, thank you so much, Drew, for the introduction, and Spencer for having us here. I'm really excited about it. And I'm excited to present my paper that explores secondary coatings for mycelium-based composites, looking at the interaction between materiality, appearance, and perception. So first off, a little bit of an introduction to mycelium. If you don't know what it is, mycelium is the vegetative root-like body of fungi. So it's comprised of these fine hair-like hyphae that excrete digestive enzymes to help conduct external digestion for the organism. And in nature, it does this often underground in dead and alive trees and other organic matter, and nourishes the organism so that eventually it produces fruiting bodies or mushrooms and reproduces, for the sake of persistence. But in the built environment, we can use it to create what are called mycelium-based composites, which are a class of material where mycelium grows on organic substrates and essentially binds them together. Some folks refer to it as nature's glue because of its natural binding properties. The substrates that it grows on are highly renewable, often coming from different waste streams. So things like sawdust, hemp, and soybean hulls, these are often sourced from agricultural, industrial waste, and tons of other agricultural post-consumer waste can be used to grow mycelium on. So it kind of just speaks to this highly renewable nature of the material. It's also at-home compostable. So anywhere from 14 to 45 days, a material, you can throw it in a backyard compost bin and it will fully biodegrade. It's also a very highly insulative and fire retardant material. And in addition to these kind of material benefits, it has pretty highly tunable mechanical properties, ranging anywhere from bone-like to cork and wood-like, depending on how you process it. To produce composites, you basically just prepare your substrate, moisten it, sterilize it, and inoculate it with a live mycelium culture. You let that grow out, and then you mold that grown out material into whatever your final form is. Now, a little bit more background, why mycelium-based composites? So in the United States, in 2018 alone, over 10 million tons of furniture were landfilled. And that's just looking at furniture, and that's just looking at landfill, not the entire scope of the waste, but there's a huge waste problem we have, and materials that aren't renewable and don't environmentally friendly go back into the grown environment pose like a pretty substantial issue for us. So mycelium-based composites offer like a really promising alternative to things like EPS foam, other like synthetic petrochemical-based products, as well as even things like fiberboard, wood-based composites, and other materials that have high levels of synthetic binders, which is, and these physical properties, like this wide range of properties I'm discussing, is what most of the existing kind of research focuses on with mycelium-based composites. But unfortunately, despite this really high potential the material has to take a number of different forms, it's still an under-desirable material to consumers. Folks are a little bit turned off by its like fidelity and overall aesthetic qualities. And so because of this, this research focuses on aesthetic refinement of mycelium-based composites using secondary coatings in applied context of consumer products. So these are a couple of the mycelium products that are out there. Most of them are speculative. The lamps are on the market, but yeah, we'll go ahead and dive in. So the approach I took to this research, first, I applied different coatings and treatments to just small little swatches that are made of mycelium-based composites. Those swatches were then evaluated. The metrics for this evaluation were based on a literature review of kind of consumer perception and reaction behavior, as well as a kind of comparative analysis to mature materials used in consumer products. The swatches that were then, the swatches that were most effective following those identified metrics were then applied to some simple luminary prototypes also made of mycelium-based composites. And then finally, those prototypes were evaluated with a small group of students in a consumer survey fashion to assess actual like external opinions on the material. So a little bit of clarification about what those kind of desirable attributes for a material and a product are. I conducted a pretty extensive, but only in some ways touching the surface on consumer perception literature review. You can basically break it down into two key sections, aesthetics and perception, where aesthetics relate a lot to like the sensorial and tactile, visual properties of a product, especially in its application. Whereas like the perceptual components relate a lot to the kind of individual and very subjective cultural and personal backgrounds and symbolic interpretations folks have of materials and products. But despite the subjectivity involved in desirability as it relates to products, there are a couple attributes that I identified as being broadly desirable. So these are the ones I'll dive into a little bit in a second, but helped evaluate the different swatches that we produced. In addition to those metrics, to help with evaluating the swatches, they were also compared to a small range of mature materials used in, like I said, consumer product applications. These were identified based on the kind of physical properties of the material, as well as the visual and material properties. So mycelium-based composites, just across their range of potential like forms and functions, are generally strongest in compression strength. They are opaque and they're produced by molding. And these processes are very similar to things like ceramics, including concrete, terracotta, and other stoneware and porcelain ceramics. So those were identified as big comparisons because of that. And then talking about just kind of material from nature materials and visual properties, things like particle board, cork, and wood were identified as other comparisons. So putting that all together with the literature review, these 5 evaluation criteria were identified to drive the assessment of the treatments: visual harmony, novelty, weight, surface regularity, and conceptual consistency. So a couple of these are pretty self-explanatory, but in terms of novelty, I'll clarify that the literature review showed that consumers like to see a moderate level of novelty. So they want a material to be distinct from kind of the existing competitors, but they don't want it to be so unfamiliar that it's off-putting. Weight also had a similar balance where you want a moderate amount of weight, but you don't want it to be so heavy it's kind of impractical. Surface regularity speaks more to the like physical surface manifestation of the material, like that really tactile sensation. And then conceptual consistency speaks to the product in its kind of very holistic context. So this came from a study on bio-based materials in design applications. And essentially it consumers identified the fact that greenwashing is a problem and they don't want to see a product that is supposedly sustainable and environmentally friendly, but there are parts of that process or its appearance that don't match up with that like supposed background. And so that question asks like, basically, does this material look like it's natural and fit within that like circular economy that it's claiming to? So these were the swatches that were treated. There were 11 different coatings selected to be applied to the materials. All of the coatings had to primarily be biodegradable. That was kind of the first key criteria because since mycelium-based composites are so readily biodegradable, it'd be a shame to introduce something that isn't to the material. Additionally, most, if not all of them, have some sort of precedented like efficacy in woodworking or other applications, just to show its potential a little bit. And then one swatch was left as a control, untreated. But beeswax was used in two forms. One just brushed on as a coating. Secondly, as a infusion baked into the kind of body of the material. A natural dye made with madder root was applied in two different forms. When you're using natural dyes in textiles, which is where that kind of precedent for this came from, generally you have to conduct a mordant process before you do the actual dye process. A mordant is just something that helps fix the dye to the actual fiber. But since no one had, to my knowledge, dyed mycelium with a natural dye before, I did one without a mordant and one with a mordant to kind of see the little bit of the difference there. And there was a bit of a difference. I also used a natural furniture polish that was made with different waxes and other oils, really popular amongst woodworkers and even kind of DIYers in terms of like, refinishing furniture and stuff like that. The oil paint and the shellac paint and the shellac tint below used a natural Mayan red natural earth pigment, completely natural, also biodegradable. And the oil paint was homemade, so it also just used a refined walnut oil as the carrier, which was also applied by itself alongside a linseed oil. Both of these oils are considered drying oils and again are very popular amongst woodworkers in terms of finishing. So these just like explore a little bit of that. And then the last big ingredient was shellac. If you're unfamiliar, shellac is derived from lac beetles, which grow on trees and other woody plants, often in West Asia and but all over. And it's essentially a like waxy animal-based resin. It's also fully biodegradable and depending on how it's processed can be more or less environmentally friendly, but does have the potential to be done really sustainably. Now talking a little bit more about these evaluation criteria to assess like how harmonious visually it was to have a little bit more quantitative support to this. I used histogram analysis in Photoshop, just assessing basically the variation in luminosity or value of the scans. And while this isn't like the most robust method to assess a material surface, it does have precedents used in like quality control and surface monitoring in production. So I use that just to give a couple points and take away a little bit of my own potential biases in assessment. Novelty, like I mentioned, I'm comparing to the material comparisons and seeing how similar or dissimilar do they look. Weight, pretty self-explanatory. The swatches were weighed before and after coatings, and that was documented. Surface regularity was assessed both just by feeling the materials and looking at them in person, but also they were scanned on a flatbed scanner. And due to that like really short focal length of the scanner, the areas that are more blurry are more recessed in the photo. So I also use those images to help guide that assessment of the swatches. And then in terms of conceptual consistency, this is probably the least objective evaluation metric, but I essentially just asked how environmentally sustainable does the swatch look after it being treated. And this is a kind of high-level overview of how those materials ended up performing. This is a little bit more focused, showing the ones that did perform most successfully. So there were 4 that were identified as having the highest potential. And then the uncoated control was also used in the prototype, again, as a point of reference. So the beeswax infusion, natural polish, and shellac all performed most desirably in 3 categories and undesirably in 1. Shellac paint performed highly in 4 of the categories and pretty poorly in just 1 of them. But these were identified as the coatings and treatments to apply to the prototypes. So a very like simple design was made, and the prototypes were produced using kind of standard mycelium production methods. So these just show like an overview of what those look like. And with these prototypes, they were evaluated by a group of 8 students who asked just a couple key questions about, how do they perceive the material? What about the material do they like? What about the material don't they like? And also just to help contextualize the mycelium in the broader scope, we asked what materials does this prototype remind you most of? So that's what I'll kind of run through for each of the prototypes. So the uncoated version, folks in some ways liked the texture and the consistent color. It was also thrown out that they liked it was hard looking, but generally folks did not like how unrefined it looked. It was received as looking kind of like mold or compost, also very rough, very lightweight, and the sound when interacting with the material was pretty undesirable to folks. The bolded, by the way, bolded terms are ones that multiple students agreed upon. So those kind of had the biggest impact in driving some of the students' conclusions, but folks related it to things like foam, popcorn ceiling, and stucco and plaster. So other kind of semi-refined materials, but pretty rough. This shellac version, folks enjoyed the color and the visual texture, as well as the smooth tactile finish to the material. In addition to just applying the shellac as like a single coat, as was done in the swatch, with a couple of these prototypes, they were also sanded on the surface and applied in a couple different iterations, just to again drive for a little bit of greater surface fidelity and smoothness. Folks did not enjoy the physical, like some people said it felt a little bit sticky, and other people disagreed with the kind of texture and said that they didn't love it. And it also was agreed that it looks a lot like OSB, potentially like wood, but materials, again, that don't necessarily have that high level of refinement or fidelity as you want in a consumer product. The shellac paint arguably performed the best out of all the prototypes. Folks really enjoyed the uniformity of the color and the finish. Some people liked the color choice, some people didn't. But overall, they enjoyed the fact that it was cohesive and also shiny. However, the surface, while smoother than the control, was not perfect. So that was another key thing that we're looking for a little bit more refinement in. And it was also compared to things like plastic, painted wood, and rubber and powder coated metal. So it definitely lacked in that conceptual consistency kind of criteria. And that was another one of the kind of key criticisms of the prototype, was that it didn't match up with, it didn't look like it was going to be a material that was highly sustainable. The beeswax infusion, folks loved how good it smelled. It smelled, if you ever smelled beeswax, it does have that kind of like honey smell to it. And smell was not anywhere on my like list of criteria, as you all probably noticed, but people like loved it. They also liked the fact that it was more cohesive in its texture, but it still lacked that like true consistency that they're looking for. Some folks also agreed that it looked moldy, especially with the some areas being more or less like white. It was compared to materials like cork and MDF most commonly. And then very similarly, oh, sorry, this is not a beeswax, this is the natural furniture polish. Similarly, folks like the visual texture that I presented and the color, especially as it related to that like sustainability kind of ethos. But again, it lacked a little bit of refinement, and the tactile texture tended to be negatively perceived by everyone. But again, it's getting a little bit closer to some more elevated materials like cork, but staying in that kind of uncanny valley of it's not quite a refined material and it's not quite a rough material. So overall, the coatings definitely altered folks' perception of the material and the product, some in negative ways, some in positive ways. But this tells me that more refinement is needed. Specifically, taking a closer look at texture, it can be definitely both an asset and an obstacle. So if it's something that's going to be textured, it's got to have a consistent texture and it's got to be pretty fine based on the responses. Otherwise, it should be completely smooth. So that kind of emphasizes some of the findings of the literature review saying that surface regularity is really critical. But as I mentioned, I also learned that scent should be a consideration in all of this, with folks really reacting positively to the beeswax. And also there were some notes, not necessarily about the coating itself, but of the fidelity of produced prototypes. So that emphasized the fact that the build quality of the object is inextricably linked to the material and the coating itself. So paying closer attention to the kind of holistic picture is really important here. But overall, this showed that continued like integrated efforts of coatings and treatments are key, but it did instill confidence in me that high fidelity mycelium-based composites for consumer product applications are possible with a little bit further refinement and effort. Hopefully you agree with me, but if not, I'd love to hear like any questions, comments, concerns, but that's it. Thank you.
In that regard. And it brings to mind the kind of history of plastics, that it wasn't going well, so to speak, in plastics until Italian designers started doing them, right? And so I think you might need some Italian designers. Here we go. We have yeah, but do you see what I'm saying?
Yeah,
right?
absolutely.
And it's just like that. It led style, and I think that's the interesting portion here is how do you now turn this into not having to catch up with style, perception, desirability, and everything like that, but how do you now lead with it in such a way that it creates that murmur. Yeah, I love the way that you put it, like the glimmer of it and the resolution. It's very important one.
Thank you. Yeah, curiously, just to that point, Italian design has been one of a big influence in my broader thesis looking at product design because of its kind of physical, like blocky forms. It lends itself pretty well to the mycelium's physical property. So I think that's a fantastic point. I'm glad you brought
And
it
the
up.
color.
Yeah.
Right? I mean, the color palette of, the Olivetti, for example, right? Yeah.
So I haven't thought about before and seeing this work many times now is actually, the possibility that actually you could kind of force more texture in or out of it, right? We've kind of been assuming the whole time that the material has to just do what it does, and you are only gonna give it color and finish. But actually, there's more to it. And I think talking about Italians is an interesting thing in the sense that, like, I think as American designers, we tend to like think that there's these rules we have to follow. These sort of, they're almost moral rules, of material and design. And I think that Italians are way more liberal about how they put two things. In general, Europeans in general are more liberal about bringing together vernaculars and aesthetics in ways that might, you know, in a way, it's not. I don't really think it's about camouflage. It's like when you isolate something too much, there's something unnatural, you know, no pun intended, in that action, right?
Yeah, that's a great point.
About some, whether you are considering, but the value is that the chicken some number of years ago was looking at replacing interiors of their cars with seats. But then like in the process, consumers were negatively responding to the smell. They wanted the new car smell, which is all VOC. And now I think Cadillac is looking at doing it, and I'm not sure what they're planning to do different. End up with a different result, but I guess that's great that people responded so positively to the results, and I was just curious also whether there was any negative response to any of the other either the uncoded or
Yeah, I didn't get any negative responses to the smell of the other materials. In the past, just in sharing other samples and showing folks the lab, people are a little bit off-put by the earthy smell of the material. Fortunately, the other treatments kind of mask that. And after a couple of weeks, the scent tends to dissipate from even like the uncoated materials. But yeah, that's I'm glad you brought that up about the new car smell and the whole other like dimension there is to explore. But yeah. Oops.
I actually have a question kind of jumping off what Jonas was talking about with texture. Do you have any more insight onto kind of what that process would be where since it's an organic material that you're growing, where you're almost going through an additive and then subtractive process, and how much room you have to work with it since you're essentially growing your product?
Yeah, that's a really good question. It is, like you said, very much an additive and then subtractive process, at least in the way it was applied to these materials. They're all produced via molding. And in this case, they weren't under any type of like compression or otherwise like densified treatments, which is another way you can kind of help mitigate the texture that appears, especially while drying. So having something that's like a little bit more compressed, you can get a little bit more of a smooth surface. But it is very much like gotta have your base form, and then from there with different treatments, you can subtract some of the texture away, but it is a pretty brittle and a precarious material. So a little bit more work is left to do in order to find like a true process like a truly subtractive process that's really effective at doing that.
It's a great presentation, really well put together. I'm curious, what do you feel is the next step for you in this kind of development?
So I'm currently working on a design and prototype of a stool. So I'm going maybe foolishly ambitious in terms of scale and application, but I think that it's to me it's all about like physical experimentation and like a whole lot of like tacit and tactile knowledge. The more that I've made, the more I learned that I didn't even expect to learn, and so I really think a lot of just really getting in and playing with the material in ways that maybe are very unexpected, or maybe some ways that are really expected, like comparing to other materials. But I think it's just about kind of building on what did work and trying to find like little ways to try new things while not completely abandoning like the lessons learned from past successes. Did that answer your question at all?
Yeah, this is great work. Thank you for the presentation. Really picking up on some of your other comments. One of the things that occurred to me was maybe that the prototype for the testing could in fact be even more neutral, like a super platonic object. And I wonder how that affects kind of the responses to it. The other question that I had was about the mycelium itself. Do you feel there are any innate properties of it that could lend to the finishing? Like, could there be such a thing as a mycelium patina or something like this? You know, I'm thinking about certain metals or woods that are valued for how they age, whether cedar grays or whether a certain bronze over time is even more valued because it takes on characteristics, and whether or not the mycelium could get you to an interesting place.
Yeah, that's a really great question. I'll go back to like an early slide with some of the examples. So generally, once a mycelium object is cured, it will stay mostly the same white. It might yellow slightly over time, but not super significantly. However, during like the growth process before curing the material, depending on some of its conditions and the way you mold it, there sometimes naturally occurs this like variation and like shift towards more of these like orangey hues and a little bit of a patchy material that from everything I've done and everything I've read, no one seems to know how to control that, but potentially like embracing it, I think could be a really viable route. Maybe it's just a little bit in contention with some of the kind of like mycophobic perceptions of the material, whether it suggests it's a little bit more of like a mold or not, but I think that is a really like important and viable route, is like embracing what it naturally tries to do.
I just have a few questions. So, for the mycelium you use, first of all, it's really nice work. I mean, the process itself is very scientific at the same time. With visual based kind of aesthetic beautiful. So you have really good balance between then for each layer of design one right curiosity is that this one type of mycelium. So my question is, if you change the type of it, or then actually it may have a totally different properties than this.
Yeah. So I did in this research use one species of mushroom. I used reishi mushrooms, Organoderma lucidum is the scientific name. Most mycelium is similarly white, but reishi is actually known for having like a really bright white mycelium. And there are some strains that are known to have slightly darker and greener hues, none that I've personally worked with. But there is a little bit of natural variation out there.
Then to get one of the research papers I have read was that it had a kind of like concrete light and kind of like still at the same time. It has kind of like air filter light on other end. How do you can the balance between many different kind of features and properties? How can you design the physical kind of the product related?
Yeah. So concrete is a pretty good analogy of a material. So mycelium is pretty brittle, but strong in compression. In terms of design, I think that it's a matter of material and function driven design to help both inform like the aesthetics and the material treatments used. So for example, in something that's a little bit more structural, considering things like densification of the material before it reaches its final form, I think is really important in mitigating some of those like risks of it being like a really like weak or material. But I also think that it's like kind of natural foamy, more lightweight. Form has an equal number of like applications. So maybe it's a question of marrying the two in one product, or just figuring out when and in what products to use each of the kind of forms. Did that answer your question?
Okay. Other questions? Okay, thank you very much. And now we are going to switch to Bill. While waiting, Neil is preparing his presentation. Neil Lucas Hitch is a designer and educator and curator for me. And then he's currently a visiting assistant professor at Carnegie Mellon. And also he was a visiting lecturer at Texas Tech. He has actually an MS degree in design at Cornell. That's a new department. Yes. New program. Yes. So you're kind of one of the first or second one. And he also MRP in Johnson University and also AA in London. Yes, for a semester, yes. Okay, that's great. So please welcome Neil. He will present about his amazing ramp Earth construction project. Please welcome him.
So, working. Thank you so much for the intro and thanks for inviting me here. I'm really happy to be here and to have the opportunity to share some of our work. So my name is Neil Lucas Hitch. My co-authors are Christina Fisher, who's also here, and our third partner is Martin Hitch. And our paper is titled Eroding Barriers, In Situ Testing and Geomimetic Design for Rammed Earth Construction. The paper details the design, testing, fabrication, and installation of the dining room, which is a public rammed earth pavilion built for the city of Bondurant, Iowa, as the first phase of a 6-part master plan we're designing for the city. The dining room consists of a series of intentionally distressed rammed earth walls made from locally sourced clay and sand that are then grafted with timber infrastructure, including a bench and a table, giving the appearance that they've been embedded within the rammed earth walls to frame this intimate public dining and picnic space. Here, the paper investigates the concept of erosion on two fronts. On the one hand, exploring the poetic distressing of rammed earth walls to sculpt architecture using geomimetic design principles. And on the other hand, developing a low-cost and fast alternative to laboratory-based compression testing in order to, metaphorically speaking, erode barriers of entry into rammed earth construction. So for a bit of background, biomimicry, as coined and described by Janine Benyus in her 1997 book of the same name. This is a widely researched and implemented design methodology in which biological processes and methodologies are mimicked to enhance both the quantitative and qualitative aspects of building. One ubiquitous example is of this type of design is the Gherkin in London, which, contrary to what its name suggests, was actually designed to mimic the structure and fluid dynamics of a sea sponge. Biomimicry has been both praised and pilloried since the release of Benyus's book, but ultimately has grown into a vibrant discourse between researchers, designers, and the public. Many academics have continued to develop and amend Benyus's ideas in subdisciplines such as biosynthesis, bioagency, and biophilia, which
in their own unique way, each attempt to conceive of a broader approach to nature-inspired design that emphasizes the principles, patterns, and organization of biological processes rather than focusing on direct mimicry. And while these endeavors have been and continue to be productive modes of inquiry, they still prioritize biology above other inanimate natural processes that more directly shape our landscape. So here we introduce and build on the concept of geomimicry. So that's art and architecture inspired by geological processes in order to expand the conversation surrounding nature-inspired design beyond biological systems to also include geological systems and geological processes. So we're specifically interested in processes of erosion, and even more specifically, we studied fluvial erosion, which describes a natural process of geological design characterized by the weathering of earth and rock, driven by kinetic and abrasive forces of flowing water, which gradually remove material to induce these morphological changes. It kind of works as a form of natural subtractive manufacturing, if you will. So taking inspiration from these natural geological processes, the dining room was conceived as a series of distressed rammed earth walls made from variable parts, sand, clay, silt, gravel, and cement, that were then intentionally eroded using moving water that was sprayed onto the walls post-ramming. So while biodesign attempts to provide a framework for sustainable design, prioritizing core tenets including adaptation, integrated growth, and resource efficiency. In architecture, these principles often manifest as modular yet disposable systems or efficient but expensive and extractive systems, often or sometimes producing externalities that may undermine the intended sustainability goals. Geological systems, by contrast, as seen in this diagram of the rock cycle, operate through long-term material flows, erosion, sedimentation, compaction, uplift, repeat. So this offers a model of circular material use in architecture where earth, for example, can be excavated, utilized, demolished, and reintegrated into the landscape without disrupting this cycle in an idealized situation. So here, while geomimetic systems may not match the conventionally assessed efficiency of something like a lightweight multi-layered system inspired by biology, they start, or the hope is that they can provide a kind of alternate efficiency that's rooted in material continuity, prioritizing recyclability and reusability over performance optimization. The economic logic underpinning biodesign, which maybe is encapsulated by Buckminster Fuller's maxim, how much does your building weigh? This presumes an industrial system dependent on large-scale extraction, processing, and transportation. However, when working with earth, an abundant material that can often be sourced directly from the building site, this logic collapses as transportation costs become negligible and industrial supply chains are supplanted by local material sources. So as described, there are numerous benefits to designing with geological timescales in mind. However, a kind of oxymoronic phenomenon has occurred with the advent of modern construction, design, and regulations and codes, which is that traditional building materials like earth have become hard to utilize actually because of their resistance to standardization. Unlike other materials such as concrete, timber, or steel, earth's structural performance isn't always uniform between applications. This is a diagram showing areas of high clay concentration in the United States. From an engineering perspective, earth really isn't even thought of as a singular material due to inconsistencies in composition between different locations. Each time the material is used, at least in the context of the United States, because we don't have a lot of earth manufacturers or regulations, the material always needs to be tested every time it's used. The most common method for evaluating the strength of rendered samples is laboratory-based testing, a process during which the earth is rammed into cylinders and compressed to failure using a universal testing machine, as pictured here. However, while this is accurate, it can take a long time to yield results, sometimes weeks or even months. If you typically, unless you're a professor and you have direct access to the lab, you have to send your samples somewhere, they have to do the tests. It takes a little while for them to get back to you, so it can take a little bit of time. And it is also expensive. Depending on how many samples you're trying to have tested, it could easily cost $1,000 or thousands of dollars. In contrast, the in situ method we developed for the dining room utilizes low cost, readily available materials, including a shovel, plastic bucket, a wooden dowel, plywood, and a 275-gallon capacity IBC tank. And actually, in our case, the cost of these materials was under $20 because we're trying to choose materials to set up this kind of low-tech rig that might be readily available at a construction site. So we were able to kind of borrow a lot of these materials actually for to set up our testing rig. So each of these materials can be set up into this rig, which can test the lower bound strength of rendered samples. Unlike lab testing, we're not testing the samples to failure. We're simply just trying to ensure that our samples meet the minimum strength threshold needed for a specific application. So the idea is to envision a low-tech method for testing rammed earth samples that has the potential to broaden access to rammed earth to constituents who don't have access to a laboratory. In the discipline, again, we kind of take for granted that we might have access to these facilities, but for the average builder, a universal testing machine might be difficult to access, and in that way become a barrier of entry to earth construction. So construction of the dining room began by sourcing soil from a nearby site in Newton, Iowa, located 28 miles away from our build sites. We then performed simple jar tests to assess the material composition of the collected soils. For the uninitiated, this just involves filling a jar with dirt and water and shaking it really hard and then letting the different layers kind of settle. And you can see roughly the composition of a given soil between the clay and silt and the sand. And following this, we developed 4 unique samples composed of these different soils we tested. We added gravel, and in order for us to receive permission from the city to do the projects, they required some small amounts of cement as well. So we then set up the in situ testing rig. Each of the samples is put under the 4 corners of this tank. The tank's then incrementally filled with water, and the samples are observed for any cracking. During our testing, we were able to fill the entire IBC tank with no observed damage to any of the samples, meaning that each of the samples could withstand an applied stress of at least 46 pounds per square inch, which is above the minimum performance threshold of 30 pounds per square inch that our structure was engineered to withstand. So it's not perfect for every use case. Obviously, if you need earth as kind of load-bearing wall, you might need to find another method, but at least in some use cases, for us, we were able to provide this data. And yeah, so I guess I could just say, even though all 4 of the samples theoretically could have worked, this last sample was chosen as optimal because of its low containment of organic matter. But we were able to share this data with the building department for the city of Bondurant and receive permits. So they that this data sufficed for the department. So we hope that it can be a kind of replicable system that might allow some people to use rammed earth who might not otherwise have been able to. The first step in actually constructing the pavilion was to pour foundations. We were collaborating with SVP engineers out of New York City to help design the project. So to create this connection, there's a series of hollow structural sections that run through the rammed earth and the concrete footing. And this transfers this overturning moment into a moment couple inside the earth to prevent it from falling. Okay, so next we built formwork using reusable concrete forming equipment that we rented. The earth was then moved into the walls in 13-inch increments and compressed using a combination of hand and pneumatic tampers into roughly 8-inch lifts. And then once completely filled and compacted, the formwork could be removed to reveal 2 solid rammed earth walls. At which point a standard pressure washer was used to gradually erode predetermined portions of the wall, generating these live eroded edges, gaps, and holes evocative of naturally occurring rock formations. We then used a combination of both 3D scanning tools, just simple photogrammetry, our phones, and traditional scribing techniques to record the eroded edges, transfer them onto wooden boards, and then cut out those contours with hand tools. And finally, graft those boards onto the walls. The result is this geomimetic installation exhibiting principles of fluvial erosion as found in natural rock formations, and literally harnessing the power of erosion to shape architectural space. So you can see a kind of detail shot of the dining room and how that's similar to the, this is Hole in the Rock in Arizona, which is a natural rock formation made by water erosion. Then these walls can be intersected by an oversized picnic table and bench to shape this public picnic and dining space. That appear to be embedded within the walls themselves, as if they've been slowly excavated out of the walls over millennia. So here the structure starts to exhibit numerous positive attributes typically credited only to biomimetic architecture. These include the implementation of fractal geometry, the use of natural materials, and the presence of areas for prospective refuge. Thus demonstrating the ability of geomimetic architecture to create comfortable spaces and increase human well-being, and as such, challenge the assumption that nature-derived design must adhere to biological models, trying to broaden the discourse to encompass the slower, recursive processes inherent to geology. Thank you, everybody.
I'm gonna pass this around just so that way everybody can hear the questions, so.
Really nice work. Just curious, did you do any analysis of, talk about the cement foundation and why it was needed, and was there any investigation of its footprint in every sense versus the walls and other elements?
Sure. Yeah, it's kind of, this isn't our first rammed earth project, but it was our first like public permanent rammed earth project. So there was a series of non-negotiables working with the city, but we were working with an interesting set of engineers. That's, I'm gonna skewer the name, but it's Schleit Bergman Partner. They're based in Stuttgart, but they have an office in New York City that we were working with. But we needed a concrete footing. Did I already pass it? We designed it. So, I mean, I wasn't an engineer, so just take it with a grain of salt. But my understanding is that this whole area of, basically we shrunk the footing to be as small as possible. And instead we're using a gravel bed surrounding the concrete foot so that we the idea was to just absolutely minimize the amount of concrete that had to be poured. And the footing is also unreinforced, so there's no steel in it. So the engineers, we were working with the sustainability lead, he's a co-author on the paper too, Dan Bergsegal. So we were working with them to try to, we couldn't eliminate all cement, but at least reduce the amount of cement that had to be utilized in the installation. You can correct me if I'm wrong for statements.
Thank you.
I'm finding this session's a kind of feast of different practices where testing and analysis, as well as application and sheer involvement in craft is compelling. And that produces a kind of disorientation for me in each session as well, in order to understand why might this be important, particular practice, particular cross-disciplinary analysis that may be offered here. In this case, I'm a bit disoriented, and so I asked a friendly question. We dwelt quite a bit on the bearing capacity. Why was that important?
Yeah, so, well, I guess the important thing is like, and you can tell me if I'm not answering your question, but like our engineers specified the kind of performance threshold that these walls needed to be able to withstand. So it's a kind of two-pronged research. One part is thinking about geomimetic design and it's kind of nature-inspired design, but the other part is thinking about methods of developing this kind of testing rig that will at least kind of prove that these samples can perform to the lower bound threshold specified by the engineer. So I guess the distinction there is just we're not testing them to failure. We don't fully know the maximum strength of these samples, but it was enough information for the city to give us permits without having to test the samples in the lab.
Yeah, that's a tantalizing response, and I'll give a friendly pejorative response to that, which is that implies to me that it was in order to get permission, not necessarily to use personal judgment about what was important. And of course, permission is important, but it sounds arbitrarily important compared to the actual application here, in which, at least temporarily, we need to have a yielding quality of being vulnerable to erosion. That was the trope, the simile that you chose, and then that need to be stable in the longer term. Neither of which refer to bearing capacity per se. Now, I think this is a feast of different terms of reference, but could you just reflect on the mixed syntax that perhaps you're using?
In terms of the kind of structural logic, or just between the two?
Well, I've just given you a friendly provocation, and it really is in friendship, the mixtures of different practices and the kind of bewildering numbers of expertise. Yeah.
Yeah.
Please, yeah. Maybe you need to be meaner so I understand.
No, I think that this is precisely where the dilemma lies, is the resistance that the material produces to exactitude and accuracy and standardization and so forth, whether that was the mycelium that didn't want to bind with the with the stuff, or whether that was the bamboo discussion earlier, and understanding a kind of material behavior that works that way. And I think that you outlined that. You said, look, this is something that wants to resist standardization on one hand. But on the other hand, the work that we have to do, and I think all of us are kind of incumbent on, to prove the material's viability in a very normative, conventional sense, and I think that what's interesting, I think that brings this to this
rig that you've made. What did you call it in the first slide of it? You had like one where, you know, you were like, you had a name for it in the first, very beginning, maybe second slide that you showed.
But in situ testing, right?
It had its name. It wasn't that one because that's Christina. Eroding barriers access.
Yes.
Materials. And it's like, whoa, you know, the fact that you have to do both of those at the same time makes material technology extra difficult, I think, you know, and yeah, that's where I see these two as linked.
Yeah.
Inextricably.
Yeah, thank you for answering the question.
Hey, I've got your back anytime.
Yeah, it's a kind of complicated thing we're trying to weave with the paper, which is to kind of, in one paper, talk about two disparate things we were interested in and doing. So that is where that's how the paper is kind of outlined, but I think I understand what you're asking too, or I mean, the initial proposal to the city was just like, let's build some rammed earth walls and slowly let them erode over time, or kind of start the erosion process and then let it continue over time. But just the reality of working with the city was that they needed some kind of stabilizer. There was a series of things they were concerned about. So, but yeah, I think what you're saying makes sense and probably has something, yeah, to do with the kind of tone I'm presenting it, because yeah, obviously, like we want to ensure that it does not fall down as well, but yeah, adding the cement was interesting in some ways too, because the thing that wouldn't have worked about like a concrete if there was some kind of liquid casting material is we just take off the walls and the concrete pours out, so it needs to be earth in some sense. It's important that the system is earth, but when we add cement as a stabilizer, once we take the formwork off, there was basically like a 3-window time period that we could erode the walls before they would harden enough that it would become too difficult to continue the erosion process. That's an interesting thing that I didn't really talk about that could be diagrammed.
Yeah, that's slow build, quick erosion.
Yes.
I think some of the messiness you're talking about, like, I think is really awesome. Like, we don't, you know, I don't think every project has to occupy any one logic. And sometimes like the answer is it was an experiment, right? Or was a, you know, series of experiments uncomfortably put together with a result that makes most sense. Not all sense, but most sense.
Got a question right here.
Sure, yes.
No, thank you for your presentation. I love brown earth. I also like made a research when I was in undergraduate about it, and it was more for residential. So peace in public space was shocking for me. I'm like, how you are this is very awesome. Like, I really appreciate that. But my question is more about during your research, what kind of code, like I don't know if you have to talk with the municipality or like how are those permissions when you have to design from earth like in public space, and like everything that you were proposing about eroding was an issue. I guess it was like, I don't know, like if that's a thing in which state will change. I don't know, like how do you find that information?
Yeah, well, I mean, the first thing is that in Iowa, there's no code surrounding. I think there's only one state in the United States that has codes. Maybe New Mexico has codes for rammed earth, but most states, the other 49 don't. So it's like, that's why we had to go to the city and kind of work with the engineer to like, the onus is basically on you to prove that the material will work. So yeah, there were no codes. This is the only rammed earth structure in Bondurant, and probably the rest of, maybe there's one rammed earth building that I could find in the state of Iowa. So yeah, there's not codes written. It's interesting that we were just presenting this project in Germany at a conference for rammed earth, and it functions so differently there, and they have really robust codes that they've just written for earth. And actually, they were telling us that in Germany, if you have any cement, it's no longer even considered rammed earth, which is so it's not even the same material. But yeah, we're kind of in our infancy, I guess, here, like working with these materials.
So there's no code for public space, like. That was my question, more like about public space, not just like rock.
Yeah, do you have any, the other thing is our client was the city, so we kind of had a shortcut to getting permission to do it. I mean, the honest truth is that this town is so small that I don't think they even had a process for permitting art projects really. So it really was all kind of, yeah, just based on if they looked at the drawings and. Yes.
And you may have covered this, but too much in my mind. Did you draw the subtraction in the construction document? And to what level of accuracy did you intend to meet?
Like here?
Yeah, and look, you showed in your representations, but I assume they asked for CDs.
Yes, yeah.
So was it in the CDs, and how? And how did you try to approximate it, or it was much more of a sculptural?
It was an approximation because obviously the CDs were submitted before we eroded the walls. So
no, but in other words, like, you could do it as an intentional fabrication, or one that's much more improvisational. It seems like it was somewhere in between, but
yes,
I wonder.
A combination of both. So we had them drawn kind of very loosely in the documents we submitted to the city, but you can kind of see. Maybe in these pictures of like here you can see we like intentionally lowered some of these bars. So this was like where we planned to have these like rough shapes eroded out.
But like, was it maybe a 6-inch tolerance would have been your intention, or were the 1-inch tolerance?
What was there? I mean, it wasn't that specified. We had some constraints, which was we were trying not to get within a foot of any of the steel poles themselves. So there was a kind of perimeter around these steel poles that we were trying to avoid. But beyond that, we did kind of want it to be improvisational. Yeah. So I mean, we had a small team there, and you can see we were kind of just like, eroding, taking a step back, looking at it, repeat process. Do you want to add anything?
It's a very sculptural process when we actually did it, and we just marked the minimum we could go. Where was that foot kind of offset? But for the construction documents, we did draw the approximation of the erosion. So that was evident, and they knew that was coming. There was a shock.
This reminds me of a series of artworks that happened in the 80s by Richard Brown. They're called earth clocks that were rammed earth that was intentionally eroded over time. And I wonder, is there, I know it's fixed by the concrete, but is there a time period that you imagine erosion will continue, or is this considered a permanent installation, or is it something that you're expecting changes to happen?
Yes, I mean, that's like in our initial proposal, it was this continued cycle of eroding. The city was, I don't know, like we weren't referencing that artist specifically, but we were referencing a lot of land art. And there's a big controversy with the Mary Miss project, who is a land artist in Iowa right now. So the city was hyper concerned with durability. The kind of compromise was that we placed cement caps and took some extra measures of some kind of, I guess you can't see it great anywhere, but you can kind of see the caps of the walls have this cement on top. So the thought is that hopefully those areas of cement or water won't be able to penetrate into the top of them, so they'll erode less. And then these areas that are open that we've already started to erode will be the primary area that continues to erode over time. So that's the idea.
How was the decline work? How was the decline work?
Yeah.
fun.
I was wondering if at all you considered not that this would be like the appropriate method, but if you considered actually integrating the benches in the like formwork and manufacturing, like construction of the walls. I imagine it would require some pretty complex formwork if it would even be possible. I was wondering if you considered it at all.
Yeah, like embedding them in the walls and then eroding them out, literally. It was considered, but there's fears that they rot if this, and especially I think in the stabilized wall, if you add cements, the fear is that the wood will start to rot. Yeah, ramming around then makes it difficult. Yeah, thank you everybody for all the questions.
Sorry, one more question. To me, it is the most challenging project. It's a beautiful one. Material itself,
Can you speak up? I'm sorry.
this material itself is a really important step. My question is that your previous institute method about measuring the strength of the samples, hypothetically, if you reduce the size of, the diameter and the height into half, then actually do you only need the quarter of the water instead of 1 meter by 1 meter by 1 meter cube?
Yeah, we write a little bit about that in the paper, that one option, because like right now we can only test this, like we're trying to think how to test them to a higher bar. So the idea was we could reduce the diameter of the samples and then the minimum threshold that we can test would double. So or to like fill the tank with something other than water that might be more heavy, etc. But it's so that's kind of what we're thinking now, like how can we increase the amount we can test or the size of the load. Yeah.
And in my mind, that kind of requires at least one round of lab testing so you can create the baselines, right? So
yes, that was
once you had those scales, then it would be easy because you're testing at a scale that's relative to concrete too, right?
Yes. Yeah.
So once you change that, then there's no reference anymore. So you have to build a new reference, right?
Yes. Well, we just wrote about a kind of different aspect of this for a conference in Germany, and this was like the primary. Somebody said that, and we said what we said, and then somebody gave us comments that was that. So yes, this is like the
it's coming.
Yeah, thank you very much.
This orientation is partially my bad, so I should give you a coffee break for this presentation. So let's have a coffee break, and maybe 10 minutes later, I will start my presentation. Thank you very much. I was so immersed over your presentations. I totally forgot about that. I should offer coffee break. But again, thank you very much for your amazing presentation.
No, we're not. No, we were connected through this organization to the city. It's basically an invited competition to design a master plan for the sport.
Yeah. Also, I just wanted to thank you for bearing with the heat. They don't turn on the AC till next week.
We met somebody who is from the city and who started this like nonprofit, basically inviting artists to these cities. We met in the element.
What are they ordering? Right. So
What's your name? Jonas. Yes, Jonas. Nice to meet you. I go by Lucas, but my email will be Neil.
Yeah, I'll forward it on. Very, very.
My phone said, but don't forget it. I was gonna put it in my. We might do
Sure, yeah. As long as one of you will. Like,
I got it, those nice days. I was wondering if there's a similar, like, issues with bamboo or how bamboo. Like, how do you get through?
I would think about it. There are, how weird it is. Code idea. And Latin America, there's no different. Four of them. Or last two around them, not quite fine. But it's the same thing. Take an approach where you really are another standard. I think it makes sense to stay with us for a while because all the, it's not only the acceptance of the results and the familiarity, all the testing machines are set up to test those samples. Anywhere in the world, you find four testing machines. Any civil engineering, anywhere in the world. It's like it would be any easier. We're doing some parts. There's nobody wanting to test them. Everybody's like, well, we're doing things here right now. And they're like, well, what do you compare it to? What machine? What standard? But doing core sample compression testing. It's immense.
It also has your reference.
Yeah, you again, once you have the method, I think I agree, like finding like a way to fuse or scale a hydraulic press with things like a planing scale, for example. And Harry's is really good at that stuff too, like not building it, but a map.
We actually talked to a lab in Des Moines to try to get them to let us test our samples there. And they can really use this for concrete. And they were like, oh, we're doing ram dirt. What? And they started, I called them several times and they stopped talking. They stopped returning my calls. They were just like, it just confuses them so much.
Sometimes what you need to do is first, like, you know, like, I don't talk about this work in bamboo and bamboo. Sometimes I don't talk about, you know, a low embodied energy, so indigenous, bio fortified material, something like that, right? So what you're doing is it's like a low concrete masonry unit. It's in fact like that. For the engineer, that's helpful to. Because they don't feel like you're in left field, they don't know how they answer the questions. So you bring them to that body of knowledge they have. Oh, well, it is different, but it will just be less impression.
Yeah.
You know, sometimes they're like, well, where do I start? Just break the fucking thing. That's what
Just break
force it.
But I do think there's this litigious problem in our society where like that engineer now has their name attached to that text.
Yeah. But it's not only in our country, it's in every country. Like even in engineers are mostly trained with a very similar kind of mindset, right? So even in Latin America, the response, you know, you find like 1 in 50. I mean, we all know that. Like, it's difficult to find engineers that are not like, even the ones that you think are risk averse, as soon as you tell them you think are risk averse, they're like, no, I'm not.
Well, safety factor 25.
Right.
On the other point, it's interesting that going to a hardware store or whatever, I never tell them what I'm actually trying to do.
Right.
Sorry, no, I can't. Instead, I'm making some shelves.
Comments, because I went through this presentation, incredibly experience as I did in the previous one. So, not because I was in school, just the situation that we're in. One area of starting to create value with very responsibility.
mean, first, one of the reasons why I would say student is that I think there is something happening in each of these presentations as well. We're going through this forlorn process of making a releasing enormously labor intensive presentations at beautiful graphics, which might be all followed if it's the wrong form. Which I think is, but still, it's not. It's in fact, if you got the old sheen, it was like standing. So my first comment is just think like this. It's important for us to stay obviously your face and own it and very, very rather than to do that. I'm very interested because it's interdisciplinary practice is really challenging. It's guaranteed that every single person in the room is so, welcome to our tribe as opposed to feeling like you're but that means you have to prepare yourself and make yourself really work on self-esteem. At least, I'm speaking personally, because I'm so very often embarrassed about large scale responsible or it's at work. And the defensiveness, the aggressive defensiveness from authority is really, really challenging. But then I do think at the same time there is something about the need to learn the rhetorical practice and meta-legal practice as well as jumping into the expertise that pulls us into the kind of deterministic act, which is very time consuming and very disorienting if it turns out that it is the wrong form, which it will be sometimes. And by rhetoric, I mean like just like really fundamental practice of what, why is it important? What justifies this? What warrants that? What's the qualification of that warrant? That's possibly copy, but it's graduate students should be taking that kind of coursework in order to learn that thesis, and if they aren't, then they should. And it's really incredibly valuable for that knowledge creation, authorization, responsibility, reliability assessment process to be part of it. That if it's not handled, if it's not controlled very explicitly as kind of like the general conditions before you jump into the specification, like it's the general part of the spec which says this is the spec that I should use. Here's how to read it, and now here's the content. That kind of thing. If that doesn't happen, then I think it's really risky to jump into.
Probably would help one fellow that said,
even more dangerous.
We asked the why question and they couldn't answer
It's not a thing anymore. I mean, it's part of the practice. It's guaranteed to be happening when we are innovating.
So I also think you don't have to have like I think the name of this book, but I read it many years ago. Book on this research in China where there's mice or it was mice. And they're basically just running random experiments, right? With the goal of discovering what you should be researching. And so we have a very singular linear lens. I don't care if we're using, design thinking or other kinds of models of regional thinking. We have a very linear approach. In kind of American mindset.
So like
sometimes
leaning into the naive.
Well, I wouldn't even think you're naive about what your goals are. You may not be naive about like the general subject, right? Sure. But in other words, the suspension of actually having a particular agenda other than just to observe.
Wait to form a thesis.
Right. And I would say that like sometimes your instincts are right, but along the way, you make some steps that's probably unnecessary. But that's how you figure out what you're refining in the first place. In my mind, like the model and design so often, even when we do embark on materiality, is different than the mindset of art. And if you look at I'll go back to the bike as an example. Halfie, the guy that designed the carbon fiber bikes, is a sculptor, right? It's so common. It's somewhere in the training. even if they've turned into a designer, someone has an artistic training, they don't get hung up in these things quite as easily. And that's why they have the fortitude to go so far. So in other words, if you're too linear, if you question yourself too much, you feel like, oh, I'm an imposter. No, I'm an artist, right? That freedom to not have to have it make sense longer, I think, is part of how we make discovery. But maybe we don't spend enough time in that territory.
But I think that's fundamental to the academy. I mean, that's the idea, is to like research something that maybe is meaningless. At first. It doesn't, you don't know. You kind of, so you don't exactly know why. I mean, it's actually one of the frustrations, particularly in the art and architecture world, is where, applying for a big grant of like $5,000, and I go over to arts and sciences, like, oh, I got $3 million to look at these Mars rocks. And you're like, I'm trying to apply something that might actually have like sustainability or like human, and you're looking at Mars rocks, and your budget is like much bigger.
Well, you got to go to space, man.
And so sometimes, I'm sure there's some benefit, but then there's that ability to investigate something that doesn't necessarily have a solid foundation. And then as you discover,
I'm really scared about this. Sorry.
No,
I'm quite fearful about you saying meaningless though, because I think that makes us a silly. That's a recipe for just point blank rejection. But I do think that there's a class of problems which are ambiguous, and I think ambivalence and wicked problems will really need to be spread into much more of a spectrum where we have a toolbox for it. That's for sure.
Yeah.
We have plenty of time.
Oh yeah.
Which sense? In the music world, you needed to be soft for a while you were in the remote, and then it needed to be hard and impervious. Whether resistant after that, and that might have been a better test for public benefit, of art officials, rather than bearing capacity, which to my mind is irrelevant, given that you aren't bearing.
If I said
People might climb on it. I think that's
safety. I mean, that's the old, we used to call it the 50 biker test.
Yeah, no,
50 bikers are going to push a thing. Which is like vandalism.
I'm being specific about bearing. I mean, it's not irrelevant.
I don't know if I said, maybe I said bearing on the podium, but in the paper, our engineer said, like, I could try to say the strength of the wall. In opposition for the bearing.
I'm not happy about the test you used anymore, because that was just classical equilibrium-based bearing, which would not yield the results that we need in this application, which is a whole turning and actually tensile component to the thing, which is quite different. And, it's a more complex, this free wall, which we use in hurricane practice, jumping on with parkour and so on, is that's a more complex animal than straight brush. Wrong test, but I respect it. That's the one they wanted. It's like a quality to do it.
There are additional tests that of pushing the wall too, and the whole engineering of that bar was for this force, and definitely that was part of the engineering process as well. We did it
by this way, and so that would be very different than a core which then resists.
I think also just to the point of like working with cities, they understand weight. They understand there's certain things about like that as like a kind of almost, we knew these walls were gonna be fine, but we just kind of had to like almost calm their nerves through the permitting process. And so like understanding like that as like, oh, I can understand that the kids that are gonna climb on this is gonna be okay. And so like if there's certain tests that like are more of appeasing the client you're working with or the city, just like within the unfamiliarity of this, the building.
A lot of conversations talking about posing as engineers. Another one that really excited was the project is like this row testing that was done. So I think is like so valid, but it doesn't confine to the lab experiment, which I think like being able to quantify the level in a certain sense is really get this push out. Probably one of the more valuable parts of the project, in my opinion.
Yeah, going through the fire. Yeah, like the amount it needs to withstand its insane.
We were working with this, had done a workshop with this random builder down in Arizona. And he constantly sends his soil samples to a lab and they constantly perform as well as just a cement wall one. So he kind of reassures like it would meet that. But it's funny that we have to that is what we have to live on too, is these kind of unrealistic measures. And so I feel like we were trying to and what we were able to achieve was passing something through where it's not meeting the unrealistic way, but it's meeting what actually is necessary for the use case.
That's what kind of fascinating, not just the solving the technical problem, it's like solving the arbitrary permission problem and taking it from an artist's point of view. Like, okay, this test would cost thousands of dollars. Well, it's basically just pushing something weight. Let's just fill a water tank. That's what you push. I mean, I think you're actually just taking another aspect of the problem. So approach something.
Yeah, exactly.
And relatively arbitrary.
What about your slides?
Oh, no, there's no rocket or
workshop.
I was like,
My phone and
oh, and then I called it back. He was like, oh, hang on. I ended up playing that.
I go by Lucas, but my email is
yesterday, like 3 started, I was talking. It's the more things that I'm able to. Guys are probably.
The guy with the big beard. Probably should find out the woman who was but he would be the chair or
The common thing about
So we forget also that.
You're in the art department? I wish I was in the art department. Oh, yeah.
Yeah, we have our architectural here, but mostly just.
There are, well, I wrote that book 12.
So that one was basically, it was small enough to go as. Small enough to consider, no, it's considered shame.
They're not meant to. You have to be really.
There's a
Yeah. So, yeah, and I'm curious as to what you were saying.
How they
The phrase.
enable people to process and
But it makes sense to me.
You know the architects chat.
I think that
Sort of like chat on. They had a project built out of bamboo last year.
those are the authorities.
They're in the pilot.
Oh,
But it's like it's a bamboo pavilion on the water. It's got like red, like
it's in Thailand.
Yeah. But I have a friend that's that country in Thailand who's trying to build something in Pittsburgh based on bamboo and has gone through like how
Yes.
trying to get permission to do it.
Yeah.
And this guy came and gave a lecture. My friend asked him, like, how do you build like
Yeah.
and the chat was like, you just say like, why are you trying to get permits? That's never gonna happen. Just build it.
And that's the how much research and location for
Now.
Right.
And so that's what it seems to be. In a lot of ways, we're past we're dealing with it's not thousands of humans of humans. Right. It's like, oh, no, it's possible. It's a history. Long traditions.
And actually, network leads us to.
Rexburg needs a lot of maintenance, and I think that's where this weird disconnect is too, that the city just wants to put this here and never touch it. But a lot of these things actually require some kind of regular maintenance. I don't know.
Many people, but even still.
To a degree, quite honestly, even
Yeah, that's true.
this is one of the things.
Yeah, not.
There's a new here in Timberlake building. In the front doors alone. Have $10,000 a year. Like buildings. And this idea of building is actually just like fully.
So they slow down.
Those are not building have it done. Like, okay,
But this long, all of them.
18-inch concrete.
Right.
And even then,
And then if you
because so I noticed this that I've heard
still utilizing their.
come on, everything is sure that Washington. It's often not really discussed.
So
As we know, our maintenance rate.
But I kind of felt that technology, kind of like
I'm kind of a little bamboo.
Oh, yeah.
Are you not?
Are you trying to consider bamboo?
Okay, that's fine.
So.
But so it's great direction. So that artists are for possession. So how is like here, I was the one. Okay, another 2 hours.
And then once you have
so I like that. I love it's a.
So.
I mean, we're doing this in like
You have no.
peak July, like it's 90 degrees every day in the sun.
Compared to you.
So
Who can
we never does it. We have to like,
and if you. It's our.
When we did it in Hungary, we didn't even have it.
And then it's.
Yeah, that's why I did a lot of.
Yeah.
Sometimes they ask, you can come after me. I was on. Yeah, that was. Very proud. And I actually really enjoyed
I'm gonna find Philip later and ask him. Oh, I want to ask him like point blank what.
They use the word berry instead of
It seems like good, but over something that basically it's not really about.
I don't think like that's just. Like this is a real project I have to do.
I don't know 1 hour. We had a very similar conversation. About
How about
another project that was on about the kind of design. So, I'm excited. Well, he's giving a.
Okay, I think we're gonna get back going again. So you come sit down, that would be wonderful.
I think that's why they were French.
Oh, yeah, okay, yeah. I mean, it's several degrees of separation from biology. I don't even know who the new professor was. That is so back in time.
I didn't know that we're going to.
Oh, okay.
But yeah, it was a good competition. Like the winning team, this role the winning team, and members based off their
Anxiety. Washed out of rewind.
So
I can talk about it next. Things that way is learning. I'm gonna be like it was really clear, but I could tell like I knew how much went into it at the same time.
It's just like.
It's like
It's just,
yeah.
Makes me feel a lot better.
Max, you're 60 something. You're not how bad it is. Yeah.
Yeah, yeah. I'll get a little butter. Yeah, me too. It's very interesting.
So I had like so many of these things, progress and student aid. Just like
Yeah.
it is. I was like, okay.
Yes. No one. Soon. Yeah.
But I think we're gonna go ahead and get started again.
Yeah.
Yeah, great. I do not urge everybody to sit with plenty of time. So I can look at it. I'm just and this is really way more comfortable for me compared to last night. Because and actually I have a presentation until last night, just the presentations in the morning, like very linear. I have a clear problem, I have a clear method, and I have a clear vision. And actually yesterday's keynote, which was really inspiring, particularly at the end of it, there was one question that how do you get all these amazing ideas, and then how do you get those from both forms? And particularly the kind of the red screen with radical, it was so visually strong. And then actually her answer was iterate 150 times, 160 times, she said. So right after watching yesterday's keynote, I changed everything. So I couldn't say goodbye to Daniel. Okay, oh, my presentation problem, I have to update it. So I changed that. So I started from the memorable words from last person, disagree. So I always struggle with. It's interestingly, so my academic background originally in engineering, so I'm supposed to have linear orientation. But surprisingly, when I come to the United States, actually, all my education was contradicting to that. But all you guys talk about linear, kind of like clear goals, and so kind of like I'm still struggling at what I have learned in American education system is the feel free, meandering. Actually, the first chapter, the first book I read once I came into the United States was Louis Gattari's The South of the Country. Then actually, the first keyword was rise. You're no riser. Actually, that riser was mentioned. So this orientation, come back to this orientation. So I mean that where's Neil? Oh yeah, in this presentation, in my view, is really an actually bottom-up approach. So it's actually material research is really kind of bottom-up approach because it's not about solving problems, it's rather about what we can do with the material. So definitely it cannot be a glass box approach, it's rather about black box approach. So we change inputs, we change output, and so kind of identify what's the kind of pattern between those outputs, and then kind of find achieve what we want to do. So actually, so go back to orientation and clearly identifying problems to pollution. Because actually, we still live in Socrates' Cartesian, but rather I want to introduce actually at this moment something that I change everything. So kind of like Kant's actually Kantian word, which is not in absolute word. Then actually I switch our gears to relative. So doesn't receive that. So my presentation is not about identifying problem, which is engineering thinking, rather design thinking, which is designing the question itself. So you probably many of you already read about this horizon chapter in Guattari's book. So he mentioned that there's no end. It's all about connections, multiplicity, and kind of like those kind of things. And actually, that's about my research. So actually, this is my favorite thing to show to my design students, not my engineering students. I have both design and engineering. So there are kind of like disconnected bacterial seeds, but actually when they grow it, they influence each other. And then actually another one grows, and then actually influence going back. It's kind of like a simultaneously move back and forth. And actually that's what the ecological system is actually the research that I had before. But actually I removed all some financial things unnecessary. So I'm going back to, I'm glad that some of you are not familiar with Bruno Latour's natural theory. So I just kind of reintroduced that. So he mentioned about, so in the United States, actually half the population agree about using gun. Half the population. Actually, I offered this lecture to Apple, but then actually Apple kind of banned from to please do not use any guns and bombs in the lecture. But this is not actually Apple's lecture, so I'm reusing. So and then actually so what happened is that those who can carry gun, those who have access to a gun and can use a gun, compared to those people who cannot. Actually, if I over exaggerated, those who can carry a gun is kind of a little bit different species or different type of people, because they are capable of killing other people, and actually that's really extraordinary power. And actually, the use of AI, or can you imagine that you can walk to New York or you can walk to Virginia? You never thought about it, right? Because you know that you should take advantage of technology and must go there. Otherwise, it doesn't make sense. So kind of we are actually now become highly familiar with take advantage of technology and being transferred or transformed from. And then actually Bruno called it mediated situation. So so kind of my research in overall, going back to the previous bacterial thing, kind of how to get mediated situation or different research. So kind of in the end, actually the last project that I want to explain is actually my latest grant, that the project that I got a grant from Korean government that about in situ 3D printing on the moon. But I mean, moon project, the more I do, it's all about imagination. There's no data about their land, there's no data about their territory, so it's supposed to be work with my vision and my belief that it's supposed to be like that. And actually all this kind of my belief or my insight came from all those different kind of projects. And actually that I will show you a lot of projects. And seemingly they are not related, but at the end, what I'm saying, what I want to try to say is that I'm a kind of like convergentist, which is kind of connecting a lot of different dots. And then that kind of creating hybrid, actually that become my space research. So first one, so kind of several years back, I developed a cable robotic micro smart farm project from a company nearby my university. So the general approach about smart farms that make a really huge one, and then so make the price really down. to make it competitive. But I don't really agree about this one. So, I mean, yeah, I'm always sure that many of you have like a mini coffee machine at home. Like it's just, even now these days it's $50. But the first commercial coffee machine called we have Italian. And the price about $7,000 was almost like the cost of a house. So meaning that the cost, the machines cost almost equal to the house now becomes just your lunch or your nice dinner, the cost of nice dinner. So what we developed was how can we make the micro smartphone using kind of AI technology. So what I have researched is actually computer vision algorithm. So I kind of thought about, can we monitor leaf by leaf condition, and can we offer nutrients or water or kind of like mass customized way of raising those vegetation. And actually I made one. So this one was actually, so I had an interview with one of Korea's major broadcasting systems showing that a camera is monitoring each leaf and the water that can be provided to them. Okay. Okay, and then the second project is actually so that one is called a gantry system, which basically you probably all know about from CNC or 3D printing. So the kind of one of the weakest point of a gantry system is that gantry system is supposed to be bigger than the object that it can control. So basically, if you want a 3D print house, you need a bigger gantry system to build the house. Otherwise, you can actually modularly produce them and you can assemble them later. But it doesn't really make sense. So later, I kind of switched to cable-driven robotic system with another computer vision that this one actually read the vector difference of each leaf and actually detect the moment of that it needs any nutrients or water. So actually this system actually detect with using simply two cables and two servo motors, it actually kind of move around all the glass work and actually can offer water. And then next one is actually a robotic construction technology development project. I got some grant about this one. So actually I start to research about robotics, and probably you all know this kind of things. Lately, you see a lot of them. So using industrial and generative robotic paths, and actually you can actually carve out plywood or MDF or solid wood. So actually, this was the result. Then actually I switched to another robotic system. So you probably kind of see. Probably see a lot of kind of this kind of robotic, wood work. And then actually this is the result of it. And then actually if you design any kind of surface, actually this robotic system can build robotic wood. Or actually I kind of supposed to using a brick, but brick is too heavy, so I kind of can make it lightweight. And this one is another robotic woodwork that robot built it. So I kind of thought about what robot can do that humans cannot. So this one is actually sinusoidal gap between each wood. So actually, it's that humans are great to make a repetitive work, but actually, if all kind of gaps are different, that really human can do. But then I said only robot can do that kind of project. So we have some lighting. Then I kind of continued this kind of robotic construction into actually 3D printing client. But actually the great thing is that I developed from scratch. So I didn't use any Rhino or whatever. I just built from scratch everything. So that's kind of beautiful part here. And then later, unfortunately, you have a really United States with great culture about making it, but Korea we don't. So recently, kind of like about 5-6 years ago, Korean government started to build a makerspace. So actually, I got a grant to build makerspace in my university. So to my president, I have to convince him to. I got a grant, but I don't have a space. I didn't have a space, so I presented to the president of my university. What we need for next generation is not using 3D printers or laser cutting. We need to educate them to build 3D printers, to build robotics, and build kind of make tools that make another object. So actually, that my strategy was quite successful. So he gave me a lot of space. So actually, so this is the first stage of makerspace I got for my university. So then I kind of used my first budget here. This is kind of like a crude way of making makerspace. Then later, I got another project called Robotic Food Tech R&D Center from municipality. So actually, for this project, I got 20 for the last 2 years. I got 23 patents, 12 journal papers. So so kind of like with kind of this environment is actually like this. So we have over roughly about 30, more than 35 robot arms, all kinds of different types of robot arms from all different kinds of manufacturers. So this, and then later that actually I can start some making based project here. This is the kind of like right here. So and then part of it is actually food technology, robotics. So I have a soup making robot and frying robot and kind of, or kind of ice cream robot and stuff. And actually this one is actually defect copy being remover. And this one is actually using industrial robot. And this one's 100 times faster than collaborative robot. And actually, this is my robot kitchen, frying robot, hamburger robot, and fish cooking robot. Then I got another project called Dream Tree. This one, the name is itself was given by Pohang City. I have no right to change that. So this one is actually education center using robot arms. So actually, this is my proposal to the city. So there was actually 3 robot arms on the track. So that can actually make a drop coffee. There are another 6, and actually at the beginning there's this study area, but later and I add another 6 small robot arms for. This is kind of like abandoned, kind of like a ghetto in Pohang. So actually the problem is that both parents need to work, so they don't really care about their children, whether they playing or they just don't care. So we want to invite them to this education center, so children can run robotics and computer programming there, and their parents can get a free robot dropped coffee. So and then actually this is my but actually we have a lot of issues with constructors and robotic engineers. Very interestingly, they never know each other. They're supposed to work together to build this robotic system in interior, but surprisingly, they don't talk to each other. So I have to kind of to be a middleman to talk with robotic engineers and kind of carpenters and interior architects. So this is the result. So finally, we made it, and actually very recently we opened it. So kind of children actually run from there and volunteering undergrads to teach computer programming to children. So this is the result of it. Another interesting thing is that this one offers roughly about 360 different coffee beans. So it is almost impossible for human being or human labor to roast 360 different coffee beans and also handling those of that. And even we actually offer different kind of mixture of different types of coffee beans from Arabica to Java to African or with South America. So we built another robotic system that actually mix all the coffee beans together instead of human beings. So that just generate all the different combinations of it, and then we collect data that how much portion of aromatic components such as cherry or almond or chocolate. And then actually we also develop a robot arm system to actually roast almost like soup or kind of one person size roasting system. And actually it's interesting that this is the website that the visitor ordered. So there is no Americano or sorry for Italian. There's no espresso. What you do is you design your flavor. So you design your blueberry, the major character. Then actually the second option is how much do you want a blueberry and how much do you want to add caramelized or honey? Then actually we offer exact proportion of that flavor. And then actually we ask them to make it. So it's very interesting thing happen. So normally if you're not coffee experts, then actually you cannot really feel those aromas. So actually once you just order Americano, then you just something something tasty. But once you order it, I order 20% of cherry, 40% of almond, and 20% of it, then you start to recognize that because you ordered. Yeah. Whether it's true or not, it doesn't really matter, but you start to recognize that you ordered. And then actually you name it. And actually our business model is that there's no other company who can order like that. So actually they have to order from us. Okay, so that's the. And then I got another project with deep learning based culinary robots development. Yeah, normally when I offer a lecture, I introduce myself architect, but here today in our school of architecture, I have to say I'm not an architect. As you see here, I'm just a technology designer. So in this project, something amazing thing is that my team envisioned that all the labor-based system will have no end. Because I don't know, I mean, the physical laboring, we have to, but does it really we must have to do for our living? I don't know. So, but actually robotic system is very expensive to develop for each application. I mean, each application, what I mean by each application means that whatever the shape or element would change like by 1 millimeter, we have to redevelop each robotic system. So that was kind of like, I thought, the biggest or highest hurdle that I thought about. So instead of that, we proposed that what if anybody can teach robot arm who doesn't know anything about program or robotics can teach robot arm if we can transfer human experience and human knowledge to robot arm and the robot can replace human. I mean, I know some people are worried about that it will replace our human labor, but the first target is those target area will be the area that we don't want to work, something dangerous area or something very hot or humid, those kind of things. So actually, this is one of our first prototypes. So my researcher is teaching this robot how to cook tofu, one of the easiest food. So, and we call this one as constructivist approach of robotic training. Because many robotic research try to imitate what humans do that robot can do. So that's the kind of all the difficulty came from. That's what I thought. But when a human being teach robot arm, it's kind of like the same thing happened that an instructor, a grown-up instructor, teach children. And actually, if a person is smart instructor, he changed the way he teach depending on the student level of his development. So kind of like, and then actually, while my researcher repeating her teaching to robot arm, actually, she gained a kind of insight how to teach a robot arm do what humans do. And then actually this one was highly successful. And this one is showing robot arm without any training. So actually there's a kind of deep learning involved of it. So actually this robotic cutting is very different from human cutting because human teaches different way of a robot do cutting instead of human being. So I don't know whether you realize it, since there is no second hand to hold the tofu, so actually it kind of have more coming back and forth to have a nice cutting, but maintain the material staying on this position. And actually for the next 4 years, I have to develop 12 other cooking robots. So there are many, so that's kind of what I do. So I think this was really a game changer. Once we successfully made a platform that any human being can teach robot arm as he teaches human novice people, then my team believes that a radical game, it could be a radical, it technically can be a radical game. If I exaggerate it. So I got another project, alternative meat 3D printing. So yes, we are repeatedly. So at first time we developed clay 3D printing. Now it's we 3D print meat. So this one is one of the examples. So interestingly, actually, one of the interesting part is that the meat, the red one is actually protein. The white yellow one is actually fat. So this one can design exactly what you want.
So actually, if you want, so we actually use LLM, and then actually the user type and describe what kind of meat they want. So hey, I want to try a wagyu like blending of fat and meat, it generates. And then if children want to eat it, then I like a kind of like a character of dog or character, and then actually you can create. So it kind of like so this one, so the problem is that alternative meat is kind of like tastes really bad. So kind of like we are actually kind of trying to make this the shape of the alternative meat to satisfy any kind of like customer's desire. So all these projects actually come back to the space program because we have to do a lot of different material thing, and all those kind of technologies we tested from the last project become the source of our project for the institutes really thinking. So this one is actually a long time ago, about 6 years ago. There was a kind of bicentennial competition from NASA. So actually we applied it. So this is just kind of like this little bit faster presentation of the proposal we submitted to NASA. So at the time we use a laser printering and 3D printing using dust and then actually other technique. And actually very luckily, because I'm not a citizen of the United States, I have to write that I will give them any grants for NASA for that. Anyway, I will apply. But luckily, I was selected one of 12 teams to submit secondary material. And actually, this one is actually mine. So actually, the competition's requirements were that designing some habitat that 4 astronauts can stay and do some research. But our proposal is rather than how can we rebuild a kind of colony for human civilization, kind of a foundation of human civilization at the end of it. So actually, that's the beginning of my proposal for 3D printing on the moon. Actually, if you want to send 1 pound to the moon, actually it will cost roughly about $10,000 US. Imagine a robot arm which is roughly about 200 kilograms. The cost is, you can multiply that. So kind of we thought from scratch that how can we do if you build a building on the moon, what we should do then actually I thought that I should restart from everything, from the construction method, sending method, everything. So our proposal actually, and previously my team had a project with NASA developing tensegrity robotics. This is actually my students developed 4 different kind of tensegrity and actually applying it to robotic system. So the beautiful thing about this project is that tensegrity structure is so lightweight, it costs almost 0 compared to any construction or robotic technology that we have today. And actually one of my team members developed this robotic bridge tensegrity system when he was in his PhD degree in Apple, Switzerland. So our proposal was actually developing a robotic autonomous driving possible robotic system that can 3D print and navigate the moon. And then actually I have to say this one was actually last year. So we just passed it. Even this one was started last June, so it even didn't pass 1 year yet. And then actually I'm introducing a couple of thoughts that I had. Actually, this conference is really amazing because I always know I thought about some technology oriented, but now I think from materials wise, I can reorganize the way how or what I need to think about. So I'm talking about weather. We all know about what weather is. So at the beginning of the Earth's time, so there's mountain, and throughout the more than 10 million years, this mountain actually become salt. So I mean, this one shows that the kind of the puncture is represent some kind of physical weathering. And that kind of the above and lower part is kind of like chemical weathering process. If I take a look at about a little bit details about the weathering process, very interestingly, there's no linear, meanings in terms of clear cause and effects. There are a lot of unrelated causes create a network of effects, and finally, rock become soil, and then later decompose, and then become a lot of different types of sand or types of soil. So it becomes this. Let's take a look at about a little bit more about it. I redraw the history of Earth. So more than 46 billion years ago, I'm not a history, but one thing interesting is that the weathering process coming from 46 billion to almost 20,000 years ago. Then actually human being started somewhere from here. Actually, so I'm kind of rethink about the weathering process from the history of the Earth, and then actually humans start to reverse weather process. So actually, the Earth create all the soils and the powder. Then actually, we use those soils and create a building out of it by adding sometimes water, by sometimes oil, sometimes other binders. And if you check about the human civilization, that about 31,000 years ago, humans start to build some object, like by just human. Basically, they probably made the finger. And roughly about 18 years ago, humans start to build the tool, bolts, and other stuff. And interestingly, by using this, technique or materials, actually, human become really smarter. So interesting things happen. You probably all knows about dynasties, clay, terracotta warriors. Really amazing thing about this one is actually the production system, not the object itself. So production system, extremely modular production system actually came with it. So to create 1,000 different faces, but actually by modularizing the silhouette of a head. So one village can produce frontal heads, another village can produce rear head, and then once by combining them, that become a complete head. Hands, fingers. So one village can, once they kind of identify some kind of interface between fingers and hand to wrist. If they maintain the diameter or the shape of the wrist, any village can produce hands and another village can produce arms, and then they can meet together and become a modular assembly of human body. And the result is amazing, thousands of armies, soldiers, horses, dogs, they are all different, but extremely productive and creative system they can make. When before 210 BC. And now actually, again, this is a little bit another story, but we human beings start to make brick, modular brick. What is the meaning of those? And create a wall and flowers, floors and words. Basically, this can create architecture. Then create a city. So this and then this one is actually, I don't know, some of you are already familiar. Katarpuyuk. One of the first city made out of clay. And actually this one is built in about 7,500 years ago. And then actually this one is the model in the museum that actually imitates the city. And actually you probably well know about this one. So I kind of thought about that, what we do. So I'm going back to the theory about actor network theory. Bruno Ratter talked about man-government hybrid as an example of mediated situation. I'm kind of thinking about human material technology mediation. And then actually my example is reverse weathering on the Earth. So what we do, our civilization did was actually reversing weathering process, creating city. And then even later, people start to use fire, a new technology, and create porcelain. And even recently, now finding a new material is called a China clay. And actually, this one actually made a transparent porcelain. So now, after kind of thinking about this kind of this ortho process, and I told you it's my imagination or my vision that we're supposed to go this direction. So think about moon. So how can we? So I mean, my idea is going back to the end point of my Mars project. Can we really civilize the Mars for human being? And then this one switched to how can we civilize the moon? And actually, moon actually has the same process like Earth, like weathering process, but this is really kind of the moon's surface. And actually, that weathering process are kind of different from Earth's weathering process, and mainly that Earth's weathering process rather dependent on temperature, moisture, water, mechanical thing. But on the moon, it's rather dependent on basically radioactives, and then actually extreme heat. The lowest one is roughly about minus 180 Celsius. I'm sorry, I'm not familiar with Fahrenheit, but basically it's extremely cold compared to you, and extremely hot during daytime. So these extreme heat, but no moisture, and then actually radioactive is the main parameter that make this weathering process. So you can actually buy some of the Regulus simulant, meaning that there's some NASA specified physical specification that, because there are a lot of research on how to use moon Regulus. So actually there are a couple of different standards with moon Regulus, and actually, but basically the process is pulverize, desiccate, and sieve. Basically in each angle is just grind and bake it and then actually separate it and later blend them together. So this is something you can buy. It's not really on customer market, but if you contact the manufacturer of the moon Regulus, you can buy them. Very interestingly, in Korea, there are two companies who produce this moon Regulus, NASA certified. And actually, one is actually nearby university. I don't know why, but so I have a manufacturer nearby my university. So kind of physically, quite many things can be simulated to the moon Regulus. But one thing that still human cannot imitate is it is highly magnetically charged. So actually, they are kind of highly sticky, and it comes through all your body and your protection jacket. That's the problem. So basically, that made the whole astronauts have a lot of difficulty in walking or whatever they do on the moon. So, but the most importantly, that this difficulty again, in human civilization, human labor was kind of like quintessential part of civilization. But on the moon, there's no human being. So we are research about robotic technology that can be shipped to moon, and then that kind of create a kind of habitat first, and then later NASA actually kind of have a plan that send a human being after a city is completed, like SimCity game. So now actually this is our test. So we first combined Regulus with cement, and actually we tested the strengths. So actually we got roughly about 24 megapascal strength. Yeah, you know that roughly about 20 to 40 megapascal is a kind of current Earth standard. But there's no cement at all. So what can we do? That we have plenty of Regulus, and then actually the surface highly well powdered, so we can use that. But we have no binder on the moon, so what we can do. So we start to work on biopolymer. So we tried a lot of xanthan gum, guar gum, and a lot of different gums use them as a binder, and we tested, and roughly we have 3.5 megapascal. So, but this one is actually packed in a mold, and then we compacted and tested it. So, and then we tried another lambda, carrageenan, and sodium alginate. I'm not familiar with, I collaborate with another material scientist. So we tried it, and we roughly got 3.56 megapascal burst, and the other one is like 2.5 megapascal. This is accidental, but considering that the moon's gravity is 1/6 of Earth, so considering that it requires 20 megapascal on Earth, 1/16 is roughly 3.3 megapascal. So actually, we already make it successful. So this combination of biopolymer and moon regolith is actually successful. It kind of can be used on the moon for human inhabitants. And actually, then we need to think about how can we work on foundation and or civil engineering thing. So, and for this one, actually, we kind of found out the idea that so there are a lot of meteors hit the surface of the moon, and actually the heated area kind of like a very strong, work as a strong foundation. So then how can we use this kind of site as our kind of considering it as our foundation? Then actually we actually develop a robotic system. We use iPhone, but actually we are assuming that so this one actually can be connected to our cable-driven robot, and it scanned the surface, and already Neil made it. We can actually reconstruct the 3D form out of it. And actually, this is the process of recording it. And the clay is our moon surface simulant. And actually, this is what we got. So actually, yeah, we have to try multiple times. And this one, we can actually, this is not a picture. This one is reconstructed a geometry from those previous clay simulant of the surface. And actually, we are actually planning to 3D print on top of this geometry. So this is our first development of moon regolith combined with actually xanthan gum and other biopolymer. The problem is that we never worked with this moon regolith in biopolymer. So actually, we tried a lot, and this is one of the small samples that we successfully made. And probably you may all forgot about previous one that this is our robotic column system, and this one is actually testing by controlling the robotic system, which is each column has 3 stepper motors underneath, and 3 all together. Actually, it's kind of difficult to see here, but there's a kind of like model here in the middle, and actually this one is controlled that its position precisely. So actually we build a tensorial robotic system first, and then we test how they collaboratively control this cable-based system robotics. And then later, this one is our last work. So we developed a extruder system working with 3 cables. This one will be embedded to our cable system, and actually this one can 3D print moon regolith on actually on the moon side. So far, this is our roughly 8 months of development of our moon 3D printing technology on the moon. And so I kind of at the beginning of it, I talked about I'm a kind of like a convergence, kind of like I'm trying to create a knot or create a bridges between all different nodes. And why. So this one is another my favorite comment from Bruno Latour's. So he kind of said that when we have a really big and huge problems or questions, then he mentioned that we are powerless. Imagine about climate crisis, wars, or earthquakes. Last day in where was it, in Taiwan? Or there was a huge earthquake a couple of days ago. And then these patients are too big. And actually, I kind of thinking that there are really few researchers who focus on this kind of large questions or big problems or scale problem. Because going back to the academic culture, that academic culture asks us to narrow down our problems and solve it within that narrow question. But I'm kind of work contradicting to that kind of academic tradition that I kind of think what I'm doing is creating a knot between one disconnected part. And then actually, if I just kind of read Latour's comment that one of the reasons why we feel so powerless when asked to be concerned by these large questions is that we feel so powerless because the total disconnect between the range, nature, and the scale are so huge that our emotions cannot handle about it. So our habit of thoughts, actually, what we do is we become, what he said was a passing ear, and we just hear it once and we forgot it. So kind of what my research is doing is actually, so I kind of call it my mediated situation as reverse weathering is largely be about this disconnect, meaning that I'm trying to connect nodes and try to find or develop a solution to solve this large problem. Thank you very much. This is very common reaction from my audience. Powerless, no question. Don't know what to do with my presentation. Yes.
I love the presentation. Thank you so much. I'm wondering, as you expert in motion into robotics, do you have a big seed bank for movement? Like in farming, with these seed banks, really big seeds and preserve the seeds so that we can retain those that diversity, stuff like that. When I was watching that person like teacher robot having tattoo, I was wondering if you are like capturing movement in every bank somewhere.
Yeah, that's what a lot of researchers do. A lot of researchers do. People camera or desk camera, LiDAR, accelerates to actually capture the human motion. Yeah, so that's all the problem comes from. Because robot doesn't work like human do. Robots 6 or 7 axis arm doesn't work like human arms does. And very interesting thing is that we humans do not work same way. Imagine if there are 10 different chefs, they have 10 different ways of using knives. So from the beginning, it doesn't make sense that robot imitate how we humans do. So kind of like something new taught in our research is that I start from that. What if a human teach how to do? And this is I don't know someone here who is expert in education. The so-called constructionism approach. Constructionism is that knowledge doesn't transfer to student from a teacher. Knowledge is reconstructed by a student based on his experience and based on his knowledge. So it's kind of the thing that if I explain one thing here, if you have 30 different people, then they have 30 different understanding. So kind of like from the beginning, I thought this is kind of afterthought because we tried a lot of ways to actually imitate what humans do for robot apps. So then I realized that what robots do is very different from what humans do. And actually, the key thing is not really transferring what we do to robot arm, rather humans' knowledge and insight, our way of instructing young kids or other people. That our kid is kind of like having a kind of mediated situation between human instructors and novice robot student. And actually, this idea create a really effective way of robotic action that actually successfully doing what humans do, but natively there are two different ways of doing.
I have a follow-up question to that. I mean, particularly things like cutting, when you're dealing with materials that might have some inconsistencies.
Of course.
There's a response that the human has.
Yes.
That there's a feeling and they can respond in an instance. Of course, I mean, is that built into does the robot have that kind of sensors, or is it just simply the actions of
Yes, it has. They're encoded. So here's kind of two parts are going. So we ask human chef to teach robot, and actually the more he did, actually he understands how robot cut some food material. So actually he teaches them. And actually AI neural network that actually weight differently. The first one is weight ratio is a little bit low. The latest one is highly weighted. So this AI learned that hey, the human's teaching is better at the end of it, but first one's still valuable. So kind of after learning all this different iterative teaching, but weighting differently, so this AI actually created another new robotic gesture that actually successfully cut it. Very unique.
Is there a possibility for the robot to reteach humans?
Oh, it's really interesting.
So why is the knife a knife?
The easiest to quickest to huh? The easiest and quickest by dumb.
No. Why use if you're gonna have a human hold the robot? Why give it a knife that a human would? Why not give it just a sharp edge?
Oh yeah, that's really interesting point of it. Yeah, oh yeah, that's really great question. Actually, yeah, that's something we glimpsed before that. Yeah, actually, the knife is different from the regular knife because what we do is actually we cut it and then we slide it to separate the previous one, and then actually robot cannot really learn the subtle gesture. So actually, we kind of a little bit manipulated, added something attachment on the side of knife, and actually that's exactly your question. That why we create a new tool that robot more work effectively.
I have another part to my question. If you're trying to observe the human, why use so I first off I know it's your expertise, not mine. But when you said the robot can't feel resistance, you're particularly using AR. It does have encoded movement. It does pick up resistance.
Yes.
But and probably subtle enough if you were to ask it for the right information. But why not study the human's biological, neurobiological, physical processes innately? We know the human is really good at this task, and now it's like you're tying the human's hand behind its back and asking it to train the robot instead of letting the human perform at their highest potential. And to me, that feels like a with all due respect, a foolish way to think about how to learn from a human for a robot.
Yeah, exactly. Yes. There are a lot of various domains in robotics, and actually there are another researcher actually doing that. The reason why I'm not doing it is actually I'm not really that much hardcore robotic engineer. That's one thing. The second thing is actually I'm more about software development rather than hardware development. So actually I'm developing rather platform that using existing robot arms. That's my more focus about it. Probably that's why. But I'm not sure that there are other areas that do exactly what you asked.
It's interesting because it started with a comment about from the bottom up, and it's very interesting to think about these problems, whether they're top down or bottom up. Sure. Where do you start? Actually, should you start in the middle, bottom up, or top down?
So far, yes, I really go to the bottom, but actually I'm more about, but it really depends on the characteristic of the grant that required.
Yeah.
So actually, and then that one it required that actually the Korean government really use it within 3, 4, 5 years time frame. So that's why I kind of like I start from that.
Let's say a little bit more applied.
Yeah,
So you don't risk
more on the application side instead of pure scientific research or robotic engineering research. Yes.
So the gum for the robotic printing on the moon, the binder is being sourced from the moon, or that's being sent with the
very good.
And where does it come from?
Yeah. So so it's supposed to be biopolymer, and then actually we are still exploring and navigating, and actually we found that one bacterial or algae system that can grow on North Pole side. So it can actually resist to very low temperature. So actually our first goal is building a smart plant first. So raise algae and biopolymer from there. And then actually that's the first stage of it. And then my robotic system used that kind of mass-produced biopolymer and then mixed with regolith. Yeah, exactly. You really see the point.
Does the magnetic nature of the aggregate help?
Actually, that's really unknown territory because there's no current Earth technology that can simulate that part. So that's kind of like really a hard part for us. And but it's kind of lucky for us that because there's no current technology that can simulate bioactive development part, so we don't need to search it because no one can. But that's that every so actually my moon research is this is a consortium with Stanford and University of Miami, Stanford with NASA Ames Center and the University of Miami work with NASA Florida Research Center. So we interviewed several astronauts and they all mentioned about this magnetic part, but there's no current way to solve that. Yes, it's really big, important, but hidden area.
Building on that, just out of naiveness, could you simulate with using a vacuum? Could you have a vacuum container?
Very interesting. So Korea, the Association of Construction Industry built a moon. This basically is a kind of big oven. It's like the size is like a 12-meter diameter size big oven. So it cannot really simulate the zero gravity thing, but it can simulate the low temperature and high temperature and a little bit of a graphical simulation. So we can actually the end of the fourth or fifth years of our requirement is actually run our robotic system in that environment. Very, very high and then we have to prove that it's really work in that environment. Yes.
I found your presentation joyful and wondrous and also extraordinarily disorienting.
Yes.
And so I'm going to ask a nest of 3 questions that I hope you can kindly offer back to help steady me in my vertigo. The first is to ask you to go over this idea of reverse weathering, which is a novel conception, and I think it bears some reflection. What does it mean to you, and how did you come up with it, and how might we relate to it? That's the first question. Second is that given that involves, I think, some kind of reversal, at least almost a metaphysical reversal, looking at something upside down, then how might we find those kinds of turns of mind in ourselves so that we can navigate? In that, I'm trying to respond to the provocation you put up on the screen, because otherwise these questions might crush us, destroy us. They're frightening. Some of them are lovely, some of them are really bloody awful, unspeakable. And third, how does Bruno Latour really belong in this discussion? And what does his particular voice and the movement that he offers have to offer us in the situation that we find ourselves in today?
Online you expect that I give a good answer, but I'm already also expect that you already have an answers. Okay, so easy ones first. So actually the reverse weathering for me. Okay, so simply I'm a metaphorical thinker. I'm one of the many person who think analogy is our base mechanism of thinking. Who is the University of Berkeley? So there are a couple of different theories of our thinking, and then actually he argued that analogy is our basic ways of thinking, because we cannot think something we didn't expect or we didn't experience before. Basically, all we think is something repeatedly or variated experience we already have. I suddenly forget his name. He's really famous in the United States. Kind of like, do not think of an elephant. So, can you not think of an elephant? Okay, so you cannot. we can't. We cannot think of an elephant because I told you elephant. That's the analogy. So how we cannot think of an elephant? Because we cannot think reverse way.
Yeah, I don't think so.
Yes, so we cannot unthink about something. That's something I mentioned about. So how can we think about unthinkable? So how can we avoid of thinking about elephant? Thinking about rabbit. But by continuation of this one, we think about it, then we realize that we can only think about what we thought about before. So this weathering process is kind of like my way of try to understanding about what I am doing and try to use a kind of analogy to frame it. So for me to think about it. So that's pretty much it. So that's brutal, I know. It's because there's something unique thing I invented. So there's no logic behind it. So it's just kind of like my effort to use the weathering process as a kind of a human civilization reverse kind of like those powder into city. So kind of I understand that it's by imagination thing. So that's why it is so brutal for you to think about. But that's all kind of good ideas about you are uncomfortable about that you didn't think about it before. So that's our basic nature. There are two more questions, but
I just want to interject.
Okay.
Have you considered the self-assembly lab at MIT?
Oh yeah,
which is also done with reverse robotics. Yeah.
Oh really? I didn't know about it.
Yeah. I mean, they're doing a project where they're using natural wave forms from the ocean to recreate.
Yeah, 4D.
Yeah.
I see. Now I'm kind of thinking. Two questions. Sorry, I forgot that.
Well, I was. You've already answered the second in some way. But maybe you could also just comment about the tour.
The tour, yeah. That's one of the reasons that I was fascinated by the thinking is actually there was an incident several years back in Walmart. A 2-year-old daughter. It was sitting on a cart, shopping cart, with her mother's handbag, and in the handbag there was a kind of pistol, and then actually the daughter accidentally played with the gun and accidentally killed her father. And then I kind of the reason why I'm interested about this is that imagine 2 years old daughter. It doesn't matter whether it's 2-year-old son. Imagine 2-year-old son. They cannot survive without continuous guide or support from others. But when they combine with a gun, they have a capability or translated capability of killing others. And this part was really amazing to me. And then considering that, and then actually I kind of thought that this is why we want to develop technology and want to work with material, want to work with developing new synthetic or new rich or hybrid or translated situation. That's what I'm interested in. And what we are doing today, thinking about it from material with reality, and then inventing new interpretation. I mean, bamboo, to me, again, is just a food for panda. But now, bamboo became extremely potential component of structural or fencing material. How this can happen? To me, what is the quintessential part of it is our creating of mediated situation with inventing new idea and new technology with new material. So I kind of like it is my way of summarizing our second session, but it's just again, this is my personal interpretation of civilization or development technology. And that's what Bruno Latour's theory about that current civilization or current human development is not simply about man's history or words to it, but rather it's a combination of between man, female, and technology. So so that's what Latour interpreted about his research about human technology. So that's trying to referencing him to this conference, that what we are doing, how can we summarize this conference? That we're thinking materiality from it, but actually that create another mediated situation. Just my personal imagination. So actually I concerned about that we finished too early. Now everything is left out successfully done. And so actually I asked to re-invite two presenters here. So kind of having, if you have any questions you never mentioned, that this is your last opportunity to this amazing presentation. Okay.
I'm curious how everybody is like putting comfort into their design. Thinking about, civilizing the moon with robots. If robots are going to be the first, they're going to be the foundation for human life there. How is comfort for humans being involved in the design process? Because the soft body, robot body, like it's just totally different. So I know that you work primarily with robot arms, but I'm still just thinking about like thresholds and more from an architectural perspective. And so this combines with the mycelium and the ground earth stuff too. I don't know if we'll be excavating with robot arms, moon material, and then like creating furniture with mycelium, like how that's all going to work out. But I'm just curious how everybody is considering comfort for humans in their design process.
Very different questions to answer.
Maybe just to add, I'm wondering about if aesthetic decisions have gone into the idea of the 3D printing on the moon. Like, could we add pigments to the moon mixture to make it more? Is there any consulting with people about what they want their moon habitat to look like?
Not on the moon project, but for the Mars project, there was a specific requirement from NASA. So the requirement is 4 engineers can stay safely in Mars environment, so do some research. So it's supposed to have enough space for sleeping and bathroom, living, and food storage and other equipment. So there was really specific requirement and specific physical requirement for Mars habitat. For this one, moon habitat, actually, I have to redefine. And there's one condition from Korean government that's actually on the moon. The problem there are two important problems. One is meteors, so they regularly hit the surface. So supposed to be some protective loop supposed to be offered to any astronaut. Second thing is actually very strong rays from the sun. So actually, so these are two very difficult requirements from the government. So actually, we are actually moving as some engineers to handle. Actually, we are actually one of our consortium. We have a civil engineer to handle that kind of requirement. That's the thing. And going back to the original question, I'm not a expert in feminism theory, but one thing really great about I'm really Louis Learner feminist theory that why that the European countries are more capable than other countries is because from the I may be totally wrong, so please correct me if I'm wrong. From the Viking period, which is from the 3rd to 7th century, why Vikings are so dominant and North European world. And then actually one of the reasons was because, you probably know better than about Vikings life. And actually they live in, very, bad situation that agriculture is not sufficient to have enough food. So their economy is based on invasion. So each village actually through the kind of fight or wars is just the only way to get enough food is just taking from other villages. And then actually as time goes on, even that taking all the food from other villages are not enough, then actually small number of people go to England. And then actually England was actually have enough agricultural technology, so they don't really need to fight. So actually Vikings actually, and then actually Vikings actually manpower was so much stronger than England's. And one of the reasons was that, again, just correct me, that member of Vikings include children and females and even elderly. And actually, then how does it relate to feminism? Is that the way of utilizing limited intelligent brain, if we excavate female brains out of the country, which country is more capable? You mean that one country take advantage of both male and females intelligence versus one country only uses males intelligence? That's only the first one. Because in terms of population, it means that only 5% of populations are intelligent enough. Then as soon as one country removes the 2.5% of population, they don't have enough brain. So now this feminist idea that utilizing or take advantage of something uncomfortable territory is what I'm trying to say about this Bruno Latour's or connecting thing. One of the most difficult parts of designers education is that they hate to learn computer programming. I have to say they are generic phobia about computer programming. That's why they love to learn Grasshopper. But the more they learn about Grasshopper, the more the ways of thinking is blocked by Grasshopper. They just only think about Grasshopper's way of thinking. And then when I ask them, why do you so scared about? Because in teenage students, elementary school students, these days start computer programming using Arduino or what is that? The Lego kind of like Minecraft thing. Like, so even children learn computer programming, they don't have any problem with learning and including Scratch. But why a dirt graduate or college student who is in design? And actually this mind problem is really the biggest problem when they learn about new things. And then those students who have no fear of learning new things, and those students have a fear of one thing. This is not simply representing one thing. Those who has a habit of fearing one thing has actually many fears. So actually that thing actually kind of limits the range of one person's learning capability. It's not about hardworking. It's not about smartness. It's not about skill sets. It's just all about mind that actually defines the area of growing. So going back to the question, why do we need to work on moons or bonds? Because those are too difficult sometimes. Because that opens my capability to others. Because if I have a fear about approaching moons, then actually I probably have fear about other things too. But when I don't have approaching moons, and then when I don't need to worry about my imaginative things to present to you my moons project. Again, these are all imagine-based technology, not really weird if you ask me, do you have any concrete evidence about it? No, I don't have at all. And actually, I don't have a way to collect those concrete evidence at all. But if I start to worry about it, then actually no project can go further. So for you, yes. So again, get Wiley that instead of asking about why bamboo, we better ask why not bamboo. It would be the wisest answer today. So why not moon? Why not Mars?
Thinking about comfort in terms of our paper, I mean, one thing we were trying to do is kind of justify the project. And I think we were looking at this document called the 14 Patterns of Biophilic Design, which lays out kind of justification for biophilic design criteria. And the idea is that the research suggests that these things are good for human comfort or human well-being, that biophilic principles can increase human well-being. So what we're trying to argue is that that actually geophilic or geomimetic criteria or design processes can actually achieve some of these criteria better or as good as biophilic design processes. So that was kind of our justification. So like, for example, they talk a lot about the benefit of fractal patterns for human well-being and like this connection to nature. So what we were looking at is by eroding this wall, we're creating these fractal patterns and somehow that's beneficial for human comfort. I feel like maybe this is most direct in your research.
Yeah, I can speak to it a little bit in my research. In terms of it wasn't so present in the presentation of the scope of this exact research, but in terms of scaling this to like a furniture application, the way that I kind of think about comfort is in like slightly opposing like dichotomy. On the one hand, I think that preservation or the focus is very much on like a really much broader time scale than is human centered. So like an emphasis on sustainable materials that healthily re-enter the ecosystem. But that said, there's no point in creating a product that is supposed to be used by humans unless it serves a purpose for them. And so in that sense, it's kind of comfort is like a necessity. So in thinking about something like a stool or a chair, if it's not comfortable, should it really exist? It is kind of the question that I ask myself. And so like exploring mycelium as an example from a very material-driven design perspective, you might like kind of think that the human-centeredness and ergonomic factors are secondary, but the way that I think about it is if the kind of material-driven design process does not result in something that is ergonomic and comfortable and overall good for the well-being of humans, it doesn't need to exist. So it's kind of, to me, I think about comfort in the sense of like knowing when to move forward with something and when to realize that, you know, maybe this is not an appropriate use of the material, an appropriate application or something like that.
I mean, even I found it like, even with your kind of criteria for which of these finishes was working well. I mean, I think even to me, it's all kind of about comfort. It's like how you're giving these artifacts to people and saying, how does this make you feel? Like one thing I was going to ask is if you did any research about like how these finishings affect the like waterproofing of the mycelium. That's where I thought the presentation was going, maybe when I read the title, but it's maybe more novel that you're primarily concerned or largely concerned with how these textures, colors, scents are making people feel and how they are affecting comfort.
Yeah, actually, I think that's a really fantastic way to frame it. Because that is really essential to it. And I haven't yet done anything with water, like studying the waterproofing. I think a lot of these studies will improve the waterproof like nature of it. That's definitely one of like, the next steps. Yeah.
Just wanted to make a comment in response to all of this, which is I think it's interesting that like we just touched on senses, sense of smell, the sense of sight, really the one that many aesthetics are being kind of trained through. And with the earth and construction, actually, it's things you touch are not the earth and construction, but actually in terms of well-being, it's well known as putting your feet on the ground, in the ground, right? The direct contact with the earth has like impacts on well-being. And so it's just interesting to think about really as we approach thinking about many of these issues in a more finite way, how do we address more of our human consciousness?
Yeah, I could actually make, sorry, I can make a quick comment kind of building on that. I think that another way we build comfort is reattaching ourselves to like the grown or geological or natural environment. We're so far removed from that in so many ways nowadays. We don't know how our products or even like food are made and produced and get to where we are. And this has not been like the focus of my research, so I can't say with confidence, but I think that's an incredible disservice to us as humans. And I think that we can build comfort by gaining familiarity with our more natural resources and looking at things like a little bit more holistically.
Maybe one final comment and then we'll close. Okay, wonderful. Thank you so much for a very engaging day. It's been wonderful to have all the audience participate so extensively, and I really appreciate the way that it's been a conversation all day long. It really has. I felt some of the conversations that were happening in small group circles should have been a part of the main conference, and so I feel like we've just been having really rich dialogue all day, and that's the intent. So we're ending the session for the day, and I really appreciate everyone's participation. We'll begin again the same time tomorrow morning. Really happy to have a full day planned for tomorrow. We starting actually at 5 o'clock, so it's already open. There's an exhibition for Marlon Blackwell's work. So continuing from the presentation last night, keynote that happened last night, there will be an exhibition of his work that's happening at the visitor center, and we're gonna probably walk over there together. But I will also put it up on Google Maps so that people can look at that and join us as they wish. Let's say here. Yep. This is it. So I don't speak Korean, but it will.
I'm walking over now. If anyone's interested in taking a walk over on the next.
So yeah, we have the dean, the chair of the architecture program, Daniel, and he's going to be headed there right now. And so it's basically a few blocks away. So we're here at the Republic Building, which is here, and it's basically up here on 5th Street. And what is that cross street?
Franklin.
5th Street and Franklin, right there. Right, just so you're aware, right across the street from the visitor center is First Christian Church, which is the first Hillel Saarinen, the only Hillel Saarinen project in town. And then down the street is the Arrow Saarinen Bank, right here. And then you have 2 Kevin Roche projects here, as well as an addition by Kevin Roche there. And a plethora of other amazing architecture kind of surrounding it. So it's a nice walk, actually quite a nice walk. So it's just up past 2nd and 3rd, 4th and 5th and over. That's it. Really easy to get there. Hope you can join us at the reception. I think it would be worth our time to see Marlon Blackwell's work and to be able to support him, especially as he's doing work here in Columbus. So it's really wonderful as well. So thank you again. Let's have a round of applause for everyone who's been involved today.
And we'll have a full program tomorrow, culminating with presentations by the workshops, including the bamboo workshop that's being fabricated right now over across the way, and all the other workshops that we've been working with. So that's how we're going to culminate tomorrow, as well as with a walking tour of downtown Columbus, Indiana. So thank you again, and enjoy the evening.